theme 4. Our first speaker probably needs no introduction. He's had a long career in meteorology and climate research on monsoons and is the current director of IITM. So Christian, over to you. I'll give you a bell when 2 minutes to go.
Okay, sure. Thank you, Chair, and good morning to all of you. It's indeed a great honor for me to make this presentation. Today, I will be talking about the possible intensification of the monsoon Somali jet under global warming. So the monsoon itself, the Indian monsoon itself is a very fascinating phenomena. People have studied it over hundreds of years. And Somali jet is, I think, one of the early discoveries by Joseph and Raman. It's a very important low-level jet in the monsoon. And so it came from observations. And subsequently in the 70s, after the Monix, there were many papers by late Professor T.N. Krishnamurthy, series of them highlighting the importance of the low-level flow, cross-equatorial flow in the Somali jet. And more recently, there have been new studies, especially by Rodwell and Hoskins. I will be touching upon that. And also Boos and Emmanuel. And it has implications for the onset of the Indian monsoon. Professor Mohanty and peers, they did some interesting work on the monsoon low-level jet, how its kinetic energy increases before the onset. Soman Krishnakumar, Anantakrishnan and Soman. So the contributions have been immense. So I thought I will just open my talk with that. And I cannot be, because in the short time, I will not be able to go through all of them. And so the big question is, how will the monsoon circulation and precipitation respond to global warming? And monsoon is really a very complex dynamical system, the Indian summer monsoon. And we have the mighty Himalayas to the north and the Tibetan Plateau and the mighty Indian Ocean. And then we have the cross-equatorial flow, which crosses the equator. And equator has its own unique dynamics because of the Coriolis parameter is 0, but beta is very large. So that has very unique properties and compared to the extratropics. And then you have this beautiful system, so when the land gets heated up during the pre-monsoon and early monsoon months, you are basically, due to the lesser heat capacity of the land, you are setting up a thermal gradient and also a pressure gradient. So the monsoon circulation is set up. This is all we learn. And then because of the Earth's rotation effect, you have the low-level jet, which picks up this moisture from the Arabian Sea. That's the key point. So there is a lot of evaporation from the surface, and which takes the moisture. It interacts with the orographic barrier along the Western Ghats, the Myanmar mountains. So as the warm air rises up, it expands, cools, and condenses. It forms clouds, and the heating due to the clouds is large. We know that from the satellite observations, from the TRIM PR data, enormous amount of latent heat of condensation, which in turn acts as a feedback on the low-level winds. So it's a highly interactive system, and it is also related to the ocean because when the monsoon winds turn off the east coast of the Africa, so there's a lot of water movement further into the Arabian Sea and divergence of the water. So the cold water has to upwell from below, and it brings all the nutrients. And so there's an entire biogeochemical cycle that is linked with the monsoon. And this you can see from the satellite. The models are able to do that. So this is a very, very complex dynamical system. And and it's also affected by its own internal variabilities. People have talked about it. And there are also big drivers like the El Nino Southern Oscillation and the modes of variability of the IOD, and also the MJO. So they're all interacting with the monsoon. Now we are asking the question, how will climate change affect the Indian monsoon? This is a challenging question. It's not a very simple question, especially given that the precipitation and circulation are very strongly linked. That's the key point. So the Somali jet, the low-level jet, and the monsoon precipitation are closely linked, and they're interacting. It also involves the moist convection. So it's a very complex problem. That's the first message. And as far this is the quick assessment from the IPCC, because we understand there have been many drivers of climate change, primarily the greenhouse gases, which have led to warming. And then we also understand about the aerosols, especially the direct effect of aerosols due to the dimming. Of course, there have been land use changes, so their impacts are more regional, but our understanding is since at least the IPCC AR6, we have lesser understanding of those impacts. So I will focus mainly on the two main drivers to begin with. So when I talk about aerosols, we are really talking about the emissions that have come from the Northern Hemisphere, from Northern America, Europe, China, East Asia, South Asia. And aerosols are basically, they try to cut down the incoming solar radiation. And in fact, IMD's motto says, Aditya Jayate Vrishti, sun makes rainfall. So that's the slogan of the Met Department. So if you're blocking the solar radiation reaching the earth, it has an impact on the precipitation that we roughly understand. So with this increasing anthropogenic aerosols, there are observations for this. They have led to dimming. And so when you cool the northern hemisphere relative to the southern hemisphere, the ITCZ shifts to the warmer hemisphere. This is known. This can be explained. And it is supported by theoretical arguments. But the question is, greenhouse gases, they have a very long lifetime, unlike the aerosols. Of course, aerosols produce large gradients, spatial gradients, which can be substantial. It can affect the hydrological cycle. Greenhouse gases, on the other hand, have a very long lifetime. They absorb basically the infrared radiation, the thermal radiation emitted by the Earth, and they trap the radiation. And it also increases the evaporation. Water vapor increases, which is again a greenhouse gas, important greenhouse gas. It amplifies the warming. And it is going, because of its long lifetime, the greenhouse gases is going to stay in the future. And Europe and North America, they have almost reduced the air, improved the air quality. The emissions have improved. And and even China is doing that in recent times. And this is also, India is also on that way. So basically, in the historical period, the evidence we say that from the 50s to the 80s, the global land monsoon precipitation decreased, including the Indian monsoon, partly because of the aerosols, but has since increased in response to the GHG forcing and large-scale multi-decadal variability. I'll come to that. And during the 21st century, the land monsoon precipitation is projected to increase because the global warming is going to continue. It is projected to increase in all time horizons and scenario. And basically what we say is the African and the Asian monsoon will intensify in terms of precipitation compared to the North American monsoon. So there's going to be this is projection in the future, there's going to be a east-west asymmetry. With regard to the circulation itself, it is projected, this IPCC 6th assessment report says that the Northern Hemisphere monsoon circulation will likely weaken. And this is the assessment based on the CMIP6 models. But I want to ask this question, how will the Indian summer monsoon precipitation, not just the precipitation, because precipitation is mostly coming up because of the thermodynamic effect, more water holding capacity, rainfall increases. What will happen to the circulation? That is the important point. And all the many models, they have projected that the circulation will weaken. And the logic is, this is from the 5th assessment report, because this is just a schematic of the present and the future. When you have the greenhouse gases, of course, the land warms faster compared to the ocean. There is more evaporation, more enhanced moisture, and it will rain out. But it also says that there will be the rate of increase of moisture happens at a much faster rate compared to the rate of precipitation. I'll come to that. So when that happens, they show the stability of the atmosphere will increase, and so the circulation will weaken. This is what has been projected, and in the future. And this also, the famous Held and Soden hypothesis, the physics behind the weakening of the circulation, but more precipitation. So when you talk about the vertical velocity, when you talk about precipitation and linked to the circulation, you can say precipitation is almost proportional to omega, that is the vertical velocity, into Q. So if you make these changes in the precipitation and change in the humidity and the vertical velocity, we know that water vapor increases by about 7% per degree warming. But all these models, they're showing precipitation will increase only by 2%, which means the vertical velocity should decrease by 5% per degree Kelvin. So this is valid for closed domains. Is it valid? The question is it valid for the monsoon? And in fact, when you look at the entire time series, I'm not trying to attribute from this. This is 1871 to 2023 All India rainfall from IITM. We see this interdecadal variability. And so since the 50s, you do see some decrease till the early 2003 or 4. And so that is partly because of the aerosols. And thereafter, we see a slight increase in the increasing trend in the precipitation. And so what we did was we just took the composite of the precipitation winds from the GPCP and ER5. And by the way, this is the work of my student Ashwin Sagar and Sabin, who did the model experiments. I forgot to mention that in the beginning. So when we take the difference 2003 to 2020 minus 1979 to 2002, we see that increase in the precipitation over the western part of India, and also an intensification of the circulation itself, the southwest monsoon flow. And this is statistically significant. So what we see from the observations is that when monsoon precipitation increases, it goes hand in hand with the circulation. The monsoon low-level circulation also intensifies. So basically, we want to have a theoretical basis to understand why the monsoons should change both the circulation, and having the theoretical basis is very, very important. And so I'm going back to this work by Boos and Kwong, which was published in Nature in 2010. And Mark Kane has written a nice news and views in Nature. Basically, they argue that they use the quasi-convective equilibrium framework for the monsoon. And so the thinking is moist convection is important. And basically, when you have the monsoon winds, which moisture-laden winds coming from the Indian Ocean, it increases the maximum subcloud entropies over the Indian region, not over the Himalayas. And the Himalayas are basically blocking the cold and dry air from the north. So basically, you have the high energy air mass over the Indian region, which is undiluted, and it remains favorable for moisture-driven convection. And this underlies the strength of the monsoon. So the strength of the monsoon is basically linked to the moist convection. And they also further go on to argue that, the Tibetan Plateau is not really an important component. It's not a thermal forcing. Of course, Tibetan Plateau and the Himalayas, they block the dry and cold air coming from the north. So the monsoon intensification, the strength of the monsoon circulation, it depends basically on how the moist convective processes are captured in the model. And you have to keep this environment, preserve it. You cannot allow the dry air and cold air coming from the north. And that is one of the key. So high resolution becomes important there. And the moist convective framework, this was started from Arakawa, Schubert, and then series of paper by Emmanuel and so on. And I'm not going into the details. So this is a very important thing we have to keep in mind. And what do we mean by the moist convective quasi-equilibrium? Basically, when the subcloud layer entropy, moist entropy, or the moist static energy, it increases in the lower level, just at the cloud base. And at the free troposphere, when the moist convection happens, huge amount of heating is released. And the free tropospheric temperature, which increases in the upper level, that is coupled to the convection. And that is the key concept. So in the free troposphere, the temperature has to increase. And for this, the Himalayas are very, very important, as well as the East African mountains. So, and there was another important paper by Rodwell and Hoskins. So they talked about the mechanisms that sustain the low-level East African low-level jet. And that is basically the Somali jet. The main argument is that, of course, you need the diabatic heating for the monsoon heat source. And you also require the surface friction and the East African mountains are very, very important for orienting the flow, the jet along the over the Arabian Sea. So these are two experiments. Yeah, so on the left axis, you have the ECMWF analysis, and then you have the standard integration in the middle, which has all the mountains and heating and frictional effects. And when you drop out the East African mountains, the low-level jet slows down. So basically, the monsoon low, there is a PV modification. I'm not going, the potential vorticity gets modified as there is a cross-equatorial flow. So for this to happen, you need the heating as well as the frictional effects. The East African mountains are very, very important. And this was earlier, this is one of the very interesting papers by Krishnamurthy et al. They looked at the three-dimensional planetary boundary layer of the Somali jet. And you can see this is the longitude and latitude distribution of all the mountains along the East African coast. And they have put all these different countries. And associated with this, they find that the winds off the coast of East Africa, the meridional winds, they almost extend up to 3 kilometers in height. And the strong jet forms off just immediately off the East African coast. And then it undergoes advective acceleration in the near equatorial balance. This was a very important study. And again, this is a very important work by Boos and Emmanuel. Why does they studied the annual intensification of this Somali jet in a quasi-equilibrium framework. What at the bottom panel, I have shown the intensity. This is by Boos and Emmanuel. This is an intensity of the jet speed index. This is basically the kinetic energy they have averaged, I think, from 5 south to 20 north, 50 east to 70 east. And you can see the onset date, the blue dot above, a sharp increase in the kinetic energy, which people have. This is what Krishnamurthy et al. Used in 1981. A rapid increase, sudden increase in the kinetic energy around day 156 of the calendar year. That is around early June sometime. And why this happens? It is again because of they use the CQU framework. They find that the moist entropy develops over the Arabian Sea and Bay of Bengal, and there's a deep tropospheric ascent. And in the free troposphere, there's an increase in the temperature. And these are the composites just during the onset on the right panel, the change in the Somali wind, the change in the wind over the 10-day period preceding the jet onset. You can see a very strong intensification of the jet in response to the deep convection, moist convection. So this is the main point. So we need a theoretical basis. So the key point is when you use a model, that model should have these ingredients if you want to really study the monsoon. It should have these. So we use this high resolution global model, which we have been using for quite some time. And Sabine has made several runs. This is from the French group. This atmospheric model, it was developed by Sadourny. And we used it for several of our climate change studies. Basically, it's a global model with a variable grid resolution. So over South Asia, the grid size is less than 35 kilometers. And so the interesting things, it is able to resolve all these narrow mountains along the Western Ghats, along the Myanmar coast. And I'll just take 3 minutes. And as well as the East African mountains and the Hindu Kush mountains, narrow mountains, which is very important. It also uses the Emmanuel scheme, convection scheme, and it has a good boundary layer. So all these ingredients are built in, so it prevents the dry and extratropical air coming into the region. It's a good model for studying the monsoon. And this is the historical precipitation, 1995 to 2004 or something. And this is from the GPCP and ERA. It has a good cross-equatorial flow. What we find is we did 2 runs. We are basically giving the SST from the IPSL coupled model, prescribing it. And this it's only atmospheric only model. And we are looking at the changes we followed the SSP 245 scenario, that is for the period 2081 to 2100 in the far future, and compared to the historical period. And the SSP 245 GHG has only greenhouse gas forcing. It has no other changes. We see a fantastic intensification of the monsoon precipitation as well as the circulation. The Somali jet really intensifies. We also see that there is an excessive drying right over the equatorial region. This we feel is because of the lack of ocean atmospheric convection. If you have a coupled model, this dry bias will reduce. And not only the low-level jet, the upper tropospheric anticyclone as well as the easterlies in the upper level will increase, strengthen in future. That is what it says. So it's basically the deep convection and the pressure, the SLP patterns are shifting more westwards. They're intensifying over India. And mid-tropospheric potential vorticity also strengthens. This has implication for low pressure systems. There's also there's modification of PV. I'm not going into the detail. And we also looked at these maps of sea surface temperature and also changes in the surface moist static energy and the free tropospheric temperature, very much in line with the CQU framework, which basically the moist convective processes, they try to favor this intensification of the flow. And in addition, we also looked at the heat source, the apparent heat source proposed by NI et al. And there's a very strong, due to the heating, latent heat of condensation, we can see in the SSP 245 GHG, a strong positive vertical gradient. Basically, this is going to intensify your mid-tropospheric and lower tropospheric flow, the positive vertical gradient of heating. And when we look at the changes in the precipitation and water vapor and vertical velocity, we find that precipitation increase is substantial. So whatever water vapor is evaporated, it is efficiently converted into precipitation. And that's a big change. This is over the Indian region, whereas the humidity change is much smaller and you have a vertical velocity increases and therefore the circulation increases. So the question is, it has implications. We also looked at the 10-meter wind speed. So during the summertime, as well as the annual, there's an increase in the wind speed at 10 meters. And these are the changes related to the HIST. And you can see almost in the SSP 245, there's more than 10% increase over the Arabian Sea and other areas. And this was an interesting paper. So this has implications for generation of wind power over India. This was a paper by the NRSC people. And they say that many regions, you see also the EEZ. The Indian EEZ is a region where there is a very high potential, as much as 5%, 5 to 6.7% of total electricity generation for India in 2030. That's one of the key messages. And during the summer monsoon months, because of the low solar radiation, because of the clouds, we have a compensating effect due to the winds. So if indeed the winds are going to intensify under warming, this offers a huge opportunity for India, for the power generation. So this is my basic summary. What we find is it's a complex system and the climate change is happening. It will continue. In the future, as the global warming continues, there is going to be not only increase in the monsoon precipitation, so we need to conserve the water, but also there is the low-level Somali jet cross-equatorial flow will intensify. We discussed the mechanisms, and this has implications for wind energy generation potential. And in the future, we want to couple this model with the ocean model, because this also becomes an important tool for studying the monsoon dynamics, Indian Ocean circulation, and marine biogeochemical interactions. Yeah, thank you very much.
Thank you very much, Christian. Do we maybe have one quick question from anyone? One at the back here. No, over here.
Thank you. Nice talk. Sir, what are the physical processes that are primarily responsible for intensification of Somali jet in your simulation, like SST gradient or pressure anomalies or other dynamics?
Yeah, I think the moist convection intensifies. That is what leads to the main factor, intensification of the moist convective process, and the vertical gradient of heating, because as the convection increases, the water vapor rises and forms deep clouds. So extreme precipitation will increase. So the heating due to that, due to the release of latent heat, is going to intensify the monsoon. So the key is how well you capture the moist convection. That is going to be fundamental. That's why I had to give all this background about the CQU theory. So you need a good model, you need high resolution model. You have to understand why it is happening. And so the focus was of trying to understand why the monsoon is really intensifying. This view is different from what has been traditional view of all the CMIP6 models, that circulation will weaken. So this is a kind of counter argument to that.
Sir, is there any possibility that intensification of Somali-Z could lead to extreme events like
Yes, that
monsoons?
definitely. So extreme precipitation is also increasing. But I am only looking at where are the true. So we have to improve our early warning systems and how to alert and so disaster management, those issues, that is on one hand. But I'm also seeing where is the hope? Are there opportunities? Because if the monsoon is going to strengthen, how can we, is there a potential for wind energy generation? What are the opportunities? So with in that context, I just presented this talk.
Okay, I think we better move on. So thanks very much for your question, and thanks very much to Christian for the talk.
Yeah, thank you.
I think maybe is there? Oh, you're here. Yeah.
Thank you.
So our next talk is online by CP Chang. So do we have CP online?
I'm online.
Hello.
Can you hear me?
We can hear you. We cannot see your slides yet.
Okay. I hope you can see me now.
We can see your head.
All right, that's probably all you're going to get to see. Let me grab my PowerPoint. And do share. I have a backup PowerPoint outside. If I'm unsuccessful, someone could put my PowerPoint on it.
Can we put the PowerPoint on screen?
Let me try mine first. I'm almost there. Okay, now I need to share screen. Sorry, I'm always sluggish on these. I'm still trying to get this. I can't do both at the same time. Where's my PowerPoint? Here it is. Is my PowerPoint on screen?
Not yet.
Okay.
It may be that we can share it from here.
It's not on the screen?
No. Oh, hang on. It's starting.
It's on the screen now?
Yeah.
Great. We're making some progress. Probably you can read my title. I have to do something else here to put it in
full screen mode, yeah.
Yeah. It doesn't seem to want to.
F5 apparently is what you can press.
I can't move it for some reason. Oh, okay. Now I got to move it. I'm one step from. Can you see the full screen?
Yeah. So please go ahead, CP, and I'll give you a warning after you've spoken for 18 minutes.
All right. So my topic, this title is motivated by a textbook published by Lyon and Evans saying that says Bill Gray's earlier criteria for TC genesis, one of which is that tropical cyclones has to be 5 degrees away from the equator. And that condition may be can be relaxed because of more recent observations of TC in the equatorial belt. The more recent means after probably the satellite era. So maybe we missed the equatorial tropical cyclones because we didn't have satellite coverage. And this is the picture they produce in their textbook. And within the textbook, this is the 6 conditions of Bill Gray, which the last one says 5 degrees away. And that's based on 1968 Gray paper. The reason they say this was they're quoting our paper, 2003, that we observed the tropical cyclone Vamay, Typhoon Vamay near Singapore, near Christmas time of year 2000. So they based on that our studies, and maybe this should be relaxed. However, today I'm going to say this is the wrong statement because Vamay is unique. I'll give you the reason why it is unique and why we don't expect that to happen too often. Okay, here, these are the wintertime DJF, everything based on boreal seasons. This is the distribution of the count of vortex center. These are synoptic scale vortex center, just frequency distribution. In DJF for the entire tropics, the highest occurrence is what we call Borneo vortex. And there's a very good reason, because you have northeast monsoon and sometimes pretty strong. So you have strong winds coming down South China Sea, but you have land over the big Borneo island. So you end up with the strong shear vorticity, strong winds over the sea and no winds over the land. So naturally, you have a reason for shear vorticity and you have a high temperature, high moisture. So you're likely to sustain vortices. They're weak, they're not strong wind, but there's a reason for that. And you can look through various seasons, and none of which has such concentration, even including summertime. Say over, I had one chart. I'll just go to the next one. So this is Typhoon Vamay. That's observed in similar area, very close to the equator. The center is next to Singapore. That's about 1.5 degrees. And this one is the result of strong cold surges in our 2003 paper that shows that a week before, almost a week, I think there's 7 days on here, vorticity is the lower panel. We can see the cold surge northeast winds enhances the vorticity, and eventually the vortex wrap up, vorticity increases, and Typhoon Vamay was born. And usually there's observation, and there's some people come up with theory to explain the observation or modeling, but this is the rare example, a very exceptional case where Dr. Ha Klin of National University of Singapore had a theory on something like that 20 years before Typhoon Vamay. That was 1981, paper published in JIS. Here he used just a linearized shallow water beta plan equation. It cannot be any simpler. There's no mean flow. And he assumed that in the north, at about 30 degrees north, like the Siberian high forces a cold surge, so the pressure would rise at 30 degrees north at various time scales. That's and see what's the tropical response. And the tropical response in this case can be shown in this sequence of weather maps, where we see that the high pressure rises. Oh, by the way, this is entirely analytical. This is not a numerical simulation. This is entire mathematical. Okay, just simple equatorial wave solutions. The Rossby wave, the mixed wave, and the Kelvin wave, and so forth, with different meridional modes. So by day 4, day 6, and day 9, we see this pressure develop with a northeast-southwest tilt. And there are like Kelvin waves, mixed waves, and so forth. And what the main pattern here are the equatorial Rossby waves. And there's no terrain, the North-South China Sea, Borneo, or any island, and so forth. Just pure shallow water model, no mean flow. So how does this tilt develop? This is kind of realistic. It developed because of the Rossby waves. Remember Rossby waves move faster if the wavelength is longer. Here, long waves are those of lower ends, the equatorial mode. So n equals to 1 is the longest wave. And n equal to 1 would have its maximal amplitude closest to the equator. And then you have n equal to 2, n equal to 3, also symmetric, asymmetric modes. Their maximum amplitudes are further away from the equator. Since n equal to 1 is the longest wave, the meridional mode, but it's actually the longest wave, it moves faster towards west. So amplitude closer to the equator moves faster to the west. Amplitude away from the equator move to the west slower. So you're going to develop this northeast-southwest tilt. There's no other effect. No, it's just pure dispersive relationship of equatorial Ross waves. And the whole pattern, the dynamics here is simply geostrophic adjustment. You're forcing a pressure at the northern boundaries, and this is what you got. If we take, I think, day 3 and day 6 and put it together, and they will look like this. Now we can see closer that there's cross-equatorial flow from this Rossby wave group. And day 3 and day 6, there's return flow, and you got a vorticity, you have a cyclonic vorticity there. This dynamics is separate and different from the Borneo vortex we just mentioned earlier. That one's because of shear vorticity due to land-ocean difference and wind difference, and helped by moisture and high temperature. But this is pure barotropic dynamics, adiabatic. And if we compare this chart with what actually happened before Typhoon Vamei, they look kind of similar, pretty realistic. I cheated a little bit because the theoretical, the linear wave theory, here the scale here is actually twice as large as the scale here. But remember, there's no terrain. And if you put this linear wave into a realistic topographic distribution, you can see that this feature is going to be constrained by the land's distribution. So in a more realistic model, one would see that the scale of this could be less than what is here. So here we are presenting, or actually Dr. Lim, 20 years before the observation, presented a theory, a mechanism of geostrophic adjustment, so that pressure forcing at 30 north could produce something like the tropical cyclone genesis near the equator. And this, of course, would be helped by the shear vorticity due to the land-ocean distribution and by all the C to E energy. Now, why do I say it's rare? Actually, in the paper we published, I said this can occur like maybe once every 100 years, or even more rare. If you look at the lower level wind. This I think is 925, 25-year average seasonal winds, DJF, MAM, JGA, and SOM. Only in the South China Sea you have the conditions that can produce this kind of cyclone genesis. One could say in the summer you have a reverse winds that might be here, but there's no Siberia over Australia. Okay, it's a much huge Siberian high produced the northern winter surge. There's no counterpart in the southern hemisphere. One can, if one just focus on the same area between the two seasons, and here we take the average of the 50 days with the maximum winds. Namely, we got what 25-year worth of 90-day each season, so we have more than 25 times 100. It's close to 2,500 days, maybe 2,300 days, and take the 50 days with the maximum wind at each grid point and average them, then we see that the occurrence of cold surges, that means the northeast winds freshen up. They're kind of, this is highly variable. There are days there when they're really high, that's a cold surge that could force the dynamical vorticity genesis here, but you don't have the counterpart in the southern hemisphere. And now let's just take a look of all the so-called near equatorial TCs that ever observed. The data sources from JMA from Japan. And here we color each track with a code such that if you see green color, then that means you develop into what JMA call a tropical storm. Prior to that, you just have TD or just disturbance. Throughout all those cases, only one, that is, okay, here is the Western Pacific, here is the Indian Ocean. Only one, that is Typhoon Vamay, that you can see the green color, this tropical storm or strength between 3 north and 3 south. Those red lines are 3 degrees south and north. None of the other so-called equatorial TCs became a tropical storm intensity within 3 degrees. In fact, most of them are 5 degrees. So this remains to be the only one. And now why it happened in South China Sea and why it don't happen once? Earlier I said you have a condition, your environmental condition is favorable for shear vorticity and with the high theta E, so you favors tropical cyclone development. And further now we have the barotropic dynamics due to the strong wind. See, to have the barotropic dynamics to cause cyclone genesis, you need to have very strong pressure forcing from the north, geostrophic adjustment and so forth. You have this northeast wind. But imagine that if you do have a cyclone that or vorticity develop somewhere here that's somewhat strong, but if you also need strong northeast wind. So if you put one here, the northeast wind is going through the center of the cyclone. Obviously, that's impossible. So what's going to happen is you have strong winds over here. You're going to push your vorticity center toward the land, right? It has to be on the area between the strong winds and the very weak winds. So strong winds, which would help the cyclone development, strong winds but the terrain would hurt. The topography plays 2 roles here. One reason for the strong downstream northeast monsoon surges is because of the terrain, the narrowing South China Sea towards equator. That enhances low-level wind. But the terrain always kills the storm if it wants to develop. So this is why you have 2 conditions that counteract each other. So it would be very difficult to actually have a TC develop, even in spite of the equatorial dynamics I reviewed earlier and all the shear vorticity and moisture. We did some kind of finger counting arguments, arguing that you could say about maybe once every, in fact, I was saying once every 400 years. Then I got scared. I said, oh, that's too aggressive. I'll just say, I adjust the parameters, say maybe once every 100 years. I remember when the paper was under review, John McBride wrote on the Monsoon email discussion saying, oh, we just saw some Borneo vortex that's very similar to Typhoon Vamay before it developed. So we expect to see Typhoon Vamay, some sort of typhoon TC from this system. That's when I just got the reviewer's comment. I was going to revise the paper, and I was saying once every 100 years, and he was saying it's going to happen next week. That made me kind of nervous, but I decided to submit paper just as it is. And of course, there was no TC the following week. Okay, I'm almost near the end. After our report, and I'm aware of at least 7 research teams that reported simulation of the Typhoon Vamay development using regional models. In fact, and this has been going on the last 20 years. Everyone was successful. Some say the critical element was the large-scale flow, was the latent heat, was the boundary layer. One paper say it can't be at 0. It has to need some Coriolis parameter, maybe 2 degrees. But this successful numerical modeling, do they explain the development of Typhoon Vamay? I claim no. They are successful, but none of them actually answer the question. Because I think, there are monsoon cold surges almost every winter, and there are many winters that have strong surges as once or twice a month. I bet if these 7 research teams use their regional model to simulate, to use the initial condition of the other strong surges, they are also going to create tropical cyclones if they don't tune their model, if they just use the same parameters that give them Typhoon Vamay. So my point is that the question is not how Typhoon Vamay develop. The question is why only once throughout all these decades. So that question hasn't been answered. That's all. Thank you.
Thank you very much, CP.
Okay.
Do we have any questions in the room or online? I don't see any questions in the room. Oh, there is one. Callie.
Hey, CP. I really like that last comment. I guess one remark might be, I mean, we run regional NWP over that region every day, and we hardly ever see TCs or tropical depressions like Vami forming in those forecasts. So yeah, so I don't know how to square that with your comment that the modeling studies may have may preferentially be producing TCs in that region. Yeah, it would be a rare event in our NWP for sure. And obviously we're doing forecasting of the cold surges routinely.
Okay, that's a comment as well.
You can come back if you want.
Yeah, okay. Yeah, well, I mean, I understand that. Yeah, I don't have anything to add. It remains a mystery to me. It could be just by chance. Thank you very much.
Thank you, CP Chen. Thanks for joining us online.
Yeah, I'm probably going to quit. It's pretty late here in California.
Yes. Sorry to keep you up.
No, that's fine. Thank you. I'm so glad to see the meetings going well. Thank you.
Okay, thank you.
Bye.
So our next speaker is UC Mohanty. So would you like to come up? And can we get the presentation up?
Thank you, Chairman, and very good morning to all of you. So at the outset, I express my thanks to Dr. Krishnan and Dr. Rajgopal for inviting me to give this talk here and providing also all the facilities, including the financial support. So this work which I'm presenting, it is a work which started in India. It conceived in this hall with Dev, Yogi, myself, and Akhera from CDAC to do some work on urban meteorology in a very constructive way. And at the same time, we have a national supercomputing mission program initiated, under which the Ministry of Electronics and Information Technology, they wanted to install 70 supercomputers in leading national institutions to do work on various problems, and we picked up the metrology. So therefore, you can see that we have a very good list of collaborators with me, and they are mainly from CDAC, Center for Development of Advanced Computing, that is in Pune, next door to IITM. And then we have the IIT Bhubaneswar, that is new institution, established in 2009, and Indian Institute of Science, Bangalore, and our 150 volts India Meteorological Department, because that is a department, because we want to do something which can go directly to society. So that was our purpose. So here, that's why we have studied urban scale weather modeling system for prediction of monsoon. Of course, we focus 3 areas. One is the extreme heavy rainfall events, that other is the heat waves. So here we will focus mainly on the monsoonal heavy rainfall. So at the outset, I acknowledge definitely the Ministry of Electronics and Information Technology, who provide the financial support for this project. And then CDAC, IIT Bhubaneswar, IIC Bangalore, IMD, and my present organization, SOA University, where I am currently working. We got a lot of support from NCAR, NCEP, USGS, ISRO, NCMWF, and IMD for providing various data and the model that we are using. We use the supercomputing facility of IIT BHU, that is in Banaras, IIT Kharagpur, and IIT Hyderabad. So the overview of my talk, I'll give a brief introduction. Then I'll talk about the customization of the urban developed model. Then I'll show you some continuous semi-operational, semi-real-time simulation of heavy rainfall events, and then performance of the model versus the GFS, which is the operational in our IMD, and conclusion and future scope. So of course, we have already now a lot of talks on climate change, climate issues, and with the climate change or global warming, its impact on monsoon. It is very well known to all of us now. But actually, all we major focus is on greenhouse gases and aerosol, which give elevated heat source. But that gives a global climate change. But we have so much microclimate change that you are facing even in Pune. When I first came in Pune in 73 or so, it was really a air-conditioned city like Bangalore. There is no fan. And today, or this period, you must have seen what is the problem. So it is a well known that though global warming at the top at 1.54 or so is the rise of temperature from pre-industrial era, but city area, particularly the cities with lot of urban area, you know, temperature rises even much more, maybe 3 to 4 or 5 degrees. And now we know that about 55% of our population, they are living in the cities. And the projection is that by 2050, that may be 68%. That means 1/3 of the population, they will come to cities. So if you want to see the impact of the global warming and monsoon, obviously we cannot ignore, or we should not take it lightly, the impact of the monsoonal rain, because monsoon means actually wind is there and rain. These are two factors that determine the monsoon of the India, because we tell with the, as Dr. Krishnan show you, that it starts with the Somali jet, low level jet, but then all India, they look only for the sky, whether when they are getting rain, how much they are getting rain. And you know that Dr. Mohapatra in the inauguration also he told that 70 to 90% the annual rain that is coming from monsoon. That obviously, that is the most important aspect as Indian monsoon or Asian summer monsoon or Southwest monsoon. And you must be seeing the media and so on. Recent days, many cities which are very unusually known for a heavy rainfall, they are getting the vagaries of the monsoonal heavy rainfalls like Patna or Hyderabad, the city like Baroda, and also Bangalore, which is a very well-known city as a city of the Silicon Valley of India. And you must have seen in the media how they are using the tractor to move from one place to their office because of the heavy rainfall. But then this rain, though it is a city, but it is not all part, because it is mainly the convective system embedded with the stratocumulus things and give the precipitation even one part of the city heavily, not other part of the city is expanded. And this is a picture that is what I am showing. It is very much actually publicized in media that people in Silicon Valley, they are moving the tractor or this thing from their office to their home to office. In 2024 alone, it is again report from the news that 3,238 lives were affected, perished due to the heavy rainfalls in cities. 3.2 million hectares of cropland are destroyed, and not many houses are also destroyed, and so on, livestock. So all these things definitely urge us to do something for the cities. We have some work, and this is also now very much well known, that the number of heavy rainy days is increasing. Number of long rain spells have decreased. We don't have a spell of stratocumulus rain for several days. That is almost decreased. Similar number of moderate to rain days are decreased, but whereas number of short, heavy rainfall events are increasing. This also we have done region-wise. It shows also same way. So I'll not spend time. It is all published in JGR. Similarly, we have done a special distribution of temporal trends of the rainfall from 1991-2020, and this shows the trends, and it was divided as classification of IMD, light, moderate, heavy, and extremely heavy rainfalls. So the black one shows that where it is in decreasing trend, where it is increasing trend. So that is also, it is not uniform. And we have also seen that the decreasing rain of a long time leading to drought also, there is a shift from the western side to the eastern side in a anti-clockwise manner. This was famous work by BNG Goswami and his team that also emphasized the same thing, of course, over the only core region of the monsoon, which shows again same thing, that the moderate to light rains are decreasing the number of days, but whereas heavy to very heavy rainfalls are increasing. So this not only Indian context, even if you go to state where I belong, that Odisha. The Odisha also we have carried out some work with my research scholars and others. There also we have seen the same thing. You can see heavy to extremes increasing, light to moderate is decreasing, dry days are increasing, and wet days also decreasing, but with the scale of heavy rainfall days. So this urban modeling, which we started, as I told, we planned in 2017. It is executed by September 2019. Then unfortunately, Corona came 2020 and things were slowed down. Then it picked up. So I will show you some of the results. And computing was the major thing for us because we want very high resolution sub-kilometer scale model for the cities. And then it needs also micro scale modeling systems like data assimilation and ensemble systems and so on. And we need a lot of data, which is, as you know, that though we have, India is very famous for long time of data records of rainfall and so on, but to have a large number of observations to capture the mesoscale things, even to verify the model, is difficult because it is not available. But fortunately, in some cities, we have very good number of observations, and that I will show you. And ultimately, to translate our results to the public, it will be only by the administrators. And they don't know what is the model, what is the data, and so on. They want decision support. So that is one of the beauty of this program, which we have done. So CDAC took that responsibility to translate our forecasts to a decision support system so that it can be, just by click the button, the administrators, they can know which part of the city, how much water will be there, and whether they have to evacuate the people or it is safe for the people and so on. So I am showing you this picture which shows how urbanization has expanded. So this is the city Bhubaneswar. It is the capital of the state of Odisha. And Odisha is in the east coast of India. And this data is from USGS and taking the Landsat data and so on. So you can see that, which one? That's the pointer. So if you can see that 1980, 1990, 2000, 2010, and 2019. So you can see that the city area has grown almost by more than 10-fold in this period. The population, the city Bhubaneswar was developed only for the 20,000 people. Just a capital city for the administration and so on. And now the population is closing to 15 lakh. So that is what is growing, the both population and urbanization. So this is one example, actually. Similar the example Hyderabad versus Bhubaneswar, which is that Hyderabad also expanded by almost 13 times in the period of 1993 to 2019. So this is how it is so that it is how the city became another heat source, that is the bottom, that is the heat balance at the surface, is also another important aspect, which gives not only the heat waves or warming, it also trigger the dry convection and leading to moist convection and so on, and ultimately leading to large number of heavy rainfall events. So we took actually, in this study, we have taken, start with the 3 cities. There is a reason for that. One is the Bhubaneswar, east coast. One is the Pune, this city. Third was the Bangalore, that is in the south. And we have a program in India, Smart City program, where actually we identify the best cities. And Bhubaneswar was the number 1, Pune is the number 2. Bangalore has its own significance. So these 3 cities we started with, we thought that this experience can be translated to other cities. And this is the configuration of the model, that is WF model. So we have taken 3 domains. Outer domain is 4.5 kilometers, that is covering a large monsoon region, then 4.5 kilometers, and then 0.5 kilometer, that is city area, which we have taken actually 100 by 100 kilometers the domain. Rest of the thing I don't want to take time because we are familiar that when the physical processes, they play microphysics and so on, they play a very important role, including the boundary layer, convection, cloud microphysics, and so on. So this is the performance evaluation. We have done actually a large number of experiments with this high resolution model to decide a set of models which can be do the better. And in that regard, actually, we came down to 4 combinations. Of course, that is based on the land surface, microphysics, cumulus convection, and that is what is given in this table. And we have taken various combinations, and we have done almost 500 experiments and boiled down to these 4 combinations. And we wanted let it be a multi-model. The model physics is the main thing. So once that is changed, the performance will change. So that on the end, we can go perhaps a mean of that or a ensemble of that things. So in that, actually, we decided the 4 models. Then we wanted to see the impact of land use, land cover, or urban things on that of the urban WRF, that we are telling UWRF. So what we have taken? We have taken a case of November 20th July 2018. All conditions are same, but we have taken land use, land cover of all these 1980 to 2000 and 2019. 3 different years land use, land cover, which is a forcing factor. And rest of the atmospheric parameters, they are the atmospheric parameters, large scale flow and so on, because the boundary conditions and initial condition in this we have derived from the operational GFS of IMD. Then we have used this very famous formula, surface precipitation feedback mechanism. And here actually P is the control run, and P prime is the urban experiments. And then you can see that the blue one, which show that the urban impact, that is almost more than 40%. For this localized range, not that global. Oh, sorry. So I'm moving slow. So then actually we have taken these 3 cities, and we have taken around the model continuously for all 122 days. You can see that Bangalore has more than 100 rain gauges in the city, which is very good. Whereas Bhubaneswar have 2 regular observations by IMD. One is their airport and another one in the agriculture university. And Bangalore and Pune, and these are the number of events, 6, 8, and 8. And then you can see that the performance of 1.5 kilometers versus that of the 0.5. So it shows that that significant improvement in success rate of the forecast with higher resolution than that of the 1.5. Then we calculate also what is the false alarm, where the model is overestimating actually. Because high resolution model have one drawback, it is overestimate sometimes. And this model also have a little overestimation. So whether it gives a lot of false alarm, then it has not much meaningful. So that's why all 122 days, we calculate the accuracy of the model, success of the model in simulating the cases, and also false alarm. So you can see that success rate is more than 63% average of the all three cities, and the false alarm is less than 20%. So this signifies the model is not so bad, it is giving a good performance. Then we have seen the performance of our GFS as a WF model versus the operational GFS. And then we have taken the city, Bhubaneswar. As I told, we have 2 stations in the city maintained by IMD with all quality control. But we have so many by the smart city authorities, then local bodies and so on. So we have total 15 stations. And we found that if we go only 2 stations, we have only 6 extreme events that is captured in that 2 stations. But the whole city, which is expanded to a large one, there are 23 heavy rainfall events. And this is what is the performance of the model. The brick color, that is what is the performance or success rate of the UWRF versus the IMD GFS, which is in the blue line. So this all shows that the performance is quite significantly higher in urban model compared to that of the operational GFS at 12 kilometers. Then we have taken event by event. There are 23 events. Then here we are giving the observed is the red color one, the WR is the blue color one, and the black one is the IMD GFS. The star one is the success, the circle one is the failure. So you can see that with the urban WRF, the success rate is quite high. In fact, number of success of all these 3 cities, if we take Bhubaneswar 23, Bangalore 8, and Pune 6, then we have 26 as a success, 13 cases we have failed, total were 39, success rate is 67%, and failure is 33. Whereas the GFS with 6 success and 15% success rate, and the fail almost in 85%. Right. So then actually we see also, I show you actually because some heat waves are there now because monsoon onset date is now shifting. Many times we get monsoon onset delayed onset, and June some parts also we get heat waves. So if you see urban heat stress is one of the very important aspects. So here also you can see that this is we have taken for the city of Bhubaneswar, and we saw that it has a very good success in prediction of the heat wave. And also we saw the impact of LULC and by UDAF, and there actually you see that some heat wave in 4th June, 18th June, like that dates, which are really monsoon time. So this is the success rate again given, and we use USGS versus ISRO Landsat, and we saw that ISRO Landsat give us a better results compared to that of the USGS land surface things. As I told you, ultimately, this is my last slide perhaps. So coupled urban modeling system with a decision support system, because again, this decision support system was developed exclusively our partner, CDAC, and our colleagues are here from CDAC because as I told you, it's next door. If you have any question on that, and they are the best person to answer. And then actually, so this shows that in the meteorological, the science part, the HPC systems that we use from various academic institutions under national supercomputing missions, data sources from different sources, And ultimately, after decision support system, how it is going to the public through the local administrators, like mainly the municipality authority and so on. They for different blocks they have, and they are telling which block, how much water will be there, and so that they can take appropriate action. So here is
Okay, I think we need to finish,
Yeah.
really, because we.
Okay, so I will leave this one. This is actually an integrated platform for this model. So I come straight to my summary. Understanding and prediction of heavy rainfall events during summer monsoon are very important in context of rapidly growing urbanization and populations over Indian cities. More than 500 sensitive experiments that we have carried out to come to that 4 combinations which we have used. Then we have seen that in overall, if we have 30% is the failure rates, 65% the success rate, and false alarm is quite small. The urban development day 1, day 2 forecast up to day 3 forecast are quite good. Obviously, day 1 is much better, and as we go on, it decreases. Higher the resolution, it has a good impact. The statistical prediction skill of 0.5 significantly improve over the 1.5. Then the model remains stable and provides a reliable indication as the false alarm is below 20%. Still, there's a lot of things to be done in this model. First is that to use the assimilation in the model itself. Always I believe that since I work with NCMWF, we made the operational. I always emphasize we cannot take other models, initialization condition, and run a model. It should be self-generated. Fortunately, we have a lot of data is now available, and the IMD or Minister of Earth Science have a program of this mission Monsoon, and where actually 120 radars are coming in the country, and also number of operations are increasing. So first task is there to make a mesoscale data assimilation at least 1.5 kilometer resolution, so that will be input to the model. Second thing that you do a better as the Globus, as they always plead that Globus is better than URAP. So to include that in simulation, so to better representation of the urbanization factors. And now it is that AI train the model with ML and use the AI for a decision making for these complex problems. So that is also equally important. And that is what we are planning in the phase 2 of our program, to use the AI so that actually we can further improve the urban scale heavy rainfalls. So thank you very much. And my paper is open for the questions as well as suggestions, mainly for the youngsters who are going to work.
Okay, thank you very much.
Thank you.
Okay, one very quick question because we're already behind time. So.
Thank you, Professor Mohanty, for this talk. Could you just let me know what are your plans for the next 5 years to test your network or your performance or other regions? Because urbanization is not confined to just some cities. It's also a big problem in hilly regions.
It's a quick question, but it may not be a quick answer.
Yeah,
just a quick answer.
Yeah, actually, in fact, with now they are going to increase. Actually, they have now 6 supercomputers in 6 academic institutions, and they are going to have 70. And soon, perhaps, they are going to start that. Once that is there, we are thinking to capture about 300 cities in the, and not only prediction, but going to decision support systems, emphasizing first the 2 factors, heavy rainfalls and thermal impact, that is heat waves and thermal stress.
Okay, we wish you luck with
much.
this ambitious program. So thank you very much again. And we better move swiftly on to the next talk, which is to Endu from Scuba. Hi. So I give you a bell with 2 minutes to go.
Thank you, Chair. So good morning, everyone. My name is Hirokazu Endo from MRI in Japan. Today's my talk title is here. So the Western North Pacific and East Asian region is the most active area for tropical cyclones. So tropical cyclones significantly contribute to extreme precipitation in this region. So observational data shows a tropical cyclone largely contribute to annual maximum daily precipitation and the frequency of heavy precipitation, especially in coastal area in this region. So suggesting that the use of high-resolution model capable of reproducing tropical cyclone is preferable for future projections of extreme precipitation in this region. So our institute have conducted future global warming simulation with high-resolution MRI AGCM to study future changes in extreme phenomena and regional climate. So in our experiment, observed sea surface temperature is prescribed for the past simulation, while for future simulation, SST is made by adding SST anomalies projected by CMIP models to observed SST. So this EMIP type simulation help us avoid the effect of SST bias in coupled model. So allowing us accurately representing regional climate. And the use of different SST anomalies enable us reflect the variety of CMIP projections. So purpose of this study is using 20-kilometer MRI AGCM. We investigate future changes in extreme precipitation in the Western North Pacific East Asian region, focusing on the impact of tropical cyclones. And we discussed the dependency of future projections on model resolution. So we have conducted present day simulations with 5 members and future simulations with 2 different scenarios and 4 different SST anomalies, which is obtained by cluster analysis based on CMIP5 multi-models. First, I'll show you present day simulation. So we investigated annual maximum of one-day precipitation, RX1D, as an indicator of extreme precipitation. We also defined RX1D NTC, which is RX1D excluding tropical cyclone associated precipitation. So in observation, RX1D is large around the Philippines, 20 degrees north, and the over-oceanic area in East Asia. And the difference between RX1D and RX1D NTC represent the effect of tropical cyclone. So suggesting that the tropical cyclone influence RX1D over areas south of 35 degrees north, particularly near the 20 degrees north, where the difference between 2 indices is very large. Although there are significant uncertainty on the magnitude of RX1D among the dataset. Looking at the MRI AGCM, the observed characteristics are well reproduced, although RX1D is overestimated over the ocean south of Japan. So next, I'll show you future changes of the climatological mean RX1D and the RX1D NTC. So RX1D shows an overall increase in this region with higher rate of increase at higher latitude due to greater warming in the high latitude. Another feature is RX1D remain unchanged or slight decrease in the subtropics under the high emission scenario. So interestingly, we exclude the effect of tropical cyclones. There is an increase over almost areas, and the rate is close to the Clausius-Clapeyron rate, 7% per Kelvin. So suggesting that effect of tropical cyclones contribute negatively to changes in the mean Rx1D. So looking at the tropical cyclone frequency in the future, tropical cyclone frequency is projected to decrease in the Western North Pacific, which act to reduce the mean Rx1D. So here we compare the result of between high resolution model and low resolution model, which include the low resolution version of our AGCM and CMIP5 multi-models. So in the present day simulations, low resolution model underestimates the magnitude of Rx1D, and it failed to reproduce its peak around 20 degrees north, which is created by the tropical cyclone activities. And in the future change, a low resolution model project positive change everywhere, showing marked difference in the subtropics compared to the high resolution model, where slight decrease is projected. So suggesting that low resolution model underestimate the effect of tropical cyclone activity on the present day Rx1D, which is probably due to a weaker intensity of tropical cyclone in lower resolution model. And this limitation may result in inaccurate future projection of Rx1D. So this figure plot the future changes as a function of the amount of warming on the horizontal axis at a different latitude. The high resolution AGCM simulation shows a slight decrease in the subtropics and the high emission scenario, shown in red plot. However, when the influence of tropical cyclone is excluded, the increase approaches about to the Clausius-Clapeyron rate, 7% per Kelvin. So, and the right panel shows compare low resolution version and high resolution version. So low resolution version shows much higher rate in the subtropics compared to the high resolution version. We also plot CMIP5 multi-model results in left panels, showing considerable variability among the model, especially in subtropics. However, on the average, they follow the Clausius-Clapeyron rate. So these results suggesting that the mean Rx1D generally increases due to the thermodynamic effect, but it is negatively influenced by the modulation of tropical cyclone activity, so which is better represented by high-resolution model. So in the last part, we briefly introduce our new simulation system. Current, our simulation is based on AGCM, which doesn't include air-sea coupling processes. So this approach has faced some criticism, as air-sea coupling process is very important in the Western North Pacific. So for example, our AGCM simulation tend to simulate intense tropical cyclone anomalously far poleward in the Western North Pacific. So to address this issue, we have developed a new system called TSEC, which is based on coupled model, MRI ESM2, and it assimilates observed ocean data with a relaxation time of about 10 days to ensure realistic representation of regional climate. So we confirmed that TSEC can simulate SST cooling after tropical cyclone passage due to a short time scale air-sea coupling, leading to a reduction in intense tropical cyclones at higher latitude compared to AGCM. So we also share, we'd like to share that our new system improves sea surface, the relationship between SST and precipitation. It is well known that in observation that SST variation precede about 10 days precipitation due to air-sea coupling, air-sea interaction processes. This time lag cannot be simulated by AGCM. However, TSEC can realistically simulate this time lag, similar to how free coupled model does. So on internal variability, a local SST and precipitation correlation in JJA mean from observation shows a exceptional negative correlation over the Western North Pacific. This negative correlation cannot be simulated by AGCM. However, our new system, TSEC, can reproduce this negative correlation over the Western North Pacific. So this suggests that our new system improves many aspects of simulations. In the last, I show you tentative result of our new system based on 60-kilometer version of the TSEC. So TSEC can simulate RX1D distribution similar to observation, including its peak around the 20° north, which is associated with tropical cyclone activities. In the future simulations, RX1D remains unchanged or slightly decreases in the subtropics, which is influenced by a decrease of tropical cyclone frequency. So this result is consistent with the result of 20-kilometer mesh AGCM simulations. So, however, this feature cannot be simulated by CMIP6 multimodal mean, suggesting that the low-resolution model may have some systematic bias in their future simulation in extreme precipitation. So to summarize, according to our AGCM simulations, in the Western North Pacific East Asian region, at higher latitude, a greater rate of increase is projected for the mean RX1D. This feature is explained by two factors. First is greater warming at high latitude. The second is decrease in tropical cyclone frequency in the subtropics. We have showed that the future changes in the mean RX1D in the subtropics are influenced by the positive effect of increased moisture and the negative effect of decreased tropical cyclone frequency. So our results suggest that low-resolution model may have some systematic bias in their future projections of extreme precipitation due to underestimating the effect of tropical cyclone activity. So our analysis is based on a single model. So multi-model analysis is necessary for future study. That's all. Thank you.
Thank you very much. Do we have any questions in the audience? Yes, at the back.
Does your high frequency model, high resolution model show anything about the boundary current? That's why it is doing something regarding the decrease in tropical cyclone frequency in the subtropics?
Yeah, I couldn't catch your question. Could you say again?
The boundary current in your high resolution model and low resolution model, is it different? And that's why it is changing the frequency of your tropical cyclone in subtropics?
Yeah, this result AGCM. This result are based on AGCM simulation. So we use same CSAS temperature. So the difference is only the resolution of atmospheric model. Yeah. So I think low resolution model cannot simulate strong tropical cyclone intensity. So that's why it can fail to reproduce the peak of this extreme precipitation.
Like the mesoscale eddies in
Yeah, yeah.
your
Yeah.
model.
Yeah,
the
yeah.
Do
low
you mean
resol-
in the ocean or in the atmosphere?
Ocean, but if he is giving very high resolution SST, that may be giving a mesoscale
Okay.
feedback in the atmosphere, but in a high resolution, but not in a low resolution.
Yeah. Model, ocean resolution difference.
But do you use high resolution SST forcing data or?
This simulation, we use 1 degree
Yeah.
resolution.
Yeah.
So we don't.
So
we
they don't
didn't,
have a high resolution
yeah.
SST
Oh,
boundary condition.
Yeah, SST high resolution is important, of course. Yeah.
Of course, this will all come when you put the couple model together. So that's good. Okay, thank you very much. I think we better move on. So our next speaker is Ananya Kamaka. Oh, she's here.
Good morning, everyone. Myself, Ananya Karmakar from India Meteorological Department. Today, I'll be speaking in the topic, the distinct response of Indian land rainfall and its teleconnection to the Northern Pacific climate variability. So this will be the outline of my presentation, starting with the introduction, then data methodology, and slowly I will introduce to the topic and result discussion and the conclusion. So we all know that in recent period, the climate change and the global warming is a burning topic in the worldwide, and many studies has shows that climate change in India it's significantly impacting India, which leading to the increased extreme weather events, rising sea levels, and this can be threats to the agricultural sector, our water sources, and ecosystems. So basic main aim of this study is to analyze the climate change in India with respect to the climate classification and to investigate the underlying factors driving these changes. Now, starting with the climate classes, this is the present day map of the Köppen-Geiger climate classification map taken from this Beck et al. 2018. And these are the all climate classes all over the world. Here we can see the India is definitely showing this climate classes, but though it is not very distinct and very much prominent all over our this homogeneous Indian regions or this meteorological subdivisions, and how this climate classes changes over this recent periods or recent due to this recent climate changes scenario. So in this study, I have used the data sets of IMD gridded rainfall data sets, which is the 0.25 degree resolution, and the maximum and minimum temperatures of 1 by 1 degree data sets. And SST, we have used the scope 2 SST for this particular for this study. This is a methodology we have taken from the P. Little 2007. This is the climate classifications, what we have taken from the P. Little 2007, and these are the formulas or the criteria of this climate classes. And India mostly spans this major climate zones. This is this arid, tropical, temperate, and the colder zone, colder mountain zone. And these are the basic criteria of this here, which is taken basically the mean annual temperature and the mean annual precipitation. This is the typical map of the climate classes of the of Indian region. And our in this study we have taken from 1951 to 2020 period data sets, and this period we have like bifurcated in 5 climatological epochs, which is like a sliding or moving towards the per decade. So we got the 5 epochs. This is the epoch 1, which is 1951 to 1980, epoch 2, 61 to 90, epoch 3 is the 71 to 2000, epoch 4, 81 to 2010, and this is the our recent epoch, epoch 5, 1991 to 2020. And these are the each epoch's climate classifications of Indian subdivision, meteorological subdivision, or the Indian homogeneous region. Here it is seen that this the first decade from the first epoch to the last epoch, this northern India, this arid zone has been moved towards the temperate zone. It means that northern India, it is moving towards the drier climate to the recent period. Whereas in our southern peninsular India, if we see this orange part, it is reducing from the first figure to the last figure. So this this in the southern India, it is the slowly shifting towards the wetter climate class or the wetter zone. So to better understand this changes over the particular region or zones over India, this is the actually area or the climate zones in percentage area over the all over the India, and the 4 homogeneous regions. This is the northwest, central India, northeast, and the peninsular India. We basically found that this northern India and the peninsular India, these 2 homogeneous regions are showing this the main changes, which is this northwest India showing this increasing of the climate class of the arid climate class, and decreasing of the this temperate climate class. And the peninsular India, this is showing the increase of this savanna region and the decrease of this arid region. And this increasing of the arid region in the northwest India, it is almost 7% of the area of this of that particular region, which is really alarming in the recent climate change scenario. Now, to understand the particular role of the temperature and rainfall in this changes, this is the difference of the maximum and minimum temperature for each climatological epoch from its previous epoch. So here also it is very much evident in the recent period. This northern India, here it is warmer also, and even it is getting drier also. Whereas the southern India, it is getting wetter, and temperature is already warmer only. Now, these are these changes is basically happening over the decadal period, and to link this changes, how it is interconnected with the or the teleconnected with the air-sea interaction in with this Indo-Pacific region, or to see that we particularly focused on the decadal variability over the Pacific, as we know this decadal variability over Pacific can modulate the this rainfall over the Indian regions also. And here we found that this particular northern India subdivisions, this West Uttar Pradesh, East Uttar Pradesh, Bihar, Jharkhand, and Gangetic West Bengal, these 5 subdivisions rainfall, when we and take that these rainfalls are very much decreasing, and over the this northern Pacific, this particular belt SST anomaly is particularly increasing, which is like oppositely correlated. And this is the particular regression figure of the this 5 climate 5 subdivisions rainfall over the SST anomaly, and we got that a typical nature of the decadal variability of the second mode of the decadal variability of the Pacific, northern Pacific. This is which is called the Victoria mode of the variability. And this is the when we see the second mode, how this is this is how this variation of the second mode of this North Pacific variability, this is the EOF analysis of the second mode of the Pacific Ocean, North Pacific. And this is the particular of the Victoria mode which we are seeing, and this is the SST, this is the PC2 of this particular of this mode. And this mode is almost 12%, 12% of this variance in that. Now, connecting with the PC2, we have regressed the moisture transport over the Indian region, and we found that this particular northern belt of this this northern India, this moisture transport is it is decreasing, and it is weaker, and we are getting this weaker type of dipole type of nature over this northern India and the southern India, particularly for with this when we are seeing the regression with this this Victoria mode. And these green contour lines are the streamlines, regressed streamline analysis with this same PC2, and which is showing an anomalous anticyclonic pattern over the Gangetic, this Gangetic West Bengal plains. And this can show that this this Victoria mode, or the decadal variability of the Pacific, could modulate this rainfall, or the suppressed of rainfall of this particular region. Now, coming to the conclusion, the area of the Indian homogeneous region, this depicts a drier climate zone shift in the Northwest Pacific and Northeast India, from the temperate to the arid zone, and and tropical savanna to the temperate climate respectively. And this change over the North India, it's nearly 7% with this of the total area of India, due to an increasing trend of temperature and decreasing trend of rainfall, and which is the controlled by the negative phase of Victoria mode. And this decreased the transport, moisture transport, and the divergence over the northern Indo-Gangetic plain. So overall, this shift could adversely impact the northern India agroclimatic zone in future, which is really alarming, this climate shift happening in this way. So this is all. Thank you.
Thank you very much. We have two questions here at the back. So first of all, in the middle of the
Nice presentation. I just wanted to ask that regarding that increase of arid region in that Northwest India you showed. In recent papers, I have observed that there is an increasing dipole pattern that in Northwest India it is receiving more rainfall. So why so? Like I couldn't get that. It was such contrasting in that part.
Northwest India receiving more rainfall.
Yeah, because in dipole pattern, there shows a shift that Northwest India getting more rainfall and Northeast India getting lesser rainfall. But you showed that there is an increase in aridity and all that in that Northwest part of India.
Yeah, this Northwest part of India, here this is the shift is going on. This is not exactly the Northwest, what you are saying, the study, that is not exactly the Northwest. If you are saying this Rajasthan and this region, this might increase the rain or something, but particular for this Gangetic plain or the northern Gangetic plain, what we call, here it is decreased rainfall. So there is a dipole pattern of this decreased rainfall and here increased rainfall. So this dipole pattern I am talking about.
Okay, thank you.
Okay, very quickly.
Thank you, ma'am, for the nice talk. So my question is the influence of Victoria mode is stronger than ENSO in this context, or do they interact?
No, they two are very different. Actually, ENSO is a interannual variability. So, and this Victoria mode is the decadal variability of the Pacific, Northern Pacific. So these two time scales or interacting of these two time scales are very much different with the Indian monsoon. Here, what I wanted to show the long-term changes or the long-term variability effect on the Indian rainfall. So this climate changes, rather than the interannual effect on it, the longer term timescales like decadal and even interdecadal also definitely will be the more effect in it. So that's why Victoria mode is having this effect of this decadal shift.
Okay, can you elaborate why?
Okay, I think, sorry, we better move on because we're way behind time. Sorry about that. So thank you very much again. You can talk in the coffee break. So our next speaker is Glauber William de Souza Ferreira. I hope I haven't mangled that too much. So I'll give you a bell when the 13 minutes is gone.
Good morning, everyone. I am Glauber Ferreira. I am a PhD student at the Federal University of Itajubá in Minas Gerais, Brazil. and I appreciate the opportunity to be here to present the main results of a work that I have done with my PhD supervisor, Michele Reboita. And in this work, we assessed how the South American monsoon may change in the future using statistical scaling with CMIP6 GCMs. First, I highlight that South American monsoon system, it's crucial to drive the seasonal precipitation in South America, mainly in tropical and subtropical latitudes. During the rainy season that occurs between October and March, South American monsoon brings large amounts of precipitation over several areas of South America, including Brazilian Amazon, the Midwest Brazil, South and Southeast Brazil, and also southeast of South America, and the La Plata Basin region. This period is characterized by the strengthening of deep convection that is favored by the moisture transport promoted by the South Atlantic subtropical anticyclone, and also the moisture transported by the trend winds from the North Tropical Atlantic to the tropical South America, and then channeled by the low-level jets to the South and Southeast Brazil, and also the southeast of South America. The conjunction of the moisture transport promoted by the South Atlantic subtropical anticyclone and the low-level jets gives rise to the South Atlantic convergence zone. In contrast, during the Austral winter, the atmospheric circulation changed substantially, and the South American monsoon weakens, leading to a drier climate in the monsoon regions. However, some regions that are influenced by South American monsoon, like southern Brazil and southeast South America, experience a more homogeneous distribution of precipitation during the year, due to the higher occurrence of frontal systems and mid-latitude disturbance. And the South American monsoon is also marked by the rainfall variability. As we can see, the central Brazil presents annual precipitation totals higher than the central Argentina. So, given the importance of the South American monsoon, mainly due to several socioeconomic activities that are highly dependent on the system, like the agriculture and hydropower generation, it is important, it's relevant to investigate how this system may change in the future. In this context, the main goal of our work is to compare the South American monsoon life cycle using two data sets. The first is the projections and simulations provided by 8 global climate models of CMIP6. And the second data set is the projections and simulations of these global climate models of CMIP6 with statistical downscaling technique. Talking briefly about the methodology, first, we selected the GCMs according to the ranking technique developed by Hoop et al., in which the performance of a model is assessed according to its ability in simulating the statistical climate features of a given area in a given period. After choosing these 8 models, we interpolated the GCMs for the reference dataset grid, that in this case was the CPC dataset, the Climate Prediction Center. After the interpolation, we applied statistical downscaling with the quantile delta mapping developed by Alex Cannon. And it's a very interesting technique because when we we do more regionalized studies, this technique corrects the biases in the historical simulations, but also preserves the trends in the projections. We use it the historical period of 1995 to 2014. And after this application of the statistical downscaling, we calculated for each grid point the South American monsoon life cycle using the method of Liebman and Marengo modified by Bombardi and Carvalho. In this method, we calculate the anomalies, we calculate the accumulated anomalies of precipitation in pentads or 5 days, considering the climatological average of all pentads under study. After after calculating the accumulative anomalies of precipitation at each iteration, we smooth the time series with a 3-point moving average that was applied 30 times. After that, we applied the first derivative to the time series, in which we find the maximum and minimum locals of this time series that corresponds to the onset and demise of the rainy season of the South American monsoon. This procedure was done to the CPC dataset and to the both datasets of CMIP6, both the original outputs and the statistically downscale outputs, and also the two forcing scenarios that we employed, SSP2 4.5 and SSP5 8.5. Now talking about the first part of results, that is the validation for the historical period. When we see the simulation of the original outputs of CMIP6, we see here we have the ensemble average with the 8 global climate models. When we see this ensemble, we see that it misrepresents the South Atlantic, the South American monsoon, because it amplifies the South American monsoon to the Northeast Brazil, which is unrealistic. When we see the statistically downscale CMIP6 dataset, we see that improves the representation of South American monsoon and also reduces the overestimations of precipitation in Western South America. About the parameters of life cycle of the South American monsoon, it showed that both data sets, the CMIP6 original outputs and the CMIP6 statistically downscale, both data sets have a misrepresentation of the onset monsoon, mainly in the region east of 6 to west, giving a bias of about 2 to 3 pentads in relation to the onset provided by CPC, but the statistical downscaling technique improves the simulation of onset on the region west of 6 to west, or Western Amazon. Similarly, for the demise monsoon, we see that in the region east of 6 to west, both data sets indicate a bias of about 1 to 2 pentads in relation to the demise provided by CPC. But the statistical downscaling improves the representation of the demise onset in the region west of 6 to west. As a result, we have that both data sets have a bias in the duration of the South American monsoon. So concluding this first part of results, we have that statistical downscaling employed with the quantile delta mapping improves the seasonal amount and spatial distribution of rainfall compared to the original outputs. But regarding the South American monsoon life cycle, the statistical downscaling does not show huge improvements unless the representation of onset and demise of the South American monsoon in the region west of 6 West, or the Western Amazon. Now talking about the second part of results that is composed of the climate projections. We see that both data sets, and when I say both data sets, I mean the bias corrected and the original outputs, both data sets show an increasing amount of precipitation in regions like the South and Southeast Brazil, and also the Southeast of South America, and also a reduction of precipitation in the North of South America and Brazilian Amazon. Comparing the two scenarios, we see that SSP5 shows a stronger signal of both the reduction of precipitation in Brazilian Amazon as the increase in precipitation in the subtropical latitudes. And also the statistically downscale projections show a stronger signal compared to the original outputs. This signal is more evident in the second half of 21st century onwards. Regarding the onset monsoon, we see that both data sets also indicate a late onset in the monsoon and on the South American monsoon, a late of about 2 or 3 pentads, depending on the region. And also the SSP5 and the statistically downscale projections show a stronger signal of delayed onset in relation to the original outputs. Similarly, for the demise monsoon, both data sets indicate a late demise of about 1 or 2 pentads. Yeah, the late demise is shorter than the late onset. And also the SSP5 and the statistically downscale projections indicate a stronger signal than the original outputs and the SSP2 forcing scenario. As a consequence, we have that both data sets indicate a decreasing duration of the South American monsoon in the future. This repeating South American monsoon, it's about 1 or 2 pentads, but depending on the region, it may be 2 or 3 pentads. So concluding these results, we have that although CMIP6 statistically downscale improves the amount and the spatial representation of the precipitation across the South American continent, there is no huge improvements in the spatial pattern of the monsoon life cycle when compared to the original CMIP6 models. The projected change for precipitation show a stronger signal in the statistically downscale projections than in the CMIP6 original outputs. And also both data sets indicate a stronger signal towards the end of the 21st century and in the SSP5 scenario, indicating drier conditions in the Amazon and wetter conditions in the South and Southeast Brazil. Regarding the life cycle of South American monsoon, the projections indicate a late onset of about 2 or 3 pentads and a late demise of about 1 or 2 pentads. As a consequence, we have a shrinkage of the life cycle of the duration of the South American monsoon, a retreating of about 1 or 2 pentads. What is interesting is even the South American monsoon is projected to decrease in the future, the amount of precipitation is projected to increase, suggesting that these regions under the influence of South American monsoon may experience extreme events of precipitation in the future. In fact, in recent years, we have shown numerous disasters occurring in the state of São Paulo, Rio de Janeiro, and Minas Gerais in the rainy season, which caused the death of 100 people in these states. In this article that we published in 2023, we discuss with more depth about these results and also discuss about the individual projections of the 8 global climate models we employed. And practically all models converge to a delayed onset and to a reducing duration of the South American monsoon in the future. So I appreciate again your audience and the opportunity to present our research here. And I thank you for your attention.
Have any brief questions? Okay, if not, I think we better move on swiftly. Oh, there is one. Microphone's coming.
Okay. Very good study. And it's very important to know that models cannot reproduce main feature of South American monsoon. It's really very important. And my question is about the definition of onset of monsoon. Definition, what is your? Yes.
It's provided by the first derivative of the time series of the accumulative anomalies of precipitation.
Okay, after the fact. This is observation after the fact when monsoon start. Okay, thank you very much.
Thank you.
Okay, thank you very much.
Thank you.
Sorry for the keeping, but we have one more talk before the break, and that's by Paul Arthur.
Hi, can you hear me? Okay, so I'm Paul Arthur. I'll be talking about the Sahel precipitation, or the West African monsoon. I'll be talking mostly about the uncertainty, and on the uncertainty, I'll be focusing on the model uncertainty. So that's work, a study we are doing with Anna Arama at the University of Reading, okay, and Julien Boet from Fairfax. Okay. So first, I will talk a little bit about the Sahel. Where is the Sahel and why the Sahel? So basically here, what I'm showing is the average precipitation in summer. So where we have the bluish colors, that's where we have the maximum of precipitation. So we can see that it's over the coast mostly. In the north, we have the Saharan Desert, which is dry. And in the middle of that, we have a transition area with that we call the Sahel. So now if we average precipitation over roughly this box, and we look at the value for each month and each degree of latitude, what we can see is that precipitation is shifting northwards from the winter to the summer, leading to the monsoon season over the Sahel. So for this talk, I will be using an average over the July, August, September period. And then we have a southward shift, which marks the end of the rainy season. So it's basically following roughly the maximum in temperature for the northern hemisphere. Okay, so now if we average precipitation over the Sahel and we look at the anomaly, what we can see is that we have a strong interannual variability, but also a multi-decadal variability. So we had a decrease of the precipitation between the 1950s and the 1980s, which have been associated with a large drought over the Sahel. And since then, we had a small recovery, so an increase in precipitation. It's a partial recovery because we are not going back to the values we had in the mid-1950s. But what we know is that the variation of the West African monsoon has strong impact on the population. We can think about the impact on human health, agriculture, the economy. The drought of the 1980s was a very good example of what could be the impact of the change of the West African monsoon. But what we would like to know now is how this monsoon will change in the future. Will we have an increase of the precipitation or a decrease of the precipitation? So to know that, we used climate models with different emission scenarios. What I'm showing you here is the average of the some same six models. So I'm looking at the end of the 21st century, and at the in summer, with a high emission scenario, the SSP5 8.5 emission scenario. And what we can see is that we have increase in precipitation over the center of the sail, a decrease over the western part of the sail. So it's a zonal contrast, which we have shown to be relatively robust because we got it for the same 6 model, but also the same 5 and the same 3 models. However, when we look at the ensemble spread, which is the standard deviation computed across all projections, what we can see is that the standard deviation, the spread is sometimes stronger, or it's at strong or sometimes stronger than the ensemble mean. So basically, we know that we have this particular pattern, but the changes are very uncertain. So in this talk, I will be talking mostly about uncertainty. When I say uncertainty here is mostly the differences between the projections of the different models. All right, so in another paper, we looked at the different trajectories we could have in the future change of the precipitation. So what we've done is to compute pattern correlations between models, between projections, and we computed a family tree from that. So here, what we have is that the models which are close from each other on these family trees are producing some projections which are also close. So if you do the average in each of those groups, what we can have is different trajectories. So we have one trajectory in which we have a strong increase in precipitation, another one in which we have a decrease, and 2 groups of model, which is a majority of model for which we have a zonal contrast, but with different patterns in the change in precipitation. But what we can notice in this family tree is that models which are from the same institution, so for instance, here we have the 3 IPSL models from SIM5, are doing projection which is relatively similar. It's the same for the 2 IGEM models. So there is the idea that when we do an ensemble mean in each of those groups, we could have an overestimation of one particular representation of the climate system from one particular group, thinking that maybe those models are relatively similar. But we can also see that sometimes you have different trajectories for models from the same group, which means that it's a bit more complicated than that. So what we are doing here is to look at the role of the model uncertainty, but more specifically of the structural uncertainty. So what are the differences between models, and can this lead to different trajectories? So what we have done is that we have used 39 CM6 models, the SSP5 8.5 emission scenario. For now, only one ensemble member for each model, but we are assessing internal climate variability using 4 large ensembles. So large ensembles are models for which we have here between 30 to 50 ensemble members, which are useful to look at the impact of internal climate variability. To look at the similarity between projections, we computed the root mean square error between the different projections of the different models. So it's not done only over the sail, it's a slightly larger box to account for West Africa and for the change in the atmospheric circulation, the dynamic of the monsoon. Right, so how did we decided how many components the models have in common? Basically, what we've done is to look at the components of the different models, so the atmosphere component, ocean, land, and sea ice components. So as an example, if we have 2 excess models, what you can see is that the only difference is that they have a different version of the sea ice model. So we have decided that this component is not really in common. And what we've done is to say that basically they have 3 components in common. So we took IGEM3, and between IGEM3 and Access, the only component in common is the atmosphere model, and ENM75 has no component in common for IGEM3. So that's an example, but we have looked at that for all models we had. So at first, what we have done is to look at the future change of the precipitation. So it's a difference between the end of the 21st century, 2060, 2099, minus 1960, 1999, with a high emission scenario, SSP5 8.5. We have, so that's over the center of the sail. So we have mostly an increase of the precipitation. If you look at the multimodal mean, that's a horizontal red line here. So it's an increase in precipitation, but you can see that from one model to another, you can have a very large range of responses. So what we have done is to take the 5 models for which we have a weaker change, the 5 models for which we have a stronger change to illustrate that. So in one case, we have basically no change in precipitation over the center of the sail, a decrease over the western part, maybe a southward shift of the precipitation over the Atlantic Ocean. In the other case, we have we have a strong increase in precipitation. Okay, so now we have computed the pairwise mean square error between all projections. So basically, we have the median here, the distribution. So here we took the 39 models and we have done all possible combinations between those 39 models and we compute the mean square error for each of the combinations. So we got a lot of data, a lot of values that we just used for the distribution and this box plot. We have the median here, which is a measure of the uncertainty, basically the dispersion between the projections. You can see that it's relatively large. What we can do is to compare it with internal variability. So for that, we've computed the mean square error between the different ensemble members of each large ensembles we have, and then we have put all data together to compute the box plot here, the box plot. So you can see that the distribution, which is associated with the effect of internal variability, is much weaker than the median we have here for when we are using all models to compute the differences. So basically, those differences are unlikely to be due to internal climate variability, which is consistent with some work we've shown before, which is showing that at the end of the 21st century, the main source of uncertainty for cell precipitation is the model uncertainty, not internal climate variability. And then we look at what results we have when we have, we just took the models which have no components in common. So you see that we still have a strong uncertainty, which is comparable to when we take all models. When we have one, two components, it does not change much. But now when we have three components in common, we have a decrease of the median in the distribution. And when we have all components in common, we have a stronger decrease and a very small envelope. We have also a very small envelope because we have not so many models for which we have 4 components in common. So of course we have more data sets, more values for when we have no component in common and when we have 4 components in common. So what we have done is to resample this distribution, taking the same numbers of pairs we add for when we have 4 components in common. We have done 10,000 permutations and new combinations, and we have represented, we have shown the median we got here with the red dots here. So we can see that when we have 4 components in common, we are outside of the distribution we could have when we resampled the data set for when we have no components in common. So it's unlikely that we have such a difference just by chance. It's the same thing actually for when we have 3 components in common. So what we have done as well is to look at when we have model for the same group or a different group. You can see that we have strong differences as well. We have done it for when we look at the same atmosphere model and when we have a different atmosphere model. So we have a significant differences, which is due to the use of one or another atmosphere model. We've done it for all components. So it's also the case when we have the land model. It's taking a strong difference, but we didn't get anything significant for the ocean model and a moderate change for the ice model, which is, to be honest, a bit surprising because we know the change of the ocean temperature to be a strong source of uncertainty for cell precipitation. So of course, there is a caveat in our analysis, which is that we are not assessing for the parametric uncertainty. So a lot of models are using NEMO, but they have different parameterization, and we can't really account for that yet. But that could be a future development. So that was for the West African monsoon, and basically what we've done as well is to look at that for different monsoon domains. So here I have the monsoon domains in colors. I saw that I don't have the colors on the plot, but basically the North Africa, the reddish here, is here. So we are getting something which is very similar that when we just use our box over West Africa, because it's basically this kind of same domain. If we focus over the South Asian domain in which we have India, you can see that we have a significant differences when we have 4 all components in common. So it's leading to stronger differences between models. But when we have 3 components in common, we have no strong differences and not significant. So basically the result we show and we got for the North Africa, for the West African monsoon, that's model dependent. That's monsoon domain dependent. Well, so my come message. Have I been too quick? Okay, right. Okay, so my take-home message is that we have a lot of uncertainty when we look at the effect of the climate change on the precipitation for the Sahel. we know that the model uncertainty is very large. And that's why we looked a bit at this question, this time looking at the structural uncertainty. We've shown that when you have three components in common, we have more similarity, 3 and 4 components in common between models. Of course, we don't look at the parametric uncertainty here. More complex interactions we could have between the components. But that, yeah. Okay, something we've obtained, but that I've not shown here because I was not sure to have much time, was that we also look at the sources of precipitation changes, so decomposing precipitation to the thermodynamic and dynamic components. And what we show is basically, so as what we got with a change in precipitation is mostly to do the dynamic. So when we have 3 components in common, it's changing a bit the thermodynamic. The uncertainty we have is a certain thermodynamic effect, but not so much. It's mostly to do the dynamic. Right, okay. And what we think is that we could think about using those kind of approach for model selection. Like if you want to do an impact studies, you don't know which model you want to use, but you need to use a regional model. So you won't use 39.6 model because that's too much data to run your regional models. You have to select models. Instead of looking at all data, you could already think that maybe if they have a different atmosphere model or if they are from a different group or that's a different model, you could select them to have different trajectories. Kind of the ideas, and also to think about model uncertainty, like if I want to do an ensemble mean, not having too much model from the same group. Okay, thank you.
Thank you very much. So I suppose differences in SST, changes in SST patterns in models could equally be driven by the atmosphere component of the, and not the actual ocean component.
Okay.
Changes in the winds.
Could be, yeah, but we could have a collapse of the AMOC.
Yeah, okay, as well, yeah.
Yeah,
or a different slowing of the AMOC. Are there any further questions? Everyone wants a cup of tea. So I think we'll thank Paul Arthur again. And I think we should give a round of applause for all the speakers in this session. Are you taking over?
Okay, thank you. Here we come to the end of the talk of today's session. And I would like to thank Professor Matthew Collins for chairing the session. Thank you.
Ladies and gentlemen, on this occasion, we are glad to announce that we'll be screening a short movie. This is about IITM Center for Climate Change Research, CCCR, which was established to better understand the science of climate change over the tropics and enable improved assessment of the regional climate responses to the global climate change. CCCR has grown and nurtured under the able leadership of our Dr. Krishnan. Today, we'll be screening a short film highlighting the research capabilities of CCCR. The movie title is Center for Climate Change Research Dedicated to Understand Climate Change. Thank you.
Weather and climate, 2 elements that define every facet of our existence. Climate change affects our health, our livelihoods, and the very future of our planet. Human activities have triggered significant changes in the global climate system. Understanding these shifts is crucial for preparing ourselves and future generations.
In 2007, the Honorable Minister for Science and Technology and Earth Sciences recommended the establishment of a specialized center dedicated for understanding climate change. Eventually, in 2009, this led to the approval of the establishment of the CCCR, that is the Center for Climate Change Research at the Indian Institute of Tropical Meteorology by the Ministry of Earth Sciences under the Global and Regional Climate Change Program, the 11th Five-Year Plan.
Over the past 2 years, it's my privilege to look after the duties of Project Director of the Center for Climate Change Research and continue to support the significant scientific accomplishments achieved by the CCCR scientists and researchers under the leadership of Dr. R. Krishnan, Director IITM.
The CCCR quickly became the hub of innovation and research, contributing to national and international climate studies. One of its key achievements was the development of India's first Earth System Model, IITM ESM, contributing to the prestigious Intergovernmental Panel on Climate Change report.
Earth system models are important tools that integrate the interactions of atmosphere, land, ocean, cryosphere, various Earth system components that enable us the assessment of regional and global climate change. The IITM Earth System Model first version was developed in 2013, and subsequently in-house development has been carried out to achieve a relatively balanced framework for addressing the long-term climate change over the region. At present, the next generation IITM ESM is being developed indigenously at CCCR at a higher resolution, which will provide us deeper insight into the climate variability and change, and also help us understand the challenges of climate change we face over the Indian region.
CCCR led the preparation for the first climate change report for the Indian region from Ministry of Earth Sciences. This open access book, Assessment of Climate Change over the Indian region, discusses the effect of human-induced climate change on the Indian subcontinent, regional monsoon, the Indian Ocean, and the Himalayas. The CCCR also leads South Asia's contributions to the World Climate Research Programme's Coordinated Regional Climate Downscaling Experiment, providing valuable data to enhance regional climate resilience. Model outputs published on the Earth System Grid Federation, Codex Data Node via the CCCR IITM Climate Data Portal are being extensively used by state government planning boards and disaster management authorities for preparing regional climate impact assessments and reports.
A greenhouse gases monitoring program started in 2009 at Sinhagarh, which is near Pune. And currently we have a site at different locations. For example, at central India near Bhopal, where we have a 72-meter tall tower, where we are monitoring different greenhouse gases such as carbon dioxide, methane, and various other parameters. Also, we are monitoring the carbon fluxes. And under the MetFlux program, we have tower at Kaziranga National Park where ecosystem exchange is studied. So we are measuring carbon fluxes using eddy covariance technique. Other than this, we have observation at mangrove forest site at Pichavaram. This is near Tamil Nadu, where we are monitoring the greenhouse gases such as carbon flux and methane. And we have observation site in Nainital, where we are measuring carbon flux in forest ecosystem.
CCCR began soil moisture observations in 2017, using cosmic ray soil moisture observing systems to study soil hydrology and its role in land-atmosphere interactions, advancing the signs of climate change. Understanding the past is key to predicting the future. The Paleoclimate and Dendroclimatology Research Group at CCCR studies past climates, dates historical events, and analyzes natural disasters like droughts, floods, glacier retreats, and volcanic eruptions using tree rings to offer data beyond instrumental climate records. The group also uses speleothems, limestone cave deposits, to reconstruct the Indian monsoon precipitation for the Holocene period. It has produced high-resolution rainfall data of the Indian monsoon for the last 3,200 years. Recently, the group established protocols and lab setups for trace element analysis in speleothems to study and link environmental changes to historical human habitation and migration. The Water Isotope Research Group at CCCR studies the role of hydrometeorological processes on water isotope values across India and their effect on climate reconstruction. They have recently begun water isotope modeling activities for improved climate modeling.
My group do research on atmospheric chemistry and climate using observations and model simulations. We use highly specialized balloons to measure ozone, water vapor, and aerosol backscatter at the high altitude region, that is up to 30 kilometers, at the southern slopes of Himalaya, that is at Nainital, and in central India at Bhopal. These measurements help us to understand transport of gases and aerosol to long distance variability of ozone, water vapor, cirrus cloud, and related climate change. In addition to these observations, we use chemistry climate model simulations to understand the climate change globally with a focus on the Arctic region.
Alongside climate observations, research on measurements and modeling of atmospheric chemical species is also carried out at CCCR IITM. Over the past decade, the Atmospheric Chemistry and Climate Group at CCCR has measured reactive trace gases in different environments. This work has enhanced the understanding of these trace gases and their impact on the Earth's radiative budget, both directly and by altering levels of short-lived climate forces. These observations are conducted globally, extending to remote regions such as the Arctic and Antarctic. Beyond research, the CCCR plays a vital role in capacity building, offering training and outreach programs to stakeholders, scientists, and students, helping to shape the next generation of climate experts. As we look into the future, CCCR continues to innovate. The Institute has established the Climate Data Archival and Distribution System, CDAS, to disseminate climate change projections using the IITM Earth System model developed in-house at IITM Pune. Inaugurated by the Honorable Secretary of Ministry of Earth Sciences in August 2024, the CDAS server is designed for large-scale data management, enhancing climate research capabilities in India and abroad. Supercomputers play a vital role by providing enhanced computing power to run the Earth System models ESM for generating climate change projections. For performing climate projections using ESM and to analyze huge amount of data from the ESM, supercomputers are necessary. The climate projections using IITM ESM and regional climate change projections at CCCR are carried out using high-performance computing system at IITM. The CCCR building is recognized as one of India's non-conventional, energy-efficient, and eco-friendly thermal active building or green building. Certified by the Ministry of Earth Sciences in 2012, it employs radiant and evaporative cooling systems to promote energy efficiency and sustainability. A remarkable milestone for CCCR came with the prestigious recognition of Dr. Roxy Matthew Cole, who was awarded the Vigyan Yuva Shanti Swarup Bhatnagar Award 2024 under the Rashtriya Vigyan Puraskar by the Government of India.
Over the last 15 years, I am very happy that CCCR has evolved into a truly outstanding center for addressing all the key aspects of global and regional climate change scientific issues.
Our climate is changing, and the work done at the Center for Climate Change Research is critical to understanding these shifts. As the world grapples with the effects of climate change, CCCR stands at the forefront, guiding India and the global community towards a more resilient and sustainable future.
Thank you. We will now break for tea and we'll assemble back in 10 minutes. Tea and coffee has been arranged in the guest house and in the basement of Meghdut Hall. Please assemble after 10 minutes. Thank you. Speakers of the next session are requested to upload their presentation in the computer here. Speakers of the next session, you are requested to upload your presentations in the laptop here. Thank you. Sorry. I request everyone near the Meghdut Hall to please assemble in the hall. We'll be beginning our session now.
Welcome back to session 9. The theme of the session is monsoon in a changing climate. And the chair of the session is Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology, Pune. And the rapier chair of the session are Kalik Visist and Priya Kumari. Therefore, I would like to request Sir to kindly chair the session. Thank you. Yeah. Mike.
Hello, hello, hello.
Hello, thank you. Today, welcome all of you to session 9, theme 4, that is monsoons in a changing climate. In this session, we have 5 talks. 3 of them are online and 2 here in person. So the first talk is by Professor Tianjun Zhou from IAPs and from the Chinese Academy of Sciences. His talk is on constrained projection of Afro-Asian monsoon precipitation. Professor Tianjun, are you there online?
Hello, Dr. Krishna. Thank you for your introduction. I am Xiaolong Chen, and I'm the co-author of the Tianjun Zhou's work And Tianjin has to deal with some urgent business, so I give this talk on behalf of Tianjin.
Okay.
Thank you.
Okay. Well.
Can you see my PowerPoint?
Yes. Yes, we are able to see.
Okay. Okay.
Please.
Great. Thank you.
Yeah, we are about 20 minutes late, so I would request you to do in 18 minutes. I'll just give a warning, and then
Okay.
2-3 minutes before I'll give a warning.
Okay, start my talk. Hello everyone. I'm very pleased to introduce our recent work. Sorry, not very recent because it has published in 2022. It is about to constrain the projection of Afro-Asian monsoon precipitation projection. Okay. We all know that the monsoon precipitation is very important because it has large variability across the monsoon regions and has a great influence the global energy budget and water cycle. And also in the precipitation variability can affect the water resources because it is very important to the so many people because of 2/3 of the global population live in the monsoon regions. Okay, we all know that the monsoon domain has contained several regional monsoons, and here in this study we focus on the Afro-Asian monsoon. It includes 3 regional monsoon regions. That is the Western African monsoon and the South Asian monsoon and the Eastern Asian monsoon. And the monsoon region is defined following the definition by the Wang in 2012. Why we focus on the Afro-Asian summer monsoon and why we can treat them together? Because we can see in this figure, we can see there is a systematic the circulation system across the North Hemisphere, and there is a broad cross equatorial flows from the Southern Hemisphere to the North Hemisphere in the monsoon seasons. And also there is a large scale the convergence of the monsoon circulation over the in the tropic to the subtropics. So it can be treated as the global scale system as a whole. That's why we can treat them, can study them together. And we all know that these 3 regional monsoon regions are changes in phase on many time scales. Such as if we do some analysis on their variability, we can find a dominant mode of these monsoon regions. For example, for their precipitation, we can see they can change or vary in phase. For example, at the same time. So we next for the projection of the monsoon regions, we all know that the precipitation will increase in these monsoons. We can see that a pronounced increase over the global North Hemisphere monsoons, and which is mostly contributed by these 3 monsoon regions. Because in the North American monsoon, the projected precipitation will decrease in the models. So the response of the Afro-Asian monsoon precipitation is stronger than over the global and the other sub-monsoon regions. Okay, so it is very significant in the projection. So yes, we know that there are also large uncertainty in the projections. For example, in this paper published in 2020, and we examined all the regional monsoon precipitation in the future, and to separate the sources of the uncertainties following the IPCC methods. And we can see that in the in the next century, the uncertainty is from the three different sources. One is the internal variability, that is the climate noises, and it is natural and the variability. And the other is the scenario uncertainty, because we don't know the how the economic or the emission scenario will change, and so there is various scenarios we use to project the future. And the most important actually is the model uncertainty. We have we can know that the model uncertainty will increase with the time, and will usually will be the dominant the uncertainty in the long term projection. Sorry. So we have know that the uncertainties in the future projections is controlled by many factors. One that is because the different model has different the climate sensitivities, and especially in the CMIP6 ensembles, it has been noticed by the IPCC AR6 in the assessment processes, and so because the CMIP6 models, most of them have the very high in the climate sensitivity, so we have to develop or use some constraint method to constrain the projected result that is affected by the climate sensitivity. So because the global monsoon or the regional monsoons, the precipitation is very sensitive to the maybe sensitive to the climate sensitivity, because it is about because the precipitation is closely related to the moisture increase in future. So we want to know that if the climate sensitivity also affect the precipitation changes in these three regional monsoon precipitation projections. So if yes, we may try to do some constraint the future projections of the monsoon precipitation to find how to use the observed temperature changes that are related to the climate sensitivity. And actually, some constraint has been done in the AR6 report, and yes, we also try to use to follow such an idea and to constrain the precipitation in the monsoon regions. So this is our questions, and one is what are the future changes and uncertainty in Afro-Asian monsoon precipitation, and how could the high in the climate sensitivity of CMIP6 model impact the monsoon projection, and can we constrain the precipitation projection using observational information? This is the data and matter we used, and we used 30 models in the CMIP6, and the scenario is the SSP5 8.5, and the method, the main method to constrain the result is the emergent constraint, that we want to find some historical uncertainty in the historical simulation with the future projections, and establish a solid physical mechanism between them, and try to use statistical the relationship to constrain the future projection. First, we use the intermodal a EOF method to extract the dominant uncertainty mode across the models. So in the left figure, we can see the first leading mode of the uncertainty of the precipitation projection in the Afro-Asian monsoon regions. It shows an increase the precipitation at the same time in the three regions. So and the most actually this uncertainty mode is most contributed by the Western African monsoons, because the uncertainty contributed from this region is the highest, and the second is the East Asian monsoon, and the last is the South Asian monsoon. The left figure shows the corresponding principal component of the first leading mode. And yes, we want to know how the uncertainty in this showed by the PC1 from, and if we regress the surface temperature changes in the future onto the PC1, we can find a contrast between the warming between the north and the south hemisphere. It is characterized with the warmer in the north hemisphere. It is similar to the polar amplification. This character, these features, and so it is very. It is very easy to understand because this character means the very enhanced inter-hemisphere the heat contrast. So it will increase the enhance the cross equatorial flows and enhance the monsoon. So that is consistent with the increase of the precipitation over all the monsoon regions. Actually, this features has been reviewed by previous studies, such as the Dr. Bing Wang in 22, and they found that the north hemisphere, the precipitation in future changes, and the cross equatorial flows is controlled by the inter-hemisphere, the temperature contrast in the future. Yeah. And because we want to know the future changes is easy to understand, but how it come from or where it come from. So we want to know if it is come from the historical simulation as entity. So we next we regress the historical preservation trend, the warming trend in the historical simulation onto the PC1. Yes, we can find a similar patterns that is also show the similar contrast between the two, the north and south hemisphere. Yes, this is the future, the projection pattern uncertainty, and this is the historical simulation patterns of the warming trend. So they show similar contrast. Yeah, so that provide us the possible constrained relationship to reduce the uncertainty and correct the future projections following the inverted constraint method. Yes, that is a very strict method, because if you find a relationship between the historical simulation and uncertainty and the future projections, and because we have many observation. It has the very much smaller uncertainties than the model uncertainty. So using the observation, we can get a constrained projection that has the smaller uncertainties. Yes, because yes, we must establish a solid physical explanation for this relationship. So we, as I mentioned before, it could be related to the model's climate sensitivity. Yes, if we can we can find a good relationship between the model's climate sensitivity and the simulation of the warming trend. The contrast of the warming trend between the north and south hemisphere in the historical simulation. So this uncertainty across models has a very good relationship. And the next we can see that in the uncertainty in the present day of the temperature contrast between the hemisphere and the future contrast of the changes of the contrast in the future also has a very good relationship. So I think the physical is very straightforward. If a model has a larger sensitivity, it will have a larger trend of the thermal contrast between the hemisphere in the present day, and then in the future, because the more CO2 and the more warmer, and it will induce a larger increase of the projected inter-hemisphere contrast. So it will induce a stronger the Afro-Asian precipitation in future. Yes, following the inverted contrast, we can to induce the constraint result. Yeah, you can do the constraint for the PC, and also you can directly constrain the Afro-Asian the precipitation. They can derive the similar result, and the result is that the constraint value of the Afro-Asian precipitation is about 10% increase, and actually it is lower than the raw projection, because we reduce the effect of the high climate sensitivity of most of the six models. Yes, this is the pattern, correctly the precipitation projection of the showing in the pattern, and it show the relative correction, the relative to the unconstrained result we can find in most of the regions in the Monsoon regions. The precipitation projected precipitation is reduced than compared to the raw precipitation change. Yeah. So
can you just
okay.
In a minute?
Okay, I'll finish soon. And next we will try to extend explain the precipitation change to the more the impact field, and we to try to find the relationship between the precipitation and the runoff. And in the models, we can see in the future changes of these two variables has a very good relationship. So we deliver the precipitation to the runoff. We show that in the different regions of the Monsoon regions, we can see both the precipitation and the runoff. The land fraction of where has the significant increase of the runoff and the precipitation on both both reduced compared to the raw projections. So the land areas that we experience a significant increase of the precipitation or runoff is just about above the half the 57% of that of the raw projection. Yeah. So I've finished here, and this is the summary. And we know that the projected spread of the precipitation in the Afro-Asian Monsoon regions is related to the present day inter-hemisphere contrast biases. So using this relationship, we can constrain the future projection of the precipitation. After the precipitation is constrained, it is projected to increase by about 10 percentage in the constraint projection. Yes, it is only the just 70% of the raw projections. Okay, I'll finish here. Thank you.
Thank you, Dr. Chen. We have time for one quick question. Dr. Ashit. And I think there is one question online. Dr. Chen, maybe you can see that, you can respond to the question online later. But there is one question from here. From the audience.
Just I wanted to check, like, prior to preparing the runoff projections, like you carry out any bias correction or calibration of the scenarios?
Okay, you see, if we to try to explore the impact from scenario uncertainty. Yes, here in this study, we only focused on the very high emission scenario, that is the 8.5. So yes, I think if using the different scenarios, for example, the low emission scenario such as the SSP 2.6, I think the result may be similar, especially if you focus on the long-term changes. But if you focus on the short-term or the near-term changes, I think it will need more ensembles to abstract the false signals, because in near-term changes, the internal variability is very strong, and it will impact the result.
Thank you, Dr. Chen. There are some online questions. Probably you can respond to them separately.
Okay, thank you. Thank you.
Thank you. So we can go to the next speaker, Professor Dev Niyogi. So he will be talking about urban meteorology in the context of monsoon systems. Professor Dev.
I just want to say thank you to the organizers. What has been clearly an impressive and very knowledgeable set of presentations thus far. The city of Pune is known for people speaking their mind. Today morning when I was coming, I took my Uber, and because I wanted the air to be on me, I took an XL, and the driver scolded me that for a single person, you should not take a large van. This is how the temperature increases in the cities by pollution. And I was so impressed, I gave him a 100 rupees tip right away, because this is exactly what I'm going to talk about. Urbanization is the new global change. And in the context of that, what we heard thus far has been in the context of the large-scale changes going on. But if you look at it in the global context, where Professor Mohanty talked about in the morning, what are some of the things going on with regards to the urban heavy rain aspects. Where my talk comes in is, given the fact that urbanization is the new global change, and given the fact that urban areas are getting many of these cascading hazards, and given the fact that there's this whole opportunities possible with the AI and machine learning and the digital twin framework, what are the ways in which we can start building these elements together for what could be a research to operations or research to service framing in that thing. You can send me an email if you have any question at happy1@utexas.edu. You also have much of my materials on the niyogi.dev webpage going on. So I have a lot of material, so I'm going to try and do this quickly. So urban hazards in the monsoon context, you can put it into two setups. One is what we heard with regards to many of the rain events in the context of monsoon. And the second, what we are going to experience, if not already experienced, is the urban heat. And within the context of the urban heavy rain systems, monsoon depressions and the tropical cyclones are some of the biggest heavy rain falling system. We had the thunderstorms and squall line kind of presentations in the morning before that. So urban features, they are largely a subgrid scale heterogeneity in operational models, if they are large coarser models, unless they're going down to a few kilometers, and urban feedbacks that people are trying to do for solutions, that if you're really trying to solve the issue of urban heating or something to do with urban areas, then it is really a within city heterogeneity issue. You're not going to do it for the entire city, you're going to do it in the parts of the city. So how do you actually bring in that level of details into a modeling system, and how can you make it scalable, replicable, and as a service that anyone, anywhere in the world can start using it? That's the basis of what I'll be talking. When I was here in my sabbatical in 2018, I was very fortunate we could start 2 urban programs, one of which was a national program through the Department of Science and Technology, which was a network program on urban climate. And then the national supercomputing mission that Professor Mohanty mentioned, which has been this large conglomeration of universities putting computational resources, urban data sets, models, and so forth. And there's a very nice transition that is happening now in the context of research to operation. Hopefully within the next few years, we'll start seeing we actually have an urbanized model for India and other places with high resolution. Just today, there was this report in Business Standard that Indian cities are bracing for heat waves, but they lack a long-term planning. Much of them have a heat plan, but what can you do in terms of the long-term solution that is still not known? And this is, I don't want to just pick on India. This is really a global problem. Most cities are not ready how to handle heat. most cities are not ready how to handle heavy rains and floods. And cities are not necessarily the only end place where the floods happen or heavy rain happens. They are sometimes the reason why heavy rain occurs. And this is what we have learned over a period of time. So here's an example of, for instance, what we're talking about with regards to within small cities, how do you want to do cooling? So if you have mitigative aspect by putting things like cool pavements or shading, you can actually have about 15 to 20-degree temperature differences based on the kind of mitigation efforts you can do. But for that, you first need to do some mapping. Now, the keyword I want to use here is called SIMBY, climate in my backyard. Much of what we have been doing has been talking in terms of global change, but when people are now looking for solutions, they're really looking for localized information where you can do some adaptation and heat mitigation or disaster mitigation issues associated with this increasing hazards. So for this, what we need is hyperlocalization. And by hyperlocalization, the question comes up, how do you do this? First and foremost, as Dr. Krishna always reminds, without understanding, what was the word you use? You're only going to be doing a fortune telling, that if you don't understand, then you're only going to be doing fortune telling and you're not going to necessarily have a good system. So first thing is that you need to have a good understanding and a methodology and a framework that you can develop your processes. Second, we need to have often a sustained evidence because there are so many processes that are important in an environmental system. How do you find out that this is how you want to put it into there? And to a large extent, I'm going to show this is exactly what happens in the pharmaceutical industry, that when you're trying to cure, what is the transition time from something that happens in the lab till the time you actually get the drug out in the market. The time that it takes, I just wanted to think about it, how many years it might be taking. So let's talk about July 26, 2005, one of the most iconic heavy rain events that occurred in Mumbai. Parts of the Mumbai got about 76 inches of rain, and other parts of the Mumbai were roughly like 2 or 3 inches of rain. So a tremendous heterogeneity within the city. And we have been studying the system, and it was what we found is that it was a convergence that caused because of a filament that was offshore, and the urban area created its own mesolow. And then it was over that region that 3 cells sort of got squeezed in, and they were raining perpetually over the next 24 hours. And you had 3 rain events that caused this rapid rain events there. We have been looking at the urban feedback about how urban areas are actually causing this heavy rainfall events, and especially in places like India. The urban heat and urban rainfall are interlinked. In fact, when you have a high urban heat, rain events occur outside the city. When you have everything, that is the rural area is also hot and the urban area is also hot, then you have pockets of very high heavy rainfall events that are occurring there. So the urban heat and the urban rainfall issue is also quite interlinked into the whole setup. In fact, we did a meta-analysis of all the papers that were published regarding to the urban rainfall, and we find that over cities, rainfall can be about 20% higher than the surrounding area. And the heat island is, of course, one of the factors by which you can have a modulation, whether this is going to be over the city or around the city. Recently, there was this paper we had in PNAS, and that showed that this is a global feature. Just like you can find temperature feedback from urbanization, you can find a rainfall impact from urbanization. And that urbanization rainfall effect is not something we have been dissecting out into our long-term data sets. And so that becomes an attribution issue, which at some point we need to start seriously thinking about, that how are we going to get the right projections if we are not looking at the local forcings by which the intensity of the rainfall is going to be modulated. So what is the mechanism that we have understood? There are roughly 3 factors. One is the mechanical heating associated with the urban area. Second is the mechanical deformation that can create a shear zone, which can create a localized mesolow. And a third is, of course, the aerosol concentrations. The combination of those 3, you could have a very juiced up clouds and convection occurring over the city, and that can create your urban heavy rain events there. I was very pleased to see last year we had the first urban radar network coming up in Mumbai. And so it's about 10 to 15 years from when the research is going on and when we start seeing an operational output coming up. So the research to operation transition is roughly about 10 to 12 years. Incidentally, this is the same thing that happens in the pharmaceutical industry, that from the lab to operational setup, you require about 12 to 15 years. Now, the question is, how can we speed up this transition from research to operation by developing some disruptive aspects that can help our weather and climate services? And this is where we start looking for newer ways by which we can transition into the development approaches that can help our approach. First, looking at these cities, it's a mess. There are numerous data sets out there, and each one of them will tell you a different map associated with the city. So if you are going to have a long-term data set, then we actually are going to have a very important data continuity issue about how do you actually map cities. Modis will look at it one way, you'll have the ESA world cover will looking at it another way. You can have. So first part is having a dynamic manner by which you can create your own data sets by attributes that are important for the model. So for this, we created the World Urban Data Analysis and Portal tool, which is called as WOODAPT. So it transitioned into what was a gridded land use data to a urban categories, and those are now part of the WRF setup, for instance, and some of the CLM aspect, they use the viewed up categories. And here's an example for Mumbai, that when you actually have the heterogeneity within the buildings, you can get the pockets of heavy rains that are occurring in Mumbai that you can see with regards to the red peripheral rains occurring at the coastal region. The second thing that we have now started doing is that can we use computer graphics to actually generate the input data for a model? And so what we're doing is taking a deep learning and vision algorithms, and almost like you might have seen into a video arcade where you're sitting on a motorcycle and kids might be seeing when there is a street going around. So what if you generate that imagery for a city as if it is a LiDAR image and then insert that into a weather model? And that's something we have been doing called as a digital synthetic city. So using deep learning and imagery that you have, you create the data that goes into the model to create the data anywhere then. So then you don't need to have expensive LiDAR measurements, say in places like Africa or places in India where you don't necessarily have the setup ready right away. Even in many European and US cities, it is not feasible, security or otherwise, to dynamically do that all the time. So this deep learning approach by which we can create data has been a very promising approach. And you can see these two images that were, one was generated using computer vision and one was generated by the Google Earth. And it's very difficult to detect a difference in that. And so when you actually attribute it out, they look very similar. Now, I want to change gear. So we have come to a transition in terms of our understanding that something might be happening with urban areas and rainfall to understanding that this is indeed what is happening. And we are developing models to represent urban area to improve our urban rainfall prediction. Now, another area where we are seeing this is with regards to the brown ocean effect, where the antecedent soil moisture availability can determine how far inland a monsoon depression or a storm can go. And so this link between soil moisture and the heavy rain bearing systems is a very well-studied system, especially in the monsoon depression data sets that we can start seeing. One of the first studies was by Krishnamurthy, then there was a paper by Emmanuel, which sort of popularized it for Australia. And then there have been, for monsoon region, Kishtawal from Space Application Center and us, we have several studies together looking at the relation between that. In fact, Tropical Storm Erin has been a well-studied one, which became a land cane after it came inland because Oklahoma was incredibly wet. And so the storm felt like it was back on the ocean. And so it is creating the rainfall. Now we have the data sets available with Cygnus and our new data sets that you can actually start seeing at the feedback that goes between soil moisture, the monsoon depressions, the inland potential, and the rain-bearing system that can occur. So we are very pleased that India is actually generating one of the first large soil moisture network for the entire country. So Dr. Krishna is one of the leads on that. And this is something that the Ministry of Earth Science will hopefully be starting soon, where you're going to have soil moisture network and data going from measurements to models, just the way we had the urban data sets coming in. So there are several issues out here. What does an antecedent mean? Is it 3-day, 3-week, 1 month? What does that mean? What is the area and so forth? So the questions are out there, but it boils down that we have an interrelation between heats And we have an interrelation between hurricanes. And this cascade of events occur at a given time where you might actually have a tropical cyclone coming in and you don't have energy or electricity, and you're going to have the heat stress coming into it, causing a cascade of features going on. So now back to the question. Now, if we really want to improve our land state, our urban areas, soil moisture into these models, how can we now disrupt and not have to wait for the next 12 to 15 years? Where can AI/ML or digital twins start coming into this? So for this, what we have been doing is a multi-pronged set. So through the US Department of Energy, we actually had a data unified infrastructure summary report that was recently developed. I'm a part of the BIRAC advisory, and we had this large analysis of how can we move from data to data information systems that can be used for Earth system models. We were testing this out sort of in the blind as part of the research demonstration project for the Paris Olympic. And it was a very interesting project where you actually tested it out. But the first one I want to share is this UT Globus. Professor Monti mentioned about it, that this is a global building height data set for anywhere in the world, any building height. You have this data set available for all the cities. It's downloadable, freely open. Many people have been using it for India and other places. So this UT Globus is the first one that I would like to highlight that you can use as part of the building height data set for inundation, heat, and other things going on. Much of the simulations that have been done, say from the temperature aspect, thunderstorms, or even thermal comfort, each of them have been really quite dramatically improved when you use some of the 3D morphological data set that are again openly available. Here's a representation of Austin, for instance, from this data, where it is generated using machine learning and the satellite data sets that are available to us. The digital twins is where you then start introducing the if-then scenarios, where you can actually take the building and generate information like how much is the energy used, what will be the energy used in a future climate, how can you control that? Does it have an opportunity to reduce the emissions? Does it have the opportunity for a nature-based solution? And what could it mean? And so we have been doing the series of tests through the WCRP Digital Earth effort that is going on. We call it the U-Twin. And Twin, like Austin Twin and University of Texas Twin that has been used there. One example of that is a thermal scape. So for many places in the world, we are now creating 2-meter temperature maps. These 2-meter temperature maps identify which are the really hot regions, which are relatively cold regions, and where there is a need for shade and heat so that you can start creating some sort of a place where you can have a relief for that. So that can be used for, say, the fire and smoke studies. It can be used for, as I said, this is the Paris example. I'll just quickly go through it, where we were using AI models for generating with the dynamical models going on. And this, incidentally, was for the marathon day, the thermal scape that we created, that if you are running in the marathon, what would you feel as a runner? What would people feel? And they had a question, what will happen if we delay the marathon by 1 hour or do it by an hour earlier? And we were trying to create this if-then scenarios about what would be the thermal comfort people will feel based on when you're trying to do this kind of scheduling. Okay, I'm going to skip through this. There's a nice animation as if you're running. But I'll say one important thing, and that is what is going to be available. That working under the Monsoon mission, we have been working with this Indian Ocean Land Atmosphere IOLA project, as well as the HWRF-X, which is a Hurricane WRF experimental version at UT. And we have been testing the dynamical versions and the AI-based versions. So in a real time, you're running the model as if it is the AI-based model, and then we are running the dynamical model. So this is for the Hurricane Beryl that came in, and we could see that that AI track was actually much correct, much earlier, and eventually the dynamical model picked up and so forth. We have done this for a number of them. In fact, okay, it looks like there's a Mac to PC translation. Anyway, we have done it for a number of such AI-based models. GraphCast for the FCN, mini transformers, and all the tracks that are available have been now created. Okay, this, I really wish at some point you can see this. But here's a big thing I want to share. So as part of what we have been doing, both with the Digital Earth Initiative, and we have now done a global reanalysis of GraphCast for the last 45 years. And this is now being put up at so this is a hindcast of the last 45 years at 0.25 degree globally. And so anyone who wishes to use the GraphCast boundary conditions can do it without having to need for GPUs and so forth. And why we use GraphCast, etc., you can take a look at that. But this is going to be hosted at the World Data Center for Climate, WDCC. It's about 340 terabytes of data. And this will be a first AI-based, GraphCast-based global reanalysis that will be available for much of the studies that can be done. So I will come to my conclusion, considering I'm at 18th minute. And I would just say that the digital twins or other areas, that this is where the framework we are building right now, that you work with physics model, you work with AI/ML-based approaches, merging the two. There are tremendous opportunities available right now, especially taking the AI-based models as a boundary condition to run a physics-based model, or using the AI-based model to provide the parameters within the dynamical model. And that is how we are leapfrogging going forward. I'll stop by here by saying that as we go towards hyperlocalization, the last point I want to really make is that AI/ML models are like a cheap insurance. They are quick, they happen, and you wish that it is always going to work, but you're never really sure it is going to work. And so this explainability and the uncertainty in the AI-based models still continues to be one of the big uncertainty. And this is where it should never be interpreted that we reduce our efforts in terms of developing physics-based understanding of the models. So use AI models, the digital twins, as sort of like an offset to leapfrog, not to replace the physical models, is the story I will tell, and I'll stop there. Thank you.
Thank you, Dev, for keeping time. Maybe we have time for one or two questions. Ivan.
Thank you so much, Dr. Krishnan. It is a very interesting and knowledgeable presentation. Improve our understanding of the urban climatic processes. But in case of India, we think currently we have about 35 to 40% of the population living in the urban areas. It is expected that by 2050, after 25 years, 70% people of India is prepared to migrate from rural areas to urban areas. And currently, we are unable to manage our urban areas with a population of 35%. So how we are going to manage 70%? Because the reason is that we have totally unplanned, unregulated, and unsystematic urbanization in India. That's why our urban areas are going to become the hot spot of climate change and climate change-induced natural disaster. So don't you think that these processes, which will improve our understanding of the urban climatic processes, should be part of urban land use policies? And urban environmental planning is imperative to implement these processes in the urban areas. Otherwise, we want to respond neither to the heat waves and the extreme event within the urban areas. So because none of the state governments so far has urban land use policy, urban land use planning. Even in Delhi, several thousand hectares of floodplain of Yamuna has been encroached upon by urban processes, including the government infrastructure.
You can see the slide here. No, I really, really appreciate that question. You can't see the slide here, but what I'm showing here is why data storytelling is your new superpower. If you have data, and if you have a lived experience, and if you can merge them together, it goes towards creating policies. Right now, people don't have data that can be used for creating the policies, is one of the things we hear. But I think when we create these data sets and we create this, I hope some policies will be done.
Thank you, Dave.
Thank you so much.
Running behind time, if there are some online questions. Yeah, you can probably respond to them.
I would like to I'd like to request the session chair to kindly present the mementos to the speaker. Yeah, sir.
Thematic policy.
I just use this, yeah. Okay. Thank you very much. And again, thanks for all the organizers for producing such an excellent program and conference. So let me just check this. Okay, this one. This one moves your cursor around. Look, this one moves this one moves both the cursor and the arrow and the light. Okay, so I'm Matt Collins from the University of Exeter in the UK. This is work that was really done by a PhD student, Harry Mutton, who is now working at the UK Met Office in the Climate Feedbacks group. And he, it's pretty much all his work, just under the guidance of a supervisor, a group of supervisors. And he got interested in the West African monsoon and how that might change under climate change. So he's produced 3 papers. Let's start with an orientation of the West African monsoon. So this is obviously Africa. This is not actually precipitation, it's the vegetation annual cycle. So this is measured from satellite. So you can see, what a large scale perturbation to the system the West African monsoon is, such that it causes this sort of seasonal breathing of the planet in terms of the vegetation in the Sahel region over here. If we imagine we're looking at a cross section south to north through the West African monsoon, this is similar to a plot that we saw on the first talk of the conference, actually. So the monsoon part, if you like, is represented by this deep convective circulation with rainfall underneath. This is fed by air which is coming off the ocean. So it's moist, it's convectively unstable, but also there are things happening further north. So there's a Saharan heat low over this desert region, and then there's this shallower circulation over here at about 10 to a bit more than 15 degrees of. Okay. He knows how to work it. So in contrast to this moist air, which is coming in here, this is very dry air coming in the circulation. So, what can happen is, if you like, the dry air, which is feeding into this convective area, could slow down or inhibit the convection and slow down the circulation. So there's a kind of battle between this moistening and this shallow circulation. So Harry wrote 3 papers during his PhD. The first one has been published in Journal Climate. So in this paper, we just looked at the Hadley Center climate model, HadGEM2, because those are the simulations that we had to hand. So what you're seeing in this picture is, again, this cross-section from the equator to about 30 north, averaged over a few degrees of longitude. This is from ERA and GPCP. So this is the circulation pattern in the vertical that you're seeing, and the blue curve is the precipitation. So this is the broad West African monsoon precipitation in the convective region. This is the HadGen2 version of this circulation, so it's actually pretty good. Precipitation slightly smaller, but the circulation pattern is good. In particular, we get this kind of feeding in of this dry air in the shallow circulation further north, which is, as I mentioned, could be inhibiting the convection in here. So the first question we asked is, what happens if we just increase the CO2? So what we're going to do is split up the problem into of the increases in or the climate change problem into changes in CO2 and changes in sea surface temperatures. So if we just increase the CO2, in this simulation. So this is so-called AMIP, 4 times CO2 minus AMIP. You get an increase in the precipitation and a strengthening of the monsoon and the convective circulation. So why does that occur? So on the left here, so what happens in an AMIP simulation is that the SSTs are fixed to present day values, but the land surface temperatures can actually warm. That's just the kind of way that the model's set up. So if we increase the CO2, we expect to see an increase of the temperature over land. And this is in fact not the surface temperature, but the low, it's the low level atmospheric thickness. So it's a measure of the temperature of the depth of the troposphere or the lower troposphere. So this is actually a shift in the Saharan heat low under climate change. So the West African monsoon precipitation increases in this direct 4 times CO2 experiment because the shallow meridional circulation, which feeds in dry air, weakens. So it feeds in less dry air into the convective column and the monsoon gets a boost. The reason for these changes are associated with this pattern of low-level atmospheric thickness, atmospheric temperature change over North Africa, and you get a kind of northward shift of the Saharan heat low, so it's less effective in affecting in dry air. There's also actually a soil moisture feedback in these experiments kind of later on. So you can start looking at these experiments from the place when they start, and you can see some of the feedbacks develop. Okay, so that was briefly Harry's first paper, direct effect of CO2 causing an increase in West African monsoon rainfall. His second paper was looking at the impact of a uniform ocean warming. So instead of changing the CO2, we instead just warm the SSTs by 4 degrees everywhere over the globe. And we've got experiments with the HADGEM2 model in this case, but also we could look at the CMIP ensemble because this, well, we started bringing in more models into his PhD at this point. So in this case, the uniform 4K warming actually causes a decrease in the West African monsoon rainfall. So why does this happen? So again, you can sort of look a bit in time through the simulations and see how the feedbacks develop. So the initial decrease is caused because if you warm the ocean, instantaneously by 4 degrees, all the convection moves offshore over the ocean. So you get this immediate decrease in convection over the land areas and a reduction in precipitation. Later, then there's actually a further reduction in precipitation because this shallow overturning circulation strengthens. So it starts advecting more dry air into the convective region. That is associated again with this change in the large-scale temperature gradients and also a soil moisture feedback, which we identified. And then finally, there's a further reduction because of changes in the actually 700 millibar specific humidity gradients, the north-south specific humidity gradients. So you imagine that the shallow circulation, it does have some moisture associated with it. So you could change the amount of dry air through a change in both moisture structure and a change in the circulation. So there's a sort of triple whammy here in terms of the processes which cause a reduction in West African monsoon precipitation in the case where there's a uniform warming of SSTs. So in his final paper, we put all these things together to try and look at the why models, rather like Paul Arthur was saying, why models produce these kind of different responses. So this is a rather complex diagram, but mainly these are results from up to this point. So all the columns apart from this last one from just AGCM experiments. So these three symbols, these four symbols here are different models in which we just did the direct radiative effect of CO2. So just quadruple the amount of CO2 instantaneously, and then watch the land warm up. There's also some dots here, which are the AMIP versions of these, so other climate models. And so that's the increase from the direct effect. Here, there's a decrease from the uniform SST warming with these four sets of models and the AMIP simulation. Sorry, there's one bit obscured here. That's my PowerPoint drawing, not anything that we're not trying to cover up. We also have a set of experiments for these four models in which we put in the pattern of SST change from the associated coupled model. In the AMIP simulations, for a AMIP climate change experiment, it's generally put in patterns of SSTs from some average across all the models, but you need to actually pick out, because there's some significant spread in the amount of change, so in fact, in this model, the SST change causes an increase, the pattern change causes an increase in West African monsoon precipitation, whereas this one, it shows a decrease. And then there are various other processes that were separated out in this set of experiments: plant effect, sea ice. There's a sort of non-linearity just done by doing the residual. And then here is the full AGCM experiment with direct effects, uniform SST, pattern SST, and all the other things, showing quite a wide spread. Some models show an increase, some models show a decrease. So there's a balance, if you like, or there's a competition between the direct effect of the CO2 and the uniform warming of sea surface temperatures, which is also modulated by the pattern of SST changes. And if we look here in the final column at the couple models, we see quite a broad spread, as Paul Arthur noted, with some models showing an increase and some models showing a decrease. And we tried our hardest, I can tell you, to work out some sort of emergent constraint based on what we had learned from the various different processes, but we couldn't really find one. So it seems that it's not the case that if you have a strong decrease from a uniform warming and a strong increase from a direct radiative effect, that those things cancel out. Models can have, you can select a model from any of the range here and any of the range here and add them up and get one over here. And with the pattern effect also playing a role. So still some uncertainty that's difficult to constrain, but at least we've understood some of the processes. How much longer have I got? Probably. Oh, okay, right. So, well, I'll just then summarize with this flow diagram that Harry produced. So if we have increasing in CO2, there's more warming over the Sahara compared to the West African monsoon region, a northward shift and a weakening of the shallow meridional circulation, a reduction in the dry air advected from the north into the monsoon rain band at around 700 millibars, hectopascals, and then an increase in the WAM precipitation because of that. And then further a feedback via the surface of increased latent and sensible heat fluxes and a local cooling of the Sahel, which then enhances this gradient. If we've got the uniform SST warming, you get kind of two branches here, an enhanced 700 hectopascal specific humidity gradient, change in the temperature structure, and a strengthening of shallow meridional overturning circulation. Both of these things lead to a decrease in the WAM precipitation through this increased dry air advection into the monsoon. And then another feedback of decreased latent heat and sensible heat fluxes, the local warming in the Sahel region, and then changing, again, the temperature gradients, which affect this shallow meridional overcirculation, shallow meridional overturning circulation. So this shallow cell is the main mechanism, if you like, whereby rainfall is either going up or going down. So in summary, again, the direct effect of CO2 increases the West African monsoon precip. The uniform warming of SSTs decreases the precip, but also the SST pattern is important. Much of the uncertainty associated with the response to the direct radiative effect and uniform SST warming is shown to be related to this 700 hectopascal moisture flux related to the shallow meridional overturning circulation, although it's difficult to predict in the model why that's, how strong that will be. And then there are further feedbacks via the soil moisture and the surface heat fluxes. And the final thing, which I didn't really show, the SSC pattern effect, there's already been a nice study on this by Alessandra Giannini, where she developed a kind of index, and we tested that again in the CMIP models, and that works pretty well as a predictor of changes in precip associated with that part of the change. So thank you.
Thank you, Matt. I think you are very well in time. We have time for 2 or 3 questions.
Should I go first? Oh, thanks. Thanks for that great talk, Matt. I was just thinking back to Paul Arthur's talk, which seemed to be showing that it was differences in the atmospheric models that were giving spread, if I understood correctly. Could that then, how does that tie together with your finding here that changes in the 700 millibar moisture flux divergence are a kind of key quantity here?
Well, I don't know, but it sounds like it could be consistent, right? So if you different atmospheric models giving different changes in circulation patterns, but of course, I suppose they might also have different land surface responses, SST responses. I mean, the land surface response and the SST response is not determined completely by the land surface model and the ocean model. I think the atmosphere model probably also plays a role in those changes as well. So I think, yeah. And it'd probably be interesting to test whether we could get anything out of Paul Arthur's approach.
Hi, Professor Matthew. I understand that the reason for enhancement of the monsoon you're saying is that weakening of the shallow meridional circulation, which could have enhanced the deep meridional circulation over there. So do you assign the most weightage to just this phenomena, or could there be a contribution coming from some other factor in the deep meridional circulation itself, which is actually triggering more convection in that branch and leading to a strengthened motion over there?
Well, I guess that change in the deep convection is changing the surface, changing the soil moisture, which is affecting the surface fluxes and probably the winds as well. So in some way, all these things are coupled together, and it's difficult to say what causes what. Really, often in the case in climate modeling, you're just saying that these things are all consistent with each other, and maybe not to say which one is a trigger and which one is a response. Although we do, in the papers, actually, we analyze some simulations, very short simulations, and analyze the first few days. But even then, actually, things tend to happen simultaneously.
Thank you.
Just a quick question. In the response to CO2 change and the warming, that what you have shown as northward shift in the Sahelian low, is it realistic, and do we see it happening in the 20th century? Because we have warming in 20th century. Is it in observations or even in the IPCC 20th century warming runs?
Anyone know about observations? It's a good question. I don't know. There you go. I need to go and look it up.
Some online questions. So if there are no questions, I have one. There was a paper by Schneider, Tapio Schneider. He was telling that there are shallow overturning circulation in the ocean, which affect the ITCZ movement, especially for West Africa.
Yeah, so I mean, I guess that we haven't looked here into the pattern of SST change.
But you had a coupled run, right? That was also.
Yeah, well, those are just coupled the CMIP models. So we haven't done that. We haven't really looked into the mechanism of the SST pattern change. Although actually, again, that is one of these things which is, been looking at this a lot in the Pacific, and it's very difficult to know what the forcing is and what the response is, because everything is coupled together, particularly over the ocean. So yeah, whether we can actually disentangle that.
Thank you very much, Matt. I think there's a small momentum.
I would like to request the session chair to kindly present the mementos to the speaker.
Yes, can you hear me? Hello.
Can you put it in this slideshow? Yeah, we are able to see your slide.
Already high. Let me try again. Show my slide. And can you see my slide? So can you?
Yeah.
Okay. Thank you. So good morning, everyone. I'm Jian Cao from Nanjing University of Information Science and Technology. Today, I will talk about the long-term changes in northern and southern hemisphere monsoons since 1900. So as you know, the global monsoon brings a lot of precipitation over the most people dense region, cause a lot of social and economic impact. Under the external forcing and the internal dynamics, the global monsoon has probably variability across different time scale from internal, decadal, centennial to even longer orbit time scale. If you look at the proxy data, it shows the past 21,000 years, there's a increase and a decrease of monsoon rainfall for the East Asia monsoon region. If you look at the Southern Hemisphere, the South American monsoon region, there's a opposite or out of phase change of the regional monsoon between Southern Hemisphere and the Northern Hemisphere. So the simulation shows similar feature if you look at the millennial timescale. There is out of phase change of Northern Hemisphere and the Southern Hemisphere monsoon precipitation. And over the regional monsoons in one hemisphere, there are coherent changes. But if you look more closely, there's in-phase change during the past 1,000 years on multi-centennial timescale. There's increase and decrease and increase Northern Hemisphere and the Southern Hemisphere monsoon precipitation. This is associated with the change of global mean surface temperature. So everyone knows the future change. The future change tells us the projected change of North Africa and the Asian monsoon is enhanced. However, over the Southern Hemisphere, there's a lot of spatial distribution. The increase of the relationship between Northern Hemisphere and the Southern Hemisphere monsoons is not very clear. So when we look at the past 1 century, the observation shows if you look at from 1950 to until the end of 2000s, the observation shows a decrease of monsoon rainfall. So look at the model, the simulation tells you there's a decrease of monsoon rainfall in the simulation. It's mostly due to the asymmetric axial forcing. In the CMIP models, there is a decrease of monsoon, global land monsoon precipitation, and this is much dominated by the northern hemisphere, because in the southern hemisphere, some studies shows there's enhanced or increased southern hemisphere monsoon precipitation. Thus, under the global warming during the past 1 century, the changes in southern hemisphere and the northern hemisphere monsoon is quite different. So why is not? So our question is, why the northern hemisphere monsoon precipitation weakened during the 1900 to 2014, but the southern hemisphere monsoon precipitation increased? So why does the isoforcing can dominate the declining of northern hemisphere land monsoon precipitation, although its impact on radial forcing and the global mean sea temperature is much less than greenhouse gases? So which mechanisms are responsible for the increase of southern hemisphere monsoon precipitation? We use the observation data of surface temperature from the hardware CRU, the precipitation from the GPCC, CRU, and UDAIR. You use the 3 data mean as the IPCC report. We also use the circulation data from the 4 reanalysis data. The monsoon domain is defined by the summer minus winter, exceed 2.5 millimeter per day, and the summer precipitation accounts for about at least 55% of the annual total. This is the global monsoon domain. So first, under the simulations, we use the 38 simulations of historical simulation from CMF 6, and the 14 models provided a single force experiment. That means from the DA-MIP, the greenhouse gases can increase the global mean surface temperature by 1.2 degrees in the last 30 years, and however, the aerosol only decreased the global mean surface temperature by 0.6. So if you look at the northern hemisphere, the observation shows there's a decrease of northern hemisphere land monsoon precipitation by 0.15 millimeter per day per century, and this is well produced by the climate models, especially the 14 DME shows the similar magnitude of change. So once we look at the different external forcing, the isoforce shows a large decrease, minus 0.27, and the greenhouse gases can increase 0.1 millimeter per day per century. That means the iso dominated the decline of northern hemisphere monsoon precipitation. So further, we look at the 1 degree change for the precipitation change. So this is for 1 dot indicate the decadal mean. This figure shows for 1 degree change, the ISO can change the northern hemisphere monsoon precipitation by 0.6 millimeters per day, but the greenhouse gases only affect 0.12 millimeters per day. And we calculate the hydrological sensitivity. It shows 11% per K from the aerosols. It is about 5 times of greenhouse gases. This is a large difference, and that means the aerosol is more effective changing the northern hemisphere monsoon. So why is not? We use the moisture budget analysis. It shows the contribution from the evaporation, the moisture effect, and the dynamic effect from the monsoon circulation change. As you know, under the greenhouse gas forcing, there is marginal change in the evaporation, and the thermodynamic increase of or positive contributor from the thermodynamic effect is partially cancelled by the dynamic effect. In terms of aerosol forcing, the precipitation change is the amplification among the evaporation, thermodynamic, and the dynamic effect. That means those evaporation, thermodynamic, and dynamic change in line with the temperature, not amplified the precipitation. So why is not? The key is the evaporation and the dynamic effect. First of all, we look at the evaporation. In the monsoon region, the surface evaporation is more constrained by the available energy for evaporation. So we look at the net surface irradiance from aerosol and the greenhouse gases. It shows over the monsoon region, the net surface irradiance is much larger on the aerosol forces than the greenhouse gases forces, about 5 or 6 times. And the large change of surface irradiance is due to the aerosol radiation and aerosol cloud interaction can affect the downward solar radiation, as shown in this figure. But the greenhouse gases is more effective to change the downward radiation or the short radiation. So the aerosol is more effective to change the precipitation from the evaporation. And secondly, we look at the dynamic effect. As shown here is the global mean surface temperature scale of the changes. We can see the surface irradiance change has large inter-hemisphere contrast. It causes a large contrast between hemisphere in terms of temperature and the SLP. It drives the lower boundary moisture transport from the southern hemisphere to the northern hemisphere for 1 degree for global mean surface temperature change, and cause moisture convergence and ascending motion effective at changing the precipitation over the Los Angeles monsoon region. In terms of the greenhouse gases, it is less effective compared to the aerosol force as the change of atmosphere stability will dominate the dynamic effect in terms of greenhouse gases. So if we further quantify the impact from different index thermodynamic, the cause of the dynamic effect, it is the inter-hemisphere temperature difference, the non-seasonal contrast, the cross-equatorial moisture transport or cross-equatorial flow, and the vertical zonal wind shear. So those indexes are also all shows the aerosols are more effective changing the monsoon circulation than the greenhouse gases, and the greenhouse gases is marginal change. So in this case, the aerosols can more effective changing the Northern Hemisphere monsoon. So next we talk about the Southern Hemisphere monsoon. If you look at the observation, it shows a increased trend during the historical period, and this is much because the increased rainfall from the Australian and the South American monsoon region. So this feature is can be reproduced by the analysis data, although the magnitude is much larger than the observation. And the spatial pattern shows the NOAA 23 is more close to the observation, although the tube analysis has bias, significant bias over the South American monsoon region. So we focus on the NOAA 23 to look at the possible physical mechanism. We calculate the leading trend of the precipitation and the contribution from evaporation, thermodynamic and dynamic effect. It shows the dynamic effect is the largest contributor to the precipitation increase, and the spatial pattern is of precipitation is consistent with the circulation change. So that means the circulation change is the key for the increase of monsoon rainfall over the Southern Hemisphere. And then we look at the circulation change. So the SLT pattern tells you there is a zonal SLT contrast. There's relatively less warming or cooling over the Central Eastern Pacific, and there's large warming over Indo-Pacific region. So because the zonal SLT gradient drives the low-level circulation, there is easterly from over the Western Pacific and westerly from the Indian Ocean. This moisture convergence can enhance the local circulation, not increase the monsoon rainfall over the Australian monsoon. And this circulation change can also increase the South American monsoon precipitation. So this is from the observation. And we calculate the regional monsoon index. It all shows the circulation is enhanced, as indicated by the monsoon circulation index. And also the subtropical high is enhanced. That means the circulation can transfer more moisture from the tropical ocean to the monsoon region in the observation. And what happened in the simulation? So this is the leading trend of the southern land monsoon precipitation from CMF6 models. So some of the models can produce a wetland trend, some of it is drying. So you use the 4 models of wet models it is consistent with the observation. The dry models is pretty dry. So we calculate the difference between wet and dry models. It shows the wet models can help to produce the weighting of Southern Hemisphere monsoon precipitation over individual monsoon region. And the physical mechanism is very consistent with not from the observation. It shows a relatively less warming over the Central Eastern Pacific and a relatively large warming over the Indo-Pacific region. So this can enhance the moisture convergence and also the ascending motion over the Indo-Pacific region, and the upper troposphere diverges over the Indo-Pacific, and this will cause an increase. The zonal circulation change can cause the increase of monsoon precipitation over the regional Southern Hemisphere monsoon regions. And while there is a zonal acidity gradient, we calculate the acidity gradient from Indo-Pacific minus the Eastern Pacific, and it shows there is a enhanced acidity gradient in the observation, although it has much internal variability. So this acidity gradient is driven by external force or internal variability. So we look at if you look at the CMF6 ensemble mean, there is
Professor John, just 2 minutes.
Okay,
Just only 2
this
minutes.
Okay, thank you. It's quite different from the observation because the CMF6 model tells you a needle neck warming is different from the observation. And if you look at the probability from the internal mode, we look at the pre-industry from the CSN model, it shows sometimes the model can produce the enhanced acid gradient associated with the monsoon precipitation increase. The 1200 years simulation tells there's a close association between the enlarged acidic gradient and monsoon precipitation. That means this acidic gradient is made from the internal variability. So here give a short summary is the observational data set shows the decrease in North Hemisphere land monsoon during the 1900 to 2014, and the South Hemisphere monsoon precipitation is increased during the same period. CMF6 model will produce the decrease in North Hemisphere monsoons, while the models underestimate the observed South Hemisphere monsoon trend. So in terms of the mechanism for this North Hemisphere, the also dominated the decline of North Hemisphere land monsoon precipitation, and the ISO is 5 times as the greenhouse gases in terms of monsoon precipitation change. This is because the ISO is more effective decrease the surface irradiance for evaporation, and is more effective alerting the surface temperature gradient as the monsoon circulation. It causes more effective change of monsoon precipitation than the greenhouse gases. For the Southern Hemisphere, the zonal acidic gradient drives the local circulation, which will distribute the moisture from the tropical ocean to the monsoon region. And this acidic gradient in the observation may not fully caused by the expository forcing. Natural variability is also one of possibility. Okay, that's all my talk. Thank you.
Yeah, thank you, Professor John. I think we are really running behind time. There are some questions online, chat questions. You can respond to them.
Okay.
Yeah, so we will not be able to take any questions here. Thank you very much.
Thank you.
So there's a last talk, online talk. Do we finish it or do we come back? Okay. We have the last. Ashok?
Hi, Krish.
Hello, Ashok. Yeah.
Hope you don't keep me through the lunch here. Hello?
No, we have
Okay,
to start.
let me start. Is it
We are
okay?
already late. Yeah, please can you?
Yeah, let's try to do it quick. Basically, this is the work that we have been doing. Are you able to see our slides?
No, not yet.
Okay. So I have to share the screen. Yeah. Are you able to see the screen?
No. Yeah, now it's there. Yeah, please. Ashok, I will give a warning, 12 minutes.
Yeah. So basically, this is the paleo monsoon work we have initiated in University of Hyderabad since 2016 or so. Mainly the work by Charan Tejawat, who is a scientist now in NSS, and to some extent Vidya. These are our collaborators, including Supriyo. Understanding past climate is as important as the future, particularly the last 1,000 years, because there have been epochs, or there has been periods where continental scale warming as high as first half of the 20th century has been recorded. Paleo data show you very good signals, and a lot of the things that you see during what has been experienced has relevance for the future. With that, so basically, one is what was the rainfall condition over India? It was warm and wet, as the proxies indicate. So we wanted to see what was the circulation associated? What are the factors that change this medieval warm period to little ices? There have been two, if you call major time sub-periods of this last millennium. One is the medieval warm period, or what you call as little ice age during this medieval warm period. In the beginning, the 850 to 950 AD to up to 1200. Depends on the observations and model, there is a slight shift. And then the very recent little ice age just before the historical period. So these are the periods when globe proxy observations tell you it was very warm during this period, as I told you, in the last millennium. And then there is this little ice age. And these are some of the questions that we have been trying to answer. And prior to this, there is mid-Holocene, which also attracted a lot of attention, and El Niños were weak during that time. So how was the monsoon during that time? So then Indian Ocean Dipole. With that introduction, I'll try to rush. We chose the models, several PMIP models, which simulated whatever we saw from the proxy observations, medieval warm period, warming and cooling in little ices, and historical monsoon simulation statistics were reasonably well. All these models, needless to say, you can validate only based on the historical analysis, then some comparison with proxy, but historical simulation validation, CMIC 5 is the key. So not only over the globe, but over India too, all the models tell you that medieval warm period was warm and little ices, it was cool. When you compare, when you remove the anomalies, when you remove the last millennium mean, 1,000 years, this is the condition you see. And interestingly, you have a lot of noise in the rainfall, but if you take the long-term trend, out of these 10 models that we selected, 4 models have significantly reducing some summer monsoon rainfall when you area average over India. And 4 models, another 4 to 5 models indicate that the trend is still there, but they're not statistically significant. Qualitatively, all the models have been indicating a decreasing rainfall from medieval warm period to little ice age. So is it because of some sort of El Niños and La Niñas that have played a role here? Then when you see the model correlations in certain monsoon, actually the models do a fantastic job for historical period. As far as the correlation is concerned, you get this minus 0.4 for historical period. And interestingly, for both medieval warm period and little ices, the correlations did not change much. A few models, 1 or 2 models have poor correlation, weaker correlations, but there's not much difference between medieval warm period and little ices. So despite the skewness or whatever there may have been there, but there was no change in the intra-annual relationship, which sort of reflected in your centennial scale. So what may have happened? So one key that we get is the centennial background changes in the Walker circulation. If you see the tropical Indo-Pacific, actually during medieval warm period, when compared to the long-term mean, you had anomalous convergence on a centennial scale. This is not like a Modoki type of thing. You're looking at a multi-centennial scale. And then you have a convergence, anomalous convergence in the eastern, in the equatorial Indian Ocean. This resulted in anomalous convergence over India. So what happened was whenever there was an El Nino, this background signature was opposite to your intra-annual signal and sort of reduced the El Nino effects. So thereby, so it was more than the background signature. One reason is this stronger Walker circulation contribution. So the opposite happened in little, what you call as little ice age. So relatively dry conditions. Is that only the potential factor? No. So we were looking at some other aspect. We started with this northeastern summer monsoon during medieval warm period. How was the signal? Because we don't see as much trend in, no trend. In fact, if we see some of our, whatever we analyzed in our paper in 2018, there is hardly any big trends subject to what our data qualities. Then there is no ENSO correlation with northeast summer monsoon rainfall, very poor correlation. Then you don't have much relationship with the central Indian rainfall and northeast monsoon, almost no correlation, and there is no same phase. Some papers, in fact, say they're out of phase, if you see some of the old papers. So there is not much relationship between summer monsoon elsewhere and northeastern summer monsoon. So how was it on these long time scales? So let's see. When we took only 3 high resolution models because there has to be good resolution and some ECMWF data. ECAM model. Anyway, these 3 PMIP models that I'm going to focus, all of them tell you this. Little ice rainfall is much less than medieval warm period, or people call it as MCA, medieval climate anomaly. So all these 3 models are showing more rainfall during medieval warm period over India. But the northeast monsoon, there is not much difference. Actually, they're almost similar. So then El Nino, we understand not much impact from Pacific, so it may not have affected. But there was another factor. What we see in this study is what we found was the easterly jet stream actually has strengthened during medieval warm period. It was very strong as compared to the long-term mean as well as LIA. And all 3 models are indicating the strong tropical easterly jet, or where it plays a big role in the southern peninsula. But over northeast India, the changes are much less. So what it does tell you is one reason that medieval warm period was warm and wet over India, wet was because of the strengthening of tropical easterly jet also. However, over northeast India, the impact, there is no, there is sort of what you call as, there is no big centennial variability. However, unlike rest of the India, where the medieval warm period wetness matches much with the proxy observations, or northeast India, still there is a question, because even within proxy observations, there is sort of some uncertainty. And this probably the models and observations are not reconciled so well. This needs to further examination using models as well as improving the proxy observational studies collections. So then we go to Holocene, mid-Holocene, when El Nino was not there. How was the monsoon during that time? There was some proxy studies tell you that mid-Holocene, early Holocene had a lot of good rainfall over Indian region, and solar insolation has played a role. So we did our own experiments with CAM5, and also we analyzed PMIP3 models. So I'll quickly go through the results instead of explaining the model detail experiment sensitivity. These are the standard 30-year sensitivity experiments were made by changing the orbital parameters, because there were observational studies that suggest orbital parameters may have played a role, solar radiation and changes in perihelion and eccentricity, etc., etc. So PMIP gives you all the data values, so you can force your model with these parameters. So this black line tells you is your rainfall that we got in medieval mid-Holocene areas, summer monsoon rainfall, which is much higher than, of course, these are all being compared with the historical simulation rainfall. So for medieval warm period and little ices, the rainfall was much less than what you call as mid-Holocene. This tells you that mid-Holocene temperatures, so rainfall was wet, or it was anomalously positive, and temperatures were relatively cooler during monsoon time. What may have happened? Our simulations tell you, when you compare it with historical simulations, you see a low pressure. So this fits with the strengthening of the monsoon here. This is what it's all about. Then we made some sensitivity experiments by changing orbital parameters and prescribing orbital parameters that are more relevant to HS, historical and medieval warm period, etc. All of these tell you that the orbital parameters played a big role, and that they were the factors all those parameters played a role in wet Indian conditions during that period. And LGM, when we think that there is a less rainfall, the model seems to be doing reasonably well, last glacial maximum. So this is the summary of this mid-Holocene thing. And El Niños per se were weak during that time, and model was not responding. One issue with this model was its response, be it El Niño or La Niña, very poor response and same sign. But this tells you that, at least the studies tell you that orbital parameters played a decisively important role. You can see the some results. And also there was this 8.2 kilo year period. This is earlier than mid-Holocene. When we say mid-Holocene, about minus 6,000 K and 6,000 years. And prior to that, to 8.2 K year BP also, the model captures well. It was wetter than mid-Holocene. And when compared to, on the other hand, if you use LGM orbital parameters, you get a deficit rainfall most of India, and historical to relative to the mid-Holocene, historical rainfall was much less. So
2 minutes.
Okay. Finally, so centennial variations in easterly jet stream as well as Walker circulation played an important role. And mid-Holocene, we had a very good rainfall. All these things are supported by the our model studies. Finally, people have studied ENSO from this PMIP studies, but in 2024, we wrote this small paper. What about IOD? Because there was this paper by Abrams group that you had more positive dipole events in the last LIA. So we were checking this aspect, and we did, of course, we used EOF analysis to identify the good models, and what we see is in medieval warm period, actually the models simulate IOD as EOF mode 1, whereas little ice is, as usual, it's EOF 2. So there is this centennial background difference. If you take the SST differences, medieval warm period was warmer than total 1,000 years, last 1,000 years, whereas little ices, the right side shows you that little ices was cooler, the Indian Ocean was cooler than the 1,000-year mean. Then there's a lot of information. I'll just, because of the lack of time, I'll quickly share some points. We had more positive IOD events in the simulated world during the medieval warm period, and more negative IOD events during the Little Ice Age. However, but Abram and all, only one single proxy study tells you that more positive IOD events during LIA. While the model simulates more negative IOD events, what we see is as the model is coming towards the end of the last millennium, not one model actually, several models, MME, it tells you that more stronger positive IOD events started developing as compared to negative IOD events. More strong positive IOD events, but total number of events, negative IOD events were more. So this begs a question, what happened? So what we find is, for the positive IOD events, actually the coupling strength increased from medieval warm period to Little Ice Age, whereas for negative IOD events, coupling strengths, Bjerknes feedback strengths, etc., didn't change. So on interannual timescales, for whatever reason it is, you see more and more strong positive coupling intensification for positive IOD events, which led to stronger IOD events. And one question you may have is, what about ENSO monsoon correlations? Yes, that 34% of the 36 to 37% of the IOD events were associated with the El Niños in the model world. With that, I complete my presentation of this part. The models do some good work, like, the match that the frequency of strong positive IOD events is 2.5 times more than negative events, which is matching with the observations. And at least in the last part of the last millennium, Little Ice Age, the models seem to capture the strengthening positive IOD events. So we need more observations and more model simulations.
Yeah. Thank you, Ashok.
Our summary. Sorry, I may have rushed through because of the lack of time. You can refer to these papers, and we were funded by DST and MOAS, and we thank IITM also for some HPC facilities. Thank you.
Thank you, Ashok. Maybe because of lack of time.
Yeah. Hello?
Hello. Due to lack of time, be able to take any questions.
Sure. Okay.
If there are any questions online, they'll be submitted.
Yeah.
And you can respond.
Sure.
Thank you, Ashok. And thank you.
Thanks. Bye.
So we come to the end of the. Now we have to go for the lunch break, and we are already half an hour late.
Yeah. Thank you, sir. Here we come to the end of the talk of the session 9. Now I'd like to thank session chair for chairing the session. And we will disperse for lunch break arranged at guest house in basement of this building. And we will resume the next session by 2 p.m. Thank you.
And also, there is an announcement. A participant has lost his mobile phone, Redmi phone, near the washroom area. If anybody locate that phone, please let us know. Thank you. Yeah, I think we found it. Thank you.
Sharon?
Check. Hello. Hello.
Hi.
Can you hear me?
Yes.
Yeah. Do you want to check the share screen, right?
Yes. If you can try the sharing screen. Thank you. I will try.
Okay, Annalisa, please share your screen and I'll confirm.
Okay. Have you seen the slides?
Yes. Make it full screen.
Is it working?
It's showing only in presentation mode, not in full screen. Not in full screen mode. And presentation
in
mode.
full screen. Is now full screen?
Yes, yes. Now it's full screen.
Okay.
Yeah, keep remember this setting.
Okay.
Yeah.
Thank you.
Yeah, thank you. Yeah.
काय माईक म्यूट आहे म्यूट आहे
Dr. Eleanor?
Hello.
Yeah, hello. Do you want to check the share screen or something? Yeah, yeah, yeah. It's visible full screen. Thank you. Yeah. Yeah, it's the lunch hour, so the session will be resumed after half an hour. Yeah. Hello.
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 Mm. Actually, those who didn't submit the presentation, please submit as soon as possible. Like two of them, Shivan C and Hiltrina didn't submit your presentation. Please submit it as soon as possible. Thank you.
Hi, how do we submit it? I thought we would just share our slides.
Yeah, you can mail it.
Okay.
Yeah.
But will we still do our own slides and
Sorry?
will we present our own slides?
You can send the slide to our mail, or you can send the PDF also if there is no animation.
Eleanor's question is, are the online presenters, are they clicking between their own slides, or are we telling you to click to move to the next slide?
If you're sending the slide, yeah, we can do. Otherwise, you can do that. It's fine.
Okay.
Yeah.
Thank you. I think, yes, I will launch my slides from here so that I can click myself. Thank you.
Definitely. Yeah. Yes, sir.
Yeah, I'll do that. Thank you.
Yeah. Can you please send it as soon as possible? Then we'll start the session.
You ready for me to share my slides now? Is that, you ready to start?
Wait a minute, sir. We have to invite the chair. Then,
okay.
yeah. Yeah. 2 minutes. Ms. Helena, if you are doing it online, actually you can do the slides from your side.
Thanks. Yeah.
Okay? Yeah, that would be fine. So good afternoon, everyone. Welcome to our afternoon session on monsoon in changing climate. I am pleased to invite retired Air Vice Marshal Ajit Tyagi to chair this session. IWM Ajit Tyagi is a distinguished meteorologist with several prestigious roles, including Quotidian Professor, former DG of the IMD, and Assistant Chief of Air Staff Meteorology. His contributions to meteorology and climate science have been invaluable, and we are honored to have him lead this session. Sir, the floor is yours. Thank you.
Thank you, and welcome after a sumptuous lunch. And I'm seeing that fairly good attendance. Normally people post-lunch is difficult to find them in the audience. So thank you so much for joining this. As brought out, it is the third session on climate change and monsoons. It shows the importance of monsoon for 2/3 of the global population, and also we really don't know everything about monsoon, and climate change is going to make it further difficult. And therefore, it is very important that we focus on the research part to understand the impacts of the climate change on monsoons and how does it affects various sectors, like agriculture, energy, water, more. So this is what is going to be from the research to the services part, which is the ultimate purpose of any climate or weather service. So with these opening remarks, I'm happy to be part of this important event, IWM8, and India has a lot of role to play in promoting this monsoon research. In fact, this is the third international workshop on monsoons in India. Even the IWM7 was held here at IITM. And let me compliment Dr. Krishnan and Dr. Raj Gopal for planning and organizing this workshop. So in hybrid mode, 3 or 4 will be online and remaining 2 may be physically being here. So let's start with first presentation by Andrew Turner. Its impact of the monsoons on global and the regional monsoons, impact of climate change. Andy Turner, thank you and welcome.
Hello, thank you very much.
Yeah, we are missing you, but then in hybrid mode, we are making use of your.
Thank you. I'm very, very sorry that I can't be there in person. I have a lot of teaching duties at the moment that have sort of taken over my life for this short time. So I would love to be there and be having fun with you all. So I'm gonna kind of give an overview of the results of climate change in the IPCC 6th assessment report, which is prescient because we're moving towards the 7th assessment report period. And just to sort of motivate you, I think Akshay showed this picture in his slide as well, but this is a really nice image, a merged image that captures the true impact of the monsoon on society, and it's from a village near Hyderabad, and you can see the difference between periods of no rain and abundant rains. So you know, this underlines the importance of the monsoon, which of course you all know. So the work of the monsoons in the IPCC, and of course the whole IPCC report was a team effort. A huge number of authors, about 180 authors for the physical science basis, and probably around about 12 to 15 of those people were actively involved in working on monsoons. And hopefully in this audience, this is from the IPCC meeting in Toulouse. You can see Krishnan in the front row here. I think Tianzhen Zhao has already spoken as well at this meeting, and I'm somewhere in this picture. I'm not going to show you where. And Annalisa, who's speaking a bit later this afternoon, is also in this audience. So just to say a little bit about how the monsoon information is organized within the 6th assessment report. Of course, we have at first the summary for policymakers and technical summary, which really synthesize a lot of the information. But then the real science start getting into that in chapters 2, 3, and 4, which deal with global aspects of the climate system. So the global monsoon is covered in those chapters. And that goes through chapter 2, the observations, how the climate is changing. Chapter 3, trying to attribute those changes. And then chapter 4, looking at the future projections in modeling studies. And then the real detailed information about the regional monsoons is in chapter 8 on the water cycle. And then myself, I was involved as an author of chapter 10, which is linking global to regional climate change. And we look at the methods of how you get and aggregate all of this global and regional climate information and talk and bring out regional climate messages that societies can use. And then, of course, there's chapters on extremes. And one really major feature about the AR6 was the regional interactive atlas, which I very much urge you to go and play with if you've not done so already. Annalisa and I led an annex on monsoons. So this was just talking about definitions and so on. How do we define monsoons? But then a reminder that the detailed information at the regional level of monsoons falls in chapter 8. So looking first at the global monsoon picture and the attribution of global monsoon changes in chapter 3, firstly to say that, of course, we need to look at how the models simulate the monsoon domain. And we've got some observations on the left and the CMIP multi-model mean on the right. And the red line is showing the monsoon domain using a particular index of summer minus winter rainfall. And you can see that actually the CMIP6 models are doing a reasonable job of getting where that monsoon domain is. So what do they do over the course of the 20th century, over the historical period? There's a decline in global monsoon precipitation from the 1950s to the 1980s, followed by a recovery. And that happens both in models and observations. There's also a similar decline and recovery if you take a measure of the whole Northern Hemisphere monsoon circulation. But what about attribution of the regional monsoons, which took place in chapter 8? So what you can see here is all of the different monsoon domains, and they've been split up into the different regions. And then we're looking at single forcing experiments in the 20th century. And what you can see is that some monsoons feature opposing behavior in the 20th century under greenhouse gas and anthropogenic aerosol conditions. So notably South Asia, East Asia, and Australia and the maritime continent. So you can see here that there's a tendency for wetter monsoon in the greenhouse gas only experiment, the red one, and a tendency for a drier monsoon in the anthropogenic aerosol experiment. That's the kind of green colored one. And so it's possible to come up with some attribution statements for changes to the regional monsoons across the 20th century. And I'll just go through two of them here just for time. For South Asia, it weakened in the second half of the 20th century. And this was blamed on anthropogenic aerosols, which was opposing the expected increase due to greenhouse gases. In East Asia, China, it's a little bit more complicated with a drying north and a wetting south since the 1950s. And generally, we think about that as a retreat of the monsoon circulation southwards. So that's been attributed to anthropogenic forcing, as well as the positive phase of decadal variability in the Pacific Ocean, which have helped drive that weakening, especially since the 1970s. Another key line of evidence that we need to take into account when thinking about monsoon climate change and any regional climate change is also what's happened in lots of other types of evidence. So in the paleoclimate information, we have evidence from the past, good evidence, that in warmer periods of the past with similar heightened CO2 forcing, the Northern Hemisphere monsoons were stronger, including in South Asia. So looking to the future now, and first of all to the near-term future, so out to the 2020s to 2040 period, what you can see on these maps at the bottom, if we just focus on the Northern Hemisphere summer, is that there do seem to be slight increases in rainfall in the summer in the near term. And that's both in the SSP1 scenario and the SSP3 scenario, which is a slightly stronger forcing. But really what's happening is that those changes are overcome by model uncertainty and internal variability. So there are evidence of positive changes, but really there's no robust significant change statistically. It's a different message when we look at the long term, however. So if we look at the long term for the future global monsoon rainfall, and that's shown in this figure here, we can see that as we go out to the end of the 21st century, the scenarios are all showing increases in monsoon rainfall. And that rainfall increases with time, and it also increases with the strength of the emissions scenario. So that's really quite a robust signal of future climate change. And the IPCC report says it's likely that global land monsoon precipitation will increase with the rise in global surface air temperature, and that's despite a weakened monsoon circulation in the future. So the thermodynamic aspects are winning out. We're getting more rainfall in the future. But what happens at the regional level? So chapter 8 looked into that, and all of the different monsoon regions are shown in this diagram here. And there's a couple of little different ways of looking at the information here. One of them is from left to right for each color. We're looking at the near term, the medium term, and the long term being the end of the 21st century. And then the three different colors are just showing the different emission scenarios from weakest to strongest. So what you can see here is that there are robust and consistent increases in various regional monsoons when under stronger emission scenarios and further into the future. And this is particularly clear in South Asia, East Asia, and West Africa. However, there are some regions, monsoon regions around the world, that have considerable uncertainty, especially the American monsoons. And you can see here that their box and whisker diagrams are very much hovering around the zero line. So there's a lot of work to do still to understand how these monsoons will change in the future. So just jumping out of IPCC for a moment, I'm a big fan of this diagram that was produced in a paper by Anja Katzenberger in 2021. And this looks at how Indian monsoon rainfall is changing with degrees of global warming. And indeed, it's a key message of the IPCC report for many different climate impacts around the world that those impacts get stronger and worse with each fraction of a degree of warming. And that's true for the overall Indian monsoon rainfall in the future as well. So she's taken here the CMIP6 database and looked at different times across all of the integrations out into the future in the different emission scenarios, the different ensemble members. They're all plotted on this diagram here. And then when you take the mean of each of the emission scenarios in that diagram, you get the version on the right. And you see this very clear relationship between the amount of change of global mean temperature and the increase in the number of millimeters per day of monsoon rainfall out into the future. So that's an extremely nice result. And Annalisa will talk a bit more in detail about this in a few talks' time. So the technical summary is an excellent way of just diving in to find out quick messages about what the report says about the monsoons. And in fact, it has a two-page box on the monsoons where it gives you all of the information. So its main summary is that the combination of greenhouse gases and anthropogenic aerosol forcing are fundamental to driving changes in the global and regional monsoons. But internal variability also plays a role. And I'm going to talk about that a little bit more in a moment. I'll skip over that slide. So a couple of other things we do need to think about when we're thinking about warming scenarios for the monsoons and other aspects of the climate system is the possibility of low likelihood, high impact events. One of the key ones that scientists are worried about is a spin down or collapse of the Atlantic meridional overturning circulation, the AMOC. There's medium confidence that there won't be a collapse before the end of the century. But if such a collapse were to occur, it would very likely cause weakening of the African and Asian monsoons and strengthening of the Southern Hemisphere monsoons. So even though this is a very long way away from India, it is still absolutely vital that science is done to understand some of these major problems of the global circulation. The other thing that we thought about in the IPCC report is the effect of supervolcanic eruptions. And we had something called a cross-chapter box on volcanoes. And we studied the evidence for monsoons and came out with this statement here. It is likely that at least one large eruption will occur during the 21st century. And such an eruption would reduce the global temperature for several years, decrease global mean land precipitation, and alter the monsoon circulation. And it's actually a little bit tricky to understand or give a definitive message of what that will do to the monsoon rainfall, because it very much depends at which latitude such an eruption were to occur. But read that box if you're wanting more information. So what other things have I not talked about here? And I'm not going to talk about them in more detail either. Intensification of the water cycle. This is something we've known about for years. So in other words, when it's raining, it's raining more heavily. And perhaps when it's dry, we've got longer dry spells. Heat waves are also incredibly important for some monsoon countries such as India, especially in the pre-monsoon. And of course, what society, what stakeholders, what farmers really feel is the effect of the intra-seasonal variability. And there's still, I think, a huge number of open questions in what's going to happen to the MJO, the BSISO, the monsoon intra-seasonal oscillation, and how that will change in the future and how that might affect monsoon rainfall in the future. So to end the talk, I want to talk about, I would say, 3 different major areas of uncertainty that I think still need a fair bit of work looking to the future. So the first of these I've mentioned is the internal variability, or really thinking about the interplay between that internal variability and forced change due to greenhouse gases or aerosols, etc. And we can look at this a whole lot better than we used to be able to, because there's large ensembles available now. And so you can try and gauge how big that internal variability is to the forced signal. So one such example was this in this paper by Chinese colleagues, by Huang et al. And what she did, she took a 100-member ensemble of the MPI model in the historical period and in the RCP 8.5 future, so strong warming future. And just to go to the key message, when she looked at the Indian monsoon rainfall into the near term, you can see a couple of different things happening. So if she selects in that model the 10 members that seem to give the wettest trend for the monsoon into the future, that's the blue line here, you get an enhancement of the climate change signal. But if she selects the 10 members of that ensemble that give the strongest drying trend, she gets this brown curve here, which says that you're actually getting less rainfall in the future than you expect. So out to the near term, understanding the role of internal variability is going to be very important. Another major uncertainty is that of aerosol changes. And again, this is especially important in the near term. We think we're at a point around about now in which the greenhouse gas signals are starting to dominate over aerosol signals in driving what monsoons are doing at the moment. And there's some argument that they're starting to lead to a recovery of monsoon rainfall. But there's a hugely uncertain future about what air quality policies will be in the future. So, for example, the different SSPs 1, 2, and 3 of the IPCC scenarios show different pathways for what black carbon in this row here and sulfate emissions in this row here will do in the future. And you can see that with strong air quality policies all around the world, both India and China, for example, have strong reductions in black carbon and sulfates. But in different SSPs with a mixture of air quality policies, you might get a different thing. And you might, in fact, get a dipole where China is reducing its emissions, but India is increasing its emissions. And the authors of this paper, so Bjorn Samset and one of my colleagues, Laura Wilcox, they looked at what was happening in the recent observations. And this paper's from a few years ago. It's before the global pandemic. But at that time, they looked at the trend over the 2010s and found that China was reducing emissions, whereas India's emissions were continuing to increase. And we know from our research on aerosol modeling that these things will affect monsoon rainfall in the future. I think by the time we get to the end of the 21st century, it's not something we're not going to need to contend with, because air quality policies will have been put in place globally, which can mitigate the effects of aerosol on the water cycle. And Laura is leading something called the Regional Aerosol MIP, and that data should be available for analysis, in which they're testing the impacts of changing aerosol emissions from lots of different regions on the globe. Another major thing is the persistence of GCM biases. And although the models are reproducing reasonably well the domain and precipitation of monsoons when taken in the mean, there are actually some long-standing biases that haven't gone away over generations of models. So this is a nice figure from a paper by Bock et al. in JGR, and it's firstly, it is showing the annual mean, so I appreciate it's not the monsoon season mean, but generally it gives you the same message. At the top here, we're looking at the CMIP6, on the left the mean, and on the right the bias against observations. And what you can see for the Asian monsoon region is this very familiar pattern of a very strong dry bias over India and a wet bias over the western equatorial Indian Ocean. And more globally, this is represented as a southward bias in the ITCZ. But then if you go back 10 years and you look at the CMIP5 models, you get largely the same results. And if you go back another 10 years and look at the CMIP3 models, again, you get largely the same results. And so there's been some small changes there. You know, there's been improvements to parameterizations and increases in resolution, but it hasn't solved the fundamental problem that there's this very large biases in our projections of the tropical water cycle that we need to properly address in order to have more confidence in our future climate projections. And then we might say, okay, well, we just increase the resolution and that might solve things. But the bottom diagram also shows the results of the high-res MIP experiments. So on the right, comparing the traditional CMIP class resolutions of maybe 100 kilometers resolution. And on the left, we're showing the high-res MIP high-res models. So these are perhaps looking at maybe 30-kilometer resolutions. And you can see that fundamentally that bias in the monsoon rainfall is still the same. So at these parameterized scales, just increasing the resolution is not solving the problem. So just a quick summary now, and thanks for your attention. Monsoons are changing in complex ways. The future projections of increased rainfall for the global and Asian monsoon scale proportional to the level of global warming. In the near term, internal variability is likely to dominate. But for the Asian monsoons, it's clear that aerosol pathways are also important. Model biases are a long-standing issue, and considering multiple lines of evidence, so observations, theory, global models, regional models, paleoclimate information, that's all important to adding confidence to the messages for regional climate change. And just very quickly, I just want to look towards the IPCC 7th assessment report, for which the call for authors is now out. And just to think about some potential topics of perhaps greater emphasis in the 7th assessment report. Some aspects are already written into the chapter outlines. For example, the issue of climate interventions. So there is research going on now into solar radiation management and other things. Tipping points are on the agenda. Also, how do we get to a net zero world in the future? What are the pathways towards that? What are the dangers of overshooting our, let's say, 2-degree or 1.5-degree targets and taking the wrong paths? Are there any hysteresis in the system? One issue I'm wondering about, and which certainly improves the monsoon when you get to very high resolutions and the kilometer scale, is when we start to get to those convective resolving resolutions, will we get a different message for monsoon climate change in the future? So we do need to think about upscale feedbacks. And of course, the issue of AI should be on the agenda as well. So thank you very much for your time, and I'm happy to take any questions.
Thank you, Andy, and house is open for a couple of questions.
Okay, Andy. I just want to understand in all the projections, do you see any fundamental changes in monsoon, how we understand? Do we have to revise our definition of what is onset, what is the heavy rain, what is withdrawal, right? Do we see the danger that we'll have to redefine our monsoon itself?
I don't think we need to redefine what a monsoon is. I think that's clear. You know, as you know, it's a robust signal of the seasonal cycle. and certainly anything we do that might, let's say, collapse a monsoon, the collapse of the AMOC is not going to end the monsoon. Huge volcanoes are not going to end the monsoon. It just means less rainfall. So in that context, I don't think we need to think about redefining what a monsoon is. There are, I would say, contested works looking at how the onset might change in the future. And various people are looking at ways, and I know I've been involved in some studies with some Chinese colleagues in Nanjing that are looking at how to better constrain changes in the onsets in the future. But I think changes in the onsets and so on are quite subtle at the moment. One thing that is clear, though, you talked about heavy rain. It is very clear that, you know, the world, the atmosphere can produce much heavier rainfall when it's warmer. Those of us from Europe have seen this within the last year in Spain, some absolutely incredible rainfall and levels of rainfall that have just swamped whole cities that we would never have occurred to us years ago. You know, I remember back to July 2005 and the meter of rain that fell in Mumbai on that day. So those type of things are going to get worse and more frequent in the future, and so society has to be ready for that. Thank you.
Yeah. Hello, Andy Krishnan here. That was a nice talk. I really enjoyed. Regarding the AMOC collapse, you said that is it's low likelihood or medium confidence, something you said during the 21st century. But some people say this is a very conservative assessment. There is a view I heard from some of the AMOC experts. What was assessed in is a very conservative view. So the weakening is already happening. So what are your thoughts? So is that a point you're considering in the 7th assessment cycle?
I'm sure that will absolutely be considered in the 7th assessment cycle. I mean, one thing with AMOC, I'm not quite sure how it's received in India at large. Certainly in the UK, talks about the AMOC collapse, they get much more prominent media attention than, for example, the monsoon does, because of where we are. And there's been several studies out recently which have said exactly what you've said, that we're underestimating the potential for this. I know other scientists that I work with closely, near me, that are they're not so worried about that in the same way, but it's clearly going to be a big topic for study in the next IPCC report. I think it's also a lesson for young scientists and so on, that often studies come out that contradict the previous study, and something like the IPCC is tasked with assessing the evidence as a whole. That has advantages, but it also has disadvantages, because it means that by its nature, it is a little bit more conservative, perhaps, because it has to gain a consensus of looking at all of the evidence. Yeah. So absolutely, thinking about AMOC collapse in the AR7 is going to be a really important topic.
Yeah, in that case, it may not be a low likelihood. But
it might be not as low likelihood as we think. And if we flick back very quickly to my slide on the AMOC, where was it? Here we are. That wording doesn't fill me with confidence. It says there is medium confidence that there will not be an abrupt collapse before 2100. That doesn't fill me with so much confidence. So yes. People in India and everywhere else do need to be working on AMOC issues still to understand what's going on, both in modeling and observations.
Yeah. Okay. Yeah. Thank you, Andy. Thank you so much.
Thank you, Andy. And I'm sure you've given a food of thought for AR7, and positively you'll get a lot of inputs from Indian colleagues and the participants of this workshop. Thank you.
Thank you very much.
Next lecture also online. Is this speaker available?
Hello, yes, I'm here. But
Yeah. Good afternoon. Welcome, Eleanor.
Thank you so much. Lovely. Can you see my slides?
Yes, please make it full slide.
Oh, yes, that's right.
Presentation.
And here's me. Hello. Lovely. Well, thank you so much for inviting me to this meeting. My name is Eleanor Blythe, and I work at the Centre of Ecology and Hydrology in the UK. But I'm also part of the Joint Science Steering Committee for WCRP. So that's how I think you know about my work. And what we work on is the land part of the climate system. So I might have some slightly controversial things to say to an audience of people who study the monsoon, but I'm going to show you how we see how the land atmosphere system works. So just to start right at the beginning, this is a classic diagram of the water cycle, and I think there are some interesting things to note. It isn't full. That's better. This diagram was actually put together by Kevin Trenberth, who was part of GWEX. And when at school or whatever, you're taught that the ocean has all the evaporation of the water. So the water cycle starts in the ocean, and then the water comes over land and it rains out, and then it goes back to the ocean through the rivers. Now, actually, that's a misconception. Most of the rainfall that falls on the land comes from the land itself. Okay, so only 35% of the rain that's falling on the land has come from the ocean. And not only that, but much less water goes back to the ocean through the river system than is re-evaporated. So clearly there's a land atmosphere system going on here that is providing the rainfall for the land system that we depend on. So it's just worth remembering that, especially for people who are more used to the ocean land dynamic. And what is absolutely critical for this dynamic is the spatial patterns of the land system in contrast to the ocean, but also within the land system. So when I talk about spatial patterns, I mean spatial patterns of the energy and water system. So yeah, I'm speaking to experts here, but the top left-hand corner is something that you must have been taught very early on. So you already know about the climate system and how that works in terms of where the rainfall is really concentrated on our planet. And so you already know that it goes mainly across the tropics because of the big thermodynamics of the climate system. And so we get this pattern of rainfall that's there on the top right, where there's a huge amounts of rainfall across the tropics. Then there's a band of dry, where the air is actually is the subtropics, where the air is descending, and then it gets wet again in the mid latitudes and so on, and then gets dry again. And those patterns of rainfall create patterns of vegetation. So that is clear. We know that clearly in the tropics there are very lush trees and huge leaves holding up lots of water. And then we get the dry desert areas where there's very little vegetation. If there is vegetation, it's very sparse. The soil is exposed to the atmosphere. And yet again, we get the mid latitudes where we get some trees, but they tend to be deciduous. We don't get evergreen trees so much. And then the far north, where the vegetation is becoming very sparse indeed because it's so cold. So the question we ask ourselves in the land community is, we obviously understand that the rainfall patterns are creating vegetation patterns, but can we think about the other way around? Do the vegetation patterns themselves affect the rainfall? So it's that feedback from the land system into the atmosphere system, which is what we're interested in. So what we call this is the land atmosphere system. So it's not so much the monsoon system, it's within the land and within the continents. Can we understand that system? And this image here is just to show, you can see from any kind of satellite product that clearly the land is affecting the clouds and therefore the rainfall. It's producing convective storms. It's controlling where the rain is occurring as the rain comes in from the oceans. And this is something that is important for your community, for monsoons. The land system, it's often considered that the ocean is the biggest driver of the climate system, but the land also plays a part. Now, it tends to play a part on a shorter time scale. So the memory of the heat budget of the oceans is quite long. It'll be often years, years or seasonal. Whereas the land system tends to dry out and changes its energy budget within weeks. But the atmosphere has quite a short time, a short memory. So that weekly memory, that the daily or weekly memory that the land holds, can affect the atmosphere and can affect rainfall events. And I'm going to show you some examples in this talk. But before I do, I just need a couple more of the sort of basics of the way we look at evaporation and how that affects the energy budget of the land. And the thing about evaporation is that it depends what kind of evaporation it is. And it's very important to understand this. So evaporation for the land system has three major components, and they have very different timescales. So if the rain falls on the leaves of the trees and so on, and then re-evaporates straight away, we call that interception or canopy evaporation, and it's very fast. So the trees will tend to dry out. That evaporation is a very small store. The trees are holding that water right up into the airflow, and it will be gone within a day. So interception, very fast. Bare soil evaporation, however, also quite fast. It will either drain away or evaporate within a few days. So a wet soil will dry out quite quickly near the surface. That's what we're talking about. The surface of the bare soil will dry out within a few days. Transpiration, which is the classic evaporation that people know about for the land, however, is very slow. So the roots of the vegetation go quite deep. It won't really dry out, I mean, for weeks, if not months. So it can stop raining and it will still be transpiring a couple of months later, because the trees have control, access to much deeper soil, and they also control the evaporation through their stomata, so they don't let it go very quickly. And then there's another one, snow sublimation, which I might pick up in the talk if I've got time. So we've got three very different timescales. Remember, and you're all physics trained, I'm sure, in this audience, if you change your water, you're massively changing your energy. So evaporation takes up a huge amount of energy, and therefore it cools the land. Every time it happens, it cools the land. So the water patterns that you get on the land are really affecting the heat patterns, and therefore affecting the thermodynamics of the atmosphere. And the patterns on the land can create quite big thermodynamic patterns in the atmosphere that can steer storms. Storms will follow the tracks that have been created by the land. So the land is very much controlling where it rains, and sometimes when it rains. And these are the examples I want to show you. Now, the way that we do this in models is, this is just a schematic of a classic land model. And we take account of all these different types of evaporation. We've got transpiration, interception, we have soil surface evaporation, we have the radiation coming through and emitting again. We also have quite detailed soil physics, we have quite detailed snowpack representations, and these are all working on an hourly time step. And we account for the turbulent transfer of all of these through the canopy and out above the canopy. So there's quite a lot of processes going on, but just sometimes, we find that we've missed something, or we've parameterized it based on some data that was quite historic, or we've parameterized it for representing very large scale, like 100-kilometer grids, the classic sort of GCM grid, and now we're having to parameterize it for 1-kilometer grids. So there's still a lot of work to be done to capture the vertical processes of these water and heat fluxes and their timing. And that's the business we're in. But we're very much geared towards getting the timing of the evaporation and the spatial patterns of that right, so that the atmosphere can pick up the right structures for its work. So just before I go to my case studies, this diagram I've been working on with a colleague, and because I'm interested in the timing of the evaporation, I'm also interested in the timing of the rainfall. So how often does the rainfall systems come through? Okay, and because if there's some kind of resonance between the land and how it's responding to that rainfall, and then the subsequent rainfall coming in, that could exacerbate or dampen the rain systems coming through. So this graph is showing the 4 seasons. So Northern Hemisphere, winter, top left, spring, summer, autumn. But if it's Southern Hemisphere, it's the other way around. But you can see there that the tropics, the rain comes in fairly frequently. Within a few days, you'll get the next rain event, especially if it's the rainy season. And then in the mid latitudes, it's more seasonal. You get more likely to get rain in some seasons than others. And I'm going to look at 3 case studies. One in the subtropics, where the rain is coming in every 3 days pretty regularly in its rainy season. So we're looking at the Sahel there, which is where we've done a lot of work. I'm also going to just briefly touch, but I won't spend long on it because I know you're probably not so interested, but the boreal system, and that's where the snow and the trees interact. And then a little bit on the tropical rainforest, which I expect is also of interest, where the rain comes in daily. You've got daily rain coming through there. Okay, so we'll stop the subtropics. So this is that image at the top you can see is from the Sahel. And what we have there is very sparse vegetation, a lot of exposed soil. And the rain on the bottom left, I've got just a classic sort of what's the weather like. This is the climatology of Ouagadougou. And there's a season there in June, July, August where the rains are coming in pretty hard. That's when the West African monsoon comes through. The rains are coming in every 3 days. It's very, very regular. And it's hitting quite a lot of bare soil. So this is very much a soil system for us land modelers. We've got to make sure that the timing of the soil evaporation is right so that it's capturing the dynamics with the rain as it's coming in every 3 days. And what we found was, this study was done quite a while ago. There was a huge field experiment out there in the 1990s. And we realized, this was for large scale models, that the rainfall was actually coming in not only was it coming in every 3 days, but it was coming in very densely packed. You know, there were small convective storms coming through. I mean, they're probably quite big, but they weren't as big as the grid box. And the way that the land system works, and it still works like this, is it takes the average rainfall, it takes the rainfall spread over the whole grid, and then treats that as though it's uniform across the whole grid. Now that means, because the soil hydraulics is very non-linear with soil moisture, that we'd slow down the flow of water down through the model. And it meant that we were getting our rainfall rates, the impact on the atmosphere was wrong. We were getting the rainfall was coming every day instead of every 3 days, for instance. It was coming at the wrong time of day. So what we did was we changed the soil physics model so that it accommodated the fact that actually the rainfall was coming in dense pockets, and increased the drainage of the water, and it changed the rainfall so that it came every 3 days instead. So the speed of the drainage of the soil affected the timing of the rainfall. Case study 1. I've probably run out of time. My case study 2 was about the boreal zone, and that is about how long wave radiation, I'll give you the punchline, long wave radiation is transferred from the trees to the snowpack below to increase, to speed up the snow melt. And this actual process is not in the models. There isn't a long wave connection from the vegetation to the snowpack below. And it means that we're not melting out the snow quickly enough when there are trees. And there's observational evidence that is true, that the presence of trees speeds up the snow melt. And that's against some intuition that might expect it to protect the snow because it's absorbing all the sunshine and shading the snow. But actually the long wave radiation is probably causing a faster snow melt. My final case study is probably something that you're all much more familiar with, which is about how the rainfall, for instance, in the Amazon rainforest works. So the moist air comes in from the oceans, and if there weren't, the process I'm wanting to advertise to you here is interception. So interception is when, as I said before, the water arrives on the leaves of the trees and re-evaporates very quickly. Now, there have been many studies to suggest that if that interception rate is slower or it's non-existent and all the water falls down and the only evaporation is through transpiration, then actually the rainfall would stop a few hundred meters in from the ocean. But what happens is thousands of kilometers downwind of the ocean, it's still raining. And it's a recycling of the rain through this interception process. So the existence of these big rainforests where the original water is coming in from the oceans, but the land is recycling it through this interception process. And the rain is coming every day, and the interception works at that time scale. It's re-evaporating that within the time scale of the rain coming through. And there's been some lovely studies showing this, not only from observations. So they were looking at if you how likely is it to rain over dense canopies as opposed to sparse canopies, and the dense forests produce about twice as much rain as sparse canopies. That was done from observations. If you then put that all through into a model, you find that the rain, when we have deforestation and a climate change, the deforestation itself will suppress the rainfall. And so it's very difficult to get that rainfall back. And this is a lovely study by Dominic Spracklin around that. So I hope I've persuaded you that the land processes are really important for the atmosphere systems and the rainfall and so on. So as well as the monsoon work that you do, which is obviously really important for the large scale patterns, once we get into the land system, we have to get the physics of the land system right so that it can interpret that and get the feedbacks right within the continents. So thank you very much.
Thank you, and house is open for a couple of questions.
Thank you. Thank you very much for the nice presentation. The question is about soil moisture and precipitation feedback. For example, you mentioned it's quite important. Of course, it's known. But in terms of this coarse resolution global models where we use parameterizations for convection, somehow the precipitation and soil moisture feedback is kind of overestimated. But when we go into the kilometer scale simulations, we see an EVICA feedback, let's say. So do you have any opinion on this?
Yeah, very much so. I mean, the thing is, the models have been were really designed with those large scale climate models in mind, and the soil physics is a really tricky thing. There are lots of things we're trying to look at to try and get this right. One is that you've got, as I said in the talk, you've got the vertical speed with which the soil, whether it holds the water near the surface or it drains it out. But there's also issues of redistribution of the soil water. Now, at large scales, we didn't have to worry about that. The rainfall that arrived in that grid is then available for evaporation, albeit at different timescales. But now we're working at smaller timescales. The water might be transferred from one part of the country to another to re-evaporate. It might come out in wetlands or inundated areas downstream. So the soil moisture atmosphere feedbacks at fine scales, it's keeping us busy, let's say. I think now that we've got convection permitting rain, that's the other thing that's happened, is that we have to accommodate the actual rain intensity, which affects the infiltration. So again, before with climate models, we had just sort of average rainfall intensity across the whole grid. We had a way of then clustering that to make it more intense in some places and less intense in others. But now we're getting the actual intensity because we're, say, running at 1 kilometre. And it's really challenging our land models. We've got to accommodate the actual intensity of rainfall and to get that vertical, to get the vertical structure of the water and make sure it's evaporating out at the right time. So we're very busy. As Andy said, going down to 1 kilometre, it's for the land models, it's not just about a computational difference. We've got a process difference. You know, we've got to actually bring in new processes like transfer of water sideways or bringing in inundation and so on. So we are really, really working hard to make sure we can deliver good land systems to work at the 1 kilometre scale to match what's going on with the new convection permitting models.
Thank you. Well explained. And now, okay, Dr. Krishnan.
Thank you very much, Dr. Elena. This is Krishnan here. I really enjoyed your talk. We listened to Andy Turner and other talks. So in the future, with global warming, the Afro-Asian monsoons rainfall is going to increase. So in the coming decades, we can also see vegetation changes, and it's already happening over India, in parts of Northwest India. Rainfall has increased. There are also changes in the vegetation. So what would be its feedback on the precipitation itself? So you touched upon that, but that is going to be very important.
It is really important. I mean, the vegetation, I mean, as it's quite interesting actually, because it depends. Sometimes the vegetation speeds up the water cycle. As I say, if it's intercepting a lot of water and re-evaporating it, it actually means that you've got a quicker recycling of that rainfall. But on the other hand, places where the rain is only coming in every few weeks, it can slow it down. So, for instance, for the UK, for Europe, it can change the response of heat waves because they're still transpiring even when it hasn't rained for months. So it keeps it cool. If you've got more rain coming in, you've got more potential for growing these big carbon structures called trees, and they do change the energy budgets of the land. So it's really important. Most of the vegetation dynamics models have this in them. They will be able to predict that change of vegetation and then its effect on the energy and water. But yeah, no, it makes a really big difference to the weather systems, undoubtedly. Yeah.
Thank you so much.
Thank you. And now we move to the next speaker, Annalisa. Are you there?
Yes.
Okay, over to you. Welcome.
Thank you. Trying to share. Okay. Do you see my slide, right? Okay. So thank you for this opportunity. I'm Annalisa Chierchi and I work at the National Research Council of Italy in Bologna. And this talk is about global and regional monsoons in a changing climate. And this has been done in collaboration, and I would like to acknowledge my co-author, Anja Katzenberger from Germany, Krishnan, Ashwin, and Sabine from IITM in India, and also Andrew Turner from the University of Reading that already introduced some of the figures of this analysis. So my talk is quite simple. So the outline is just I start from as background motivation from the outcome that we have seen also in Andy's talk about the monsoon projection in the IPCC-R6. I will describe the method that is mostly based on the figure from Anya's paper in 2021, and then we will look at the diversity in the hydrological sensitivity of global and regional monsoon, and then I will give you a summary and a few perspectives. So the starting point is the definition of global and regional monsoon. And the definition of global monsoon is dated back in the works that Professor Wang did in the 2000, where the global monsoon was identified as the hemispheric antisymmetric solstice mode of the distribution of annual precipitation. And it's basically the differences between what happens in the summer of the Northern Hemisphere and the summer of the Southern Hemisphere. Starting from this definition of the global monsoon that is shown here in terms of empirical orthogonal function and principal components, there have been a lot of literature where also the regional monsoon were identified as enclosed and part of this large-scale feature. But in the last IPCC report, as also outlined by Andy, the regional monsoon where there was a sort of balance in the definition of the regional monsoon, going back toward the definitions, the classical definitions that each regions had in the past, and also trying to combine the information and the definition from the global monsoon. In the IPCC and also in our study here, the global monsoon is defined as the area where there is this local summer minus winter precipitation rate that exceeds a certain thresholds, and then the regional monsoon are the color one in the figure. This is one of the one figure that shows how the global land monsoon precipitation is changing in future, distinguishing what happens in the near term, mid-term, and long term. And in terms of precipitation over land, there is a tendency toward an increase of precipitation. And if we look at the circulation index measured as the difference between what happens in the upper and lower troposphere, there is a decrease in the intensity of the circulation. And there are diversity, as also Andy mentioned, about what happens in the near term and what happens in the long term, and also what are the influence that we can get and what affect these changes in time. So the model uncertainty and the role of the model uncertainty and the role of internal variability tends to dominate what is the changes in the near term, whereas in the future we see a clear identification of this increase of precipitation, at least for the global land monsoon and also for some of the monsoonal region. And in fact, here, if we look at the different regions separately, we can see that you can see here toward the end of the figure the global monsoon and how there is an increase from near term to long term in the monsoon precipitation. And you see that there are monsoon where this increase is also shown, like over Australia, East Asia, even West Africa and South Asia, where this change is the largest one. But there are also regions where there is very small changes or even a decrease in these changes in precipitation. What we try to do here is to go a bit beyond this kind of evaluation and taking the CMIP6 models here. There is just one model per each institute, but of course we try to use as much as simulation were available, and looking at the historical, but mostly looking at the differences in the future scenarios with respect to the historical. And the 4 scenarios that we consider are the scenarios that were used also in the IPCC-R6, so the SSP 126, SSP 245, SSP 370, and the most extreme scenario. If we look at the differences between the summer and winter precipitation, we end up with this figure that clearly represents the global monsoon precipitation. This is what happens in the observation taken here as a GPCP dataset. And this is what happens in the multimodal ensemble of all the historical simulations that we have selected. The black line corresponds to the contour of the global monsoon, where the JJA minus DJF precipitation exceeds 2.5 millimeter per day. There is a realistic representation of these regions in the model, but there are underestimation in some places of the precipitation. And then if we look at what happens in the future, we see that there is a tendency to have higher precipitation in the climate scenario with respect to the historical simulation, even if there are diversity and nonlinearities that could be better understood. And in terms of methodology, we mostly focused on this type of analysis that was published in 2021 by Anja Katzenberger. And I really liked this picture when it came out, and I'm still convinced that it contains a lot of very interesting information that we, in fact, try to understand a bit more, that show how the monsoon rainfall, this is the case for India, changes with respect to the global warming increase. In a methodology framework, the reference period for the difference is this one, 1985 and 2014. And what she did is taking 20 years future period with 5 years time steps and taking the differences progressively. This is for all the members, all the model, all the scenarios that she has on hand for his work on the Indian monsoon. And this is on the right, the multimodal mean for each scenario. And as Andy already mentioned, there is a very clear increase in terms of precipitation as function of the global warming. And we decided to apply it for the global monsoon and also for the regional monsoon to see what kind of differences we were able to spot. And this is the response in terms of the global monsoon. So we have again here these differences in the monsoon rainfall over the global monsoon regions. That is the black line and the black line here that we defined before, and as function of the global warming increase. And this is what happens in terms of multimodal mean for each scenario. We took the global monsoon and we also tried to look at the differences and diversity, taking the global monsoon just in the Northern Hemisphere or just in the Southern Hemisphere or in the Eastern Hemisphere or in the Western Hemisphere. And there is a common signal that is if we try to look at the linear regression fitting at the monsoon rainfall increase for global mean temperature, the increase is the least in this scenario, that is the 3.7 scenarios. That is not the scenarios where the radiative forcing is the smallest, but it's the cases where there is the least increase. And this is evident mostly for the global monsoon in the Northern Hemisphere and in the eastern part of the hemisphere. And looking at the different regional monsoon, we see again similar feature here in the left panel, where we are looking at the South Asian monsoon, East Asian monsoon, and the Australian monsoon. And on the right, we have the other three regional monsoons, the West Africa, North America, and South America. Looking at the diversity within this graph, this is reminiscent of some ideas that I also published a long time ago now, where there was a sort of distinction between what were defined as the classical monsoon and the other type of monsoon, thinking of the, let's say, classical monsoon having a sort of better response or direct response to the thermodynamic with respect to the dynamics. And this diversity appear again here. In the South Asian and East Asian monsoon, the behavior of this and the differences and nonlinearities in the behavior of these scenarios, SSP 3.7, appears quite clear, mostly for the East Asian summer monsoon. And we decided to if we want to understand what happens there or what could be the reason for this diversity, this figure came to our mind. That could be a way understood better these differences and to dig more and found better evidence for this. And this shows the change in the aerosol optical depth and for the black carbon in the top row and for the sulfates in the bottom row. And you see as that there are differences in terms of the policies taken for strong air quality or medium air quality or weak air quality in terms of the changes in the distribution of this aerosol and the quantity of this aerosol. And you see that the SSP3 is really different from the other in terms of what is the changes in the black carbon and also in the sulfate. And is quite clear for us that is these differences that can explain this nonlinearity. The reason is that we know that black carbon and sulfate aerosol has a different response in terms of radiative forcing and then in terms of the precipitation. And so what came out from this, comparing this information about the concentration and the emission of this aerosol and what happens in terms of the response of the monsoon precipitation, it is clear that despite weaker quality policies and increased black carbon and sulfate aerosol optical depths in this SSP3 scenario, there is a precipitation increases that is less intense with respect to global warming compared to the other scenarios. And this again highlight what is and how complex is the aerosol climate interaction, and that there is important role of regional feedbacks and still problem in representing all this process in general circulation models that needs to be better investigated and better clarified. Then looking at the other monsoon regions, we see other interesting aspects that we wanted to highlight. In the case of the West African monsoon that is here on the top, we see again the changes in monsoon rainfall with respect to the global warming for all the members, and we see here the ensemble mean for each scenario. And there is a quite strange behavior where we see an increase up to a
You have
certain
2 minutes
threshold.
to close.
Sorry?
You have 2 minutes to close your
Yes.
Thank you.
Thank you. And then there is a sort of a flattening of the changing here. In this case of the West African monsoon, as was already also mentioned in by Matt Collins here a few talks before, there is a good interplay and interesting interplay between what are the anthropogenic emissions, but also the changes in the temperature of the subtropical North Atlantic Ocean relative to what are the changes in the global tropical ocean that needs to be further investigated and understood. Then the other two cases, the North American and South American monsoon, are the cases where you can see the largest uncertainties among the models, because there are models that goes in one direction and models that goes in the other direction. So it's really hard to identify a clear change, a clear signature of change. And so this still needs to be eventually better analyzed with more members, more information, and also thinking of other effects, or like the gradient in the SST, as also was shown in another talk this morning by a colleague, and that could be very interesting to further investigate. So this is what I wanted to show. Monsoon precipitation increased with global warming, mostly for global monsoon and the Asian monsoon. We spotted some nonlinearity in terms of the radiative forcing because of the diversity in the response to the different type of anthropogenic aerosol. There is one specific scenario where these changes are the largest and could be useful to investigate in more details. There are diversity in the changes in the West African monsoon because of a combination probably of a response to SST and response to anthropogenic forcing. And there are the largest disagreement in the American monsoon that we need to investigate a bit more. I thank you for your attention, and I'm open to questions if there are any.
Thank you, Annalisa. And yeah, you are invited for questions. Are there any online questions for her? I don't think. Okay, thank you once again. And now we'll move to the next speaker, Helena Ratnawati from Indonesia. Is she available online? Okay, if she is not there, then next speaker is Hunt from UK. He's okay. Welcome. At least we have physical presentation also in this session. In person.
Thanks. Just going to set a timer on my phone so that I don't overrun horribly. Actually, maybe if you could give me a bell at sort of 2 minutes to go, just so I can wrap up. Oh, all right, fine. Oh. Brilliant, thank you. Yeah, so I guess if you know me, you'll know that most of my work has been on Western disturbances. I'm afraid this talk isn't on Western disturbances, and it's not on AI either, which is my other kind of main topic recently. But if you've known me for a very long time, you'll know that my PhD was on monsoon low pressure systems and depressions. And there was always something that stuck in my mind when I did the PhD, which was that I never got to look at these things in climate models. And so now I'm a member of faculty. I've got a bit more time to do this kind of research, this kind of hobby research. And so I took some of the old equipment that I had for my PhD, repurposed it, and I've applied it to climate models. I'll just start with this animation, which hopefully will, oh, do you better play. I spent ages making this. Oh, come on. QuickTime not available. Oh, no. All right, well, if you follow me on LinkedIn, you'll have seen this. If you don't follow me on LinkedIn, do, and then you can watch it. But what you would see is rainfall in all different scales. It's sort of like a buffet, right? You've got very small kind of popcorn convection going on. Incidentally, this is output from a 1.5 kilometer model that we ran for the 2016 field campaign. This is about a 10-day long simulation of an LPS that became a depression that we then flew a plane through. But within that depression, there's all these different scales of rainfall going on, right? There's this popcorn convection, there's mesoscale convective organization, there's mesoscale convective vortices that spin up, there's lots of action around the orography and stuff, and then eventually it sort of aggregates into some relatively synoptic scale patterns. But the important thing is that almost all of these interesting features are happening at scales much smaller than the climate model resolution that I'm about to show. So basically, the entire rest of my talk, you could disregard as being rubbish. Hopefully, I'll convince you that's not quite true, because the argument is that even if we have to parameterize a lot of these processes, the statistics of LPSs are still reasonably well represented in CMIP6 models. Yeah, boring slide on methods, but unfortunately a little bit necessary. To capture these LPSs in CMIP6 models, we use a kind of very standard tracking methodology. It's you take the relative auticity in the lower levels, you do some smoothing to get rid of the high frequency noise and transient events and that kind of thing. And then we find the local maxima and we link them together in successive frames, basically. But to be able to do that, where's the pointer? Here we go. To do that, maybe I'll just come to the board, actually. This is exciting. Where are we? It's all back to front now. Yes, to do that, we need to make sure we've got 6 hourly data, because if we only have daily data, the systems move too far and too quickly, and it's not very helpful. So we need to have wins at 850, 6 hourly intervals. And any CMIP6 models that have that for any of the scenarios, we use that data. But what we want is to be able to create a multi-model mean that is slightly more authentic than if we just crammed all these CMIP6 models together without thinking. And so for that reason, we developed this metric. I'm probably standing in front of this for most of you, aren't I? We developed this metric, which is it's given this acronym FLIP, which stands for the 4 things that we measure, which are frequency, location, intensity, and precipitation. Without going into too much boring statistical detail, basically what you do is you measure how far away the distribution in the CMIP6 historical run is from era 5, which we use as truth in this study, with 1 being effectively indistinguishable from era 5 and a score of 0 being basically as far away from era 5 as you possibly get. And we score each of those different metrics, each of those different statistics, and then just take an arithmetic average. And at the very end of the talk, if I get there, there'll be a bit of storylines as well. But to be honest, we can cover that when we get there. So this is the kind of the first initial thing that we've got to do. We've got to evaluate the models and make sure that they are representing LPSs properly. And so this is the first component, or one of the components of the FLIP score. It's location. So we take all of the tracks in the historical period where that overlaps with era 5. And it gives you can compute a track density, right? So you've got hundreds of tracks for each model. You compute a kernel density estimate, and you get these nice little contour plots, which are, there are many of them. But basically, you can see that most models are kind of capturing. So this is era 5. This is the truth. Most models are reasonably well capturing that fact that you have the maximum of the Bay of Bengal, as you would expect, and some penetration over the Indian subcontinent. That's fine. Some models do a pretty rubbish job, either in terms of frequency, you've got this sort of very weak number of systems here or here, or, they don't penetrate inland. But there's quite a lot of model diversity. But one thing all the models do really badly on is systems over the Arabian Sea, which I won't cover in this talk, but it's something to bear in mind in the future that we want to sort out, because they will become more important as the climate changes. Where am I? Oh, God. All right, there we go. So this is the FLIP score altogether. This is the last slide on model evaluation. Most of you will probably be pleased to hear. And what we do here is we plot the score of the model against the effective resolution of the model. So we just take the hypotenuse of the grid spacing, basically. And there's a very clear indication that increasing model resolution improves the skill of the model. I don't think that would surprise anyone here. What would be interesting is what the shape of this distribution looks like as we get into the K scale, I think. So you have era 5 at the top at 1 there. And whilst there is this kind of general trend, some models with a very high resolution are kind of rubbish, whereas some models with a coarser resolution, like NOAA's GFDL, actually do okay. So we use this score to weight our CMIP6 multi-model mean. And basically that means that we're kind of encouraging a little bit more information from the models that represent LPS statistics well. And we're kind of not looking so much at those models that don't. But they're still included because we do want model diversity. Of course, if you saw Paul Arthur's talk earlier, you'll know why. Right, so what do we find out in the future? That's all historical model evaluation, boring stuff out of the way. Let's look into the future. Well, here are 6 statistics of LPSs that I think are probably reasonably important. And what we do here is we look at the statistics and how they change as a function of global warming level. So global warming level is basically the mean temperature of the Earth relative to the pre-industrial period. So 0, I'm pointing at the wrong screen there. So the blue line shows 0. That's basically a sort of pre-industrial and early historical. 1 degree is sort of about where we are now, and then 2 up to 3 degrees shows the future. And there's a window function in that. You don't need to worry too much about the detail. But what you do need to worry about is this very dramatic increase in precipitation, right? So again, not too surprising if you followed the talks earlier, monsoon precipitation expected to increase, but it's coming whilst the LPSs themselves are getting weaker. This is a per LPS precipitation, so it's not a function of frequency. Each individual LPS is raining a lot more, but it's getting weaker. So again, this is a symptom of the monsoon circulation, right? And we'll get onto this in a bit. The monsoon circulation weakens, but there's more precipitation. That's true for individual LPSs as well. Now, there are these kind of insignificant changes down here. Propagation speed probably going to increase a little bit, maybe going to increase a little bit. Post-landfall duration, that's quite an important statistic, but there's not really a strong indication that's going to change by more than a few hours. And what we'd also find is that the fraction of systems making landfall is likely to increase. So those are kind of overall statistics. But what about the LPSs themselves? What do they actually look like in these future climates? So here I've taken some storm-centered composites. So basically we take the center of every system and then we stack information on top of that. You're probably reasonably familiar with that. This is what the storm-centered composite precipitation looks like in ERA 5. There's precipitation sort of slightly to the southwest of the system, and most of the precipitation is confined within about 400 kilometers of the system center. CMIP6 models do quite a good job of modeling that, surprisingly good given the grid spacing, actually. They tend to underestimate precipitation a bit for various reasons I won't go into. When we move into the future, as we said, there's going to be this increase in mean precipitation associated with the systems. But what's quite interesting is this Clausius-Caplayron scaling. So you'll remember from earlier talks, we expect about a 7% per Kelvin increase in moisture availability. You might expect that naively to project onto the precipitation mean as well. And averaged over the systems, it sort of does. But there's very asymmetrical changes. So in the southwest quadrant, we're getting this very strong super CC scaling. Here at 2 degrees, 21% more precipitation, right? Here, where you would only expect 14. Here at 3 degrees, we'd only expect 21% more precipitation if it was CC scaling, but we're getting over 30. So what's going on there? Well, there's a couple of different things that probably lead to this. The first is the change in the structure of the LPSs themselves. And the other one, which I'll get onto in a bit, is the thermodynamics of the environment that they sit in. This is the vertical storm structure of LPSs. So ERA 5, this is showing meridional wind speed, by the way. So you basically take a slice through longitudes through the center of a depression. And then you have northerly winds on the west-hand side and easterly winds on the right. And the reason the easterly winds are higher nearer the floor there is because you've got the ocean and there's less friction, right? Again, CMIP6 multi-model mean does actually do a very good job in terms of the structure. It slightly overestimates the intensity, but not really as too much that we're not really worried about that. Now, as we move into the future, the changes to this structure, well, as we saw earlier, the systems are going to get weaker, and we see that reflected in the wind. The northerlies get anomalous southerlies, and the southerlies get anomalous northerlies. Okay, that's fine. But take a closer look, and you'll see that the pattern of that does not rectify directly onto the mean. So here, the wind speeds are, the maximum change in wind speed is happening at a slightly wider radius than the radius of maximum wind speed, right? This is further away from the center than this. And that means that these systems are probably shrinking a little. But more importantly, look at near the boundary there here, right? So the wind's very strong. There's a lot of frictional convergence. That's a very important process in LPSs. But there's very little change to the wind speed near the surface in these future projections. So per unit intensity of LPS, the frictional convergence associated with that system is actually increasing. Basically, the near surface dynamics of that system are allowing more convergence to happen, stronger precipitation. Did I just have that? That was called text. That's not a very good title for a slide, is it? Right, so we'll finish off with some storylines. To get these storylines, we take all of the CMIP6 models again. We just take their monthly averages and turn them into seasonal averages. So that's JJAS, and we get lots of stacks once we average over, once we aggregate over all the models and all the scenarios and all the model years. And then we cluster those on 850U, 850V, and specific humidity. And we get 4 clusters out for that describe different futures for the monsoon. Here's the first one that I'm going to bring to your attention, and this is the one that will probably look quite familiar from studies that you've looked at. Basically, monsoon circulation weakens, so you get this kind of gyre, this anomalous gyre over. This is, by the way, this is 2 degrees minus 0 degrees you're looking at here. So this is the change basically from the pre-industrial to sort of about 2030 to 2050, if you like to think of it like that. We get this anomalous gyre over the Bay of Bengal. Well, that's obviously bad news for low pressure systems. And there's a lot more moisture flux going into northern India. And that results in this north-south gradient of humidity change. So the colors you see, we're getting much more moisture in the north and we're getting more moisture in the south, but not so much more. And that means that as an LPS moves into that environment, ahead of the system where the precipitation is falling, that precipitation is being brought in on northerlies, and those northerlies are now carrying relatively more precipitation, right? So how does that rectify onto tracks? Well, as we might expect, when you slam an anomalous gyre into the area these things tend to spin up in, the track density falls quite a lot. So in this scenario, you get far fewer systems in the Bay of Bengal. But you might have seen on an earlier slide of statistics that the frequency increases, and it does, but that's because systems are starting to spin up at the edges of this gyre where there's a bit more barotropic instability. So you have some over Bangladesh and some more over Sri Lanka. So you're ending up essentially with this spreading out of LPSs in this scenario. Now, we know there's an increase in frequency, that's fine. We expect the increase then expect a decrease in intensity of about 13% in this storyline for LPSs. But look at this increase in precipitation. It's absolutely huge, 37%. More than a third increase in per LPS precipitation in this cluster because it's just so moist. It's such a wet cluster, this one. Maybe even, Anyway, we go on to the second storyline. You'll see it's slightly dry, right? And the circulation changes are quite different in this cluster. So here, again, we've got this pronounced north-south gradient in the moisture trend. But instead of a weakening of the monsoon here, really, we just get these kind of anomalous easterlies. Now, if you know about LPSs, you'll know that many LPSs arrive in the Bay of Bengal as these kind of pre-vortex seeds, these kind of mid-level to lower level, small vortices, mesoscale convective vortices that come from Southeast Asia and beyond. If we increase the easterlies, well, we increase the transport of those seeds, and there's not really a change in the barotropic instability because we're just adding easterlies everywhere. So as a result, the frequency of LPSs in this cluster goes up a lot. But because the total moisture in the environment isn't going up as much as the first cluster, we're not seeing much of a change in precipitation, and we don't see any change in intensity in this cluster because effectively the barotropic nature of the monsoon hasn't really changed substantially. And you can see what that increase in tracks looks like here. Look particularly at West India, right? There's many more tracks managing to penetrate into West India because you've got this steering flow that can push them in. Okay, that's the last slide of results. I'm sure you'd be glad to hear. Hopefully you've paid enough attention that I don't need to read through these again, but just in case, I think the key thing here to think about is that there's a lot of very diverse futures for the monsoon, and those are played out in very sensitive changes to LPS behavior. But one of the things that could be a very high impact result is this increase in precipitation in West India as LPSs are able to propagate through into that region more frequently. And this is what we saw in the Pakistan floods in 2022, right? It was an LPS managed to get all the way through. And we're already seeing, whoops. Let's go back. We're already seeing these impacts for West India, right? This is this dipole in precipitation trend. Okay, that's it.
Thank you, Hunt, and open for the questions.
Thank you, sir, for the nice talk. Actually, I have a couple of questions.
Good.
Why do you think that LPS intensity weakens despite there are more higher moisture is available in the future climate?
Okay.
And my second question is increase in rainfall is due to the longer lifespan of the LPS or due to larger rain rates per hour?
Okay, so to answer the second question, that's easy. It's a rain rate, so it's not accumulated rain. So the lifetime is taken out of the question. We want to separate that statistic out. So that's just because they're producing a higher rain rate, right? The first question, why are they getting weaker despite the greater moisture availability? Yes, it's a very good question. Basically, the largest and strongest control on LPS intensification and peak intensity, which is what we were measuring, is the amount of barotropic instability within the monsoon. So that's effectively the meridional gradient in zonal wind speed as you go through the Bay of Bengal and continental India. And effectively, the average monsoon circulation is weakening, and that means that that gradient in wind speed is falling, and there's thus less barotropic instability for these things to amp up. And once they've used it all, they can't really get anything from anywhere else. Now, you're right in that moisture plays an important role. The moisture is coupled to that barotropic instability. But if there's no barotropic instability, you can't have moisture coupled to it, right? Because there's nothing to grow off in the first place. But yes, good question.
Thank you. Okay, thank you, Hunt. And we move to the last presentation from the IITM. Sivan will be talking about teleconnection with the Antarctica and anticyclone.
Good afternoon, all. Myself, Shivan C., project scientist, IITM. First of all, thankful to everyone for giving me an opportunity to present here. Today, I am presenting here on the topic teleconnection between Asian summer monsoon anticyclone and Arctic. This work was done under the guidance of Suvarna Patnavis, Ajil Kotel, and Bernard Lecres. The summer monsoon circulation that plays an important role in the long-range transport of aerosols and gas that affect the radiative balance of remote location. Due to the Arctic amplification, the Arctic is warming nearly 4 times faster than the rest of the world. So the linkage between Arctic amplification and the transport of aerosols and gas from lower latitudes remains unclear. Taylor et al. 2022, this figure shows that the water vapor transport from the lower latitudes towards the poles and increasing water vapor in the Arctic causing Arctic warming, and mostly due to the heat releasing due to the condensation and the cloud formation that resulting greenhouse warming. So the Asian monsoon anticyclone that is stretching from West African region to the West Pacific, and the deep convection plays an important role for the efficient transport of pollutants from Asia into the UTLS region. And the Fatnavis et al. 2024 paper shows that the anthropogenic aerosols from East Asia that reduces the net radiative forcing in the Arctic region by 0.03 watts per meter square at the top of the atmosphere. And this causing cooling effect in the surface by about 0.56 Kelvin. And Beckman et al. 2021 reported that the black carbon aerosols from the Indo-Gangetic plains in South Asia to the Arctic occur within 7 days in the upper troposphere in summer season. So the long-range transport to the Arctic is essential for comprehending the current and future state of Arctic climate. So in this study, we are estimating the percentage of trajectory, age of trajectories, and at what level the trajectories are reaching the Arctic region from Asian monsoon anticyclone. So this model is a modified version of FlexPath that performed backward or forward trajectory analysis using reverse integration. So the trajectories that are released from a specific location and until it reaches a destination that we taken as the age of an air person. And the concentration or the distribution of a trajectories that reach a specific location we take as the percentage of trajectories that reaching there. And the vertical isotropic level that the air parts is reaching the target is taken at the impact level. So this model is very helpful to study the moment, study the transport pulses and assess their impact on various regions. So in this study, we releases the trajectories from Asian monsoon anticyclone 20 to 40 degree north and 20 to 120 degree east with a frequency of 3 hours and forward in time for 120 days and at a isentropic level of 370 Kelvin. And wind data and radiative heat rate from ERA 5 is used as the input. And 4 El Nino years and 4 normal years are selected for this study. So this is just a schematic representation that one trajectory that is releasing from 370 Kelvin and it is entering to the Greenland region. So here it is 370 Kelvin and they're showing it is 361 Kelvin. So that is the level at which it is entering there. And at what time it is taking from Asian monsoon anticyclone to reach there is taken as the age. So this figure actually, the trajectories that is releasing from Asian monsoon anticyclone at 5 equal divisions, that most of the trajectories from the edges are entering to the Arctic. So actually, we are releasing around 27 lakhs of trajectories from the Asian monsoon anticyclone region, and around 11% of that trajectories are reaching the Arctic. For examining more about the Arctic region, we geographically divide that region into GNP region, that is consists of Greenland Sea, Norwegian Sea, Barents Sea, and Russian coastal line, Beaufort Gary, and Baffin Bay. So this figure shows the percentage of trajectories that are entering the Arctic from Asian monsoon anticyclone, and this showing the time taken to reach there. So there is around 3.2% of trajectories are reaching the Greenland, Norwegian, Barents Sea region, and very less number of trajectories are reaching around the Russian coastal line region, and moderate loading is shown in the Baffin region. And while taking the time taken, there is minimum time around 56 days is taken in the Russian coastal line, and maximum time is taken in the Beaufort Gary region. So this figure showing the age versus potential temperature. So at what level it is loading. So the maximum loading we can see at 380 to 395 Kelvin isentropic level at an age of 30 to 50 days. And moderate loading we can see from above 395 Kelvin to 415 Kelvin at an age group of 15 to 90 days. And very less number of trajectories we can see below 340 Kelvin, and it is taking more time to reach there. So we are considering the variabilities during El Nino normal years. Here, this figure showing the time taken to reach the Arctic during El Nino year, and this is for the normal year. From the figure, it is clear that there is, in 4 divisions, we can see that during the El Nino period, more time is taking to reach there, and less time is taking in the normal days. In the GNP region, around 63 days is taken to reach here, but in the normal days, it is taken around 58 days. So it is so the trajectory is taking more time to reach the Arctic during El Nino years as compared to normal years. It is mainly maybe due to the lesser strength of Asian monsoon anticyclone and the more meandering pathways that during the El Nino years to reach the Arctic. And the trajectory takes around 4 to 5 days more to reach the GNP and Beaufort region during the El Nino years as comparing to normal days, and 2 to 3 days to reach RC, Russian coastal line, and Baffin region. So here we are showing the average age versus isentropic level variability during El Nino and normal years. In this, it is clear that almost all the most of the isentropic level that El Nino years taking more time to reach, and most of the trajectories that are reaching at 315 to 380 Kelvin are at the age group of 15 to 60 days on an average, where those below 325 Kelvin and above 390 Kelvin takes more times from around 60 to 100 days to reach. So the percentage of trajectories that are reaching the Arctic is higher at a Greenland, Norwegian, Barents Sea region and lower at the Russian coastal line. And the air parcels taking lesser time to reach the Russian coastal line, around 56 days, and more time to reach the Beaufort-Gary region, that is 63 days. During El Nino years, the trajectory is on an average 4 days more to reach the Arctic region as compared to normal years, and maximum number of trajectories that are reaching the Arctic at an isentropic level of 380 to 390 Kelvin.
Do I invite it? Yeah, okay.
Very simple question. Why should someone care about trajectories reaching Arctic?
Because there is transport from mid latitudes and tropics that cause changes, means the water vapor or the aerosol gases that are entering there, causing the radiative changes in the radiative balance. So that may causing more warming there.
Thank you. I just wanted to make a comment. I thought this is really interesting and supports some of the things we see that we think is worth happening is when we see changes in our model development in the Arctic and we wonder what the impact is actually from the low latitudes and the equatorial regions. And so your results really kind of, demonstrate that connection and the fact that, there is that link. And I think when we do our model evaluation and we don't understand why things are happening in our models in the Arctic, that the reasons for the issues we see are not necessarily from the Arctic, but they may come from quite a long way away. So thank you for that.
If none, then we should thank all the speakers of this session. And though we started late, but because of the absence of one speaker, we are closing on time for tea and the poster presentation. Thank you.
I would like to thank IWM Tyagi sir and every online and offline presenters as well as audience. So we are concluding this session. Now we are proceeding for the poster presentation in the Rutank first floor. And one more information is like we are having a cultural program today at this auditorium at 6:30 to 8 o'clock. And after that, there will be dinner at IITM Friend Lawn. So everyone welcome, please. Thank you.